Hi, everyone. Welcome to the 9th Annual OpenZFS Developer Summit. Thank you all for joining us. I'm Matt Ahrens, and I'll be talking to you about the state of the project and the conference. There we go. All right, so first off, I wanted to thank everyone who helped to make this conference possible. There are a lot of people that worked on it behind the scenes. So I wanted to thank Karen for project management, Victoria for helping us do the event management, working with all of our sponsors to make sure that we received their money and they received all the benefits that we promised them. And I wanted to thank Aaron Holding, who once again, for many years running, has designed the logo for the conference. I don't know if any of you recognize this. It took me a little while to place it as well. But the thing that's depicted here is called the Eye of Diablo. It's on top of Mount Diablo here in the Bay Area, and it's a beacon of light that's was lit right at the beginning of the pandemic as a symbol of hope and healing and strength for those who have been impacted by the pandemic, which is all of us, I think. So they light it every Sunday night, and we thought that it's a great symbol of the times and also the idea of bringing people together that this conference does as well. And last, I wanted to thank Prakash for helping with the IT and tech stuff. Next slide. Okay. So on to our sponsors. So I wanted to thank all of our sponsors, starting with our diamond sponsor, Delphix, which is also my employer. When we do this conference live, we usually have the employees stand up and we all clap for them. Maybe we can kind of do that virtually. I think that there's a feature in Zoom where you can raise your hand. So maybe we can have folks, it's under reactions. Let me find it on mine. I can't even find it on mine. Maybe because I'm, oh, there we go. Paul, Tony, Cameron, thank you. Manoj, I think maybe because I'm presenting, I can't react to my own presentation. Tons of folks here raising their hands. Thanks for, thank you all the Delphix employees, and thank you Delphix for sponsoring the conference. Next up, okay, there's some way that I can put your hands down. Maybe you can put your hands down, whatever. Next up, wanted to thank our platinum sponsor, Racktop. Anyone here from Racktop, please raise your hands. Thank you very much. And we can give them a virtual round of applause. Next up, Synedo, sponsoring the Gold Plus level. Synedo, any employees from Synedo here? Thank you very much. And at the gold level, Datto and IX Systems. Thank you. Any employees from Datto and IX Systems here? Yeah, see a bunch there. Thank you. All right, and then sponsoring at the silver level, OS Nexus and Open Drives. Thank you very much. And at the bronze level, FreeBSD Foundation. Giving them a chance to raise their hands. Yes, thank you for clapping and raising your hands. I know this is a little cheesy, but we're trying to, pull everyone in. And I want to thank again all of our sponsors who have stuck with us through the pandemic. There have been many of these sponsors have been with us for many, many years, and we really appreciate your continued financial support of the conference this year as we hold it online once again. Hopefully, the last fully online OpenZFS Developer Summit. We can all hope. So I wanted to take a minute to talk about the state of the project and take a moment to look back at what we have accomplished over the past year. So I reused this slide from last year. Last year we were talking about new features coming up in OpenZFS 2.0, which really will be released in 2020, and it was. So congratulations to everyone who contributed to that. It was a huge release, adding FreeBSD support, lots of features that we talked about at last year and previous year's developer summits that I've highlighted here. We also released OpenZFS 2.1 with a huge new feature of DRAID, which was talked about, I think, for 5+ years running at the OpenZFS Developer Summit. So I think it goes to show that there are, sometimes it takes us a while. Sometimes it takes a lot of different companies, a lot of different contributors to pick up this work. But I'm really inspired by the D-RAID project and people working across, I think at least 3 major companies contributing, picking up that work over the years and finally getting it in for everyone to use. So I think that that's really inspiring, and it gives me hope even when I see projects that are like big projects that are just starting out, and you wonder, is it ever going to be done? Is it ever going to get integrated? And we have some great examples of that actually happening. Also, in the past 3 years, we've been having these monthly OpenZFS leadership meetings. So these are open meetings. Anybody can come and attend, contribute. And I think that this has really helped the project to maintain cohesion throughout the other 11 months of the year when we aren't having this conference. And I invite you all to attend. I'll have details on that later on. So now I'll try to prognosticate a little bit. What does the future hold? What does the next year and a couple of years hold for the project? So there's a lot of work in progress in terms of new features for OpenZFS, new development. A lot of these are in flight, and hopefully they all land. Maybe they all will. Maybe they won't in the next year. It takes a lot of effort for developers to implement these, test them, and upstream them into OpenZFS. So I really appreciate all that work, and all of our developers are they're bringing OpenZFS, they're keeping OpenZFS alive and moving it forward as the industry changes. So I appreciate all the hard work that's being done on that front. There's also a lot of other things that need to happen for a release to happen and for the project to continue. So a lot of this stuff goes on behind the scenes, and we would like to bring it out from behind the curtain a little bit. So all those great features could be implemented, but they need to be integrated into the code base. They need to be reviewed so they can be integrated. They need to have somebody help them along and actually integrate it and make sure that those features are ready and done. That's kind of the role of the maintainers, who are kind of like shepherds for the pull requests. So this is on that role, we've actually made some good progress, I think, in the past year. I don't know how many of folks are aware, but I think for the past, I don't know how many years has the has ZFS on Linux existed, like a lot of years, maybe 9 years. Brian Bellendorf has been basically the one-man show of maintainership of that repo, and he's approved and integrated almost every PR. But as of this year, we've started to involve some more folks. So I'm really pleased that Tony, John, and Mark have been all contributing in terms of helping people get their pull requests integrated, making sure that they get the reviews that they need, making sure that the PRs that we do integrate are up to our high quality standards. A lot of the other roles in here you might notice are filled by just a handful of people from an even smaller handful of companies. So what I'd like to ask from the participants today is, how can you help out? We're going to make apprenticeships available. So the idea is, if you would like to help with the release process, then Brian or whoever is in charge of the releases now will take you under their wing and show you through the next release. And then for the following release, maybe you could be the next release lead. You could help us determine when the next OpenZFS release is, what's the content, how do we keep the quality bar high. That's a role that we would love to have help with. There's also other roles associated with like this conference itself that we would love to have folks help with. And there's also smaller, roles like taking notes at our monthly meetings, and as well as things like triaging issues that come in that are filed on GitHub, and then maybe providing a monthly report at our leadership meeting every month. So a lot of these are roles that don't require expertise in like ZFS kernel programming. Some of these things just require kind of passing familiarity with the project, and other things, we need experts, people who are experts in different areas that are not programming. Like emceeing this conference could be a role that you could contribute to, or serving on the program committee to help us find and choose talks for this conference. So we're gonna have a special discussion today led by Brian Bellendorf at noon Pacific time. That'll be during the lunch break. If you would like to learn more about the opportunities here, or find out what's really involved in these and volunteer, then we'd love to chat with you then. And another way to kind of get involved is to come attend our OpenZFS leadership meetings, which are held monthly. The next one is going to be about 4 weeks from now, the 7th of December, same time as this, 9 a.m. Pacific. And we send out tweets and emails about that on the mailing list, usually the day before. All right. So the past, the future, but here we are today. What's happening today? So we have a bunch of great talks, and we also have a bunch of breaks. So during the breaks, we're going to use the Zoom breakout rooms feature to allow folks to just casual chit chat with other people from the community. We'll have folks who are the speakers at the conference, as well as some notable community members who have volunteered to lead those discussions. So during the breaks, you'll see something pop up on your screen that's like, which breakout room would you like to join? And you'll see the names of the people who are leading the breakout rooms. And the folks who are not speakers, I've listed here with some of their interests. I'll try to bring up the slide when we go to the breaks as well. All right, so today we're having the presentations, and tomorrow we have a hackathon. The theme of the hackathon is quality. How can we improve the quality of the project and the quality of the OpenZFS codebase? So you might wonder, like, how could I improve quality in just one day? And this is a daytime business hours, at least business hours Pacific time hackathon, not a all night Mountain Dew fueled hackathon. Although your version of the hackathon may be fueled by Mountain Dew or other beverages. 8 hours is not a long time, but we do have a bunch of ideas about what could be done within that time, around identifying bugs that may have slipped through the cracks, reviewing pull requests. There's a bunch of older pull requests that probably need just a little bit of work for someone to pick them up and get them integrated. So we'll have a special hackathon planning session during lunch today after the volunteer opportunities one at 12:20 Pacific time. That'll be led by George Wilson. So you can see the schedule there for tomorrow. And we do have prizes. The prizes are bug or insect themed. So you'll have to come tomorrow and find out what those are. Okay, lastly, or close to lastly, this is a professional conference. We expect everyone to behave professionally, and a big part of that is being kind and being welcoming to people who may be new to the community. We'll have lots of opportunities for folks to interact and put that into action. And just remember that people come from different backgrounds, and they have different experiences coming to OpenZFS, coming to the programming world. If you have any issues, you can let us know. If you have any technical problems, get in touch with George, and you can find us all on email or on the OpenZFS Slack. You should have received a link to the how to join the OpenZFS Slack in your email if you're registered. All right, so if you have questions right now or at the end of the talks, We're going to use, you can ask your questions by typing it into chat. You can ask your questions by asking them audio visually. I will allow you to, if you would like to ask a question now, you can start your video or you can raise your hand and I will look for you and have you unmute yourself. Hi, Jorgen. Hi, Paul. Let's see if you would like to unmute. Questions? Alan had a more of a statement than a question, but he noted that many of the projects that have been integrated to OpenZFS in the past year were actually started at hackathons, which is pretty cool. This year, I mean, we would love to see projects started at this hackathon as well. I'd also love to see changes to the community or changes to our processes that might start at this hackathon. So, for example, we talked about triaging bugs, finding bugs that have slipped through the cracks. That would be a great project to do during the hackathon. But even better or more sustainable, longer term, impactful activity might be to figure out what is the process to make sure that we do triage those bugs on an ongoing basis, not just on the one day of the hackathon. So maybe finding some way to measure and show metrics around incoming bugs that have received attention and been answered or addressed or categorized or not categorized might be a great addition to the project in terms of long-term quality. All right, any other questions or comments before we go to the first talk? First technical talk, I should say. Okay, I have a question on text. Right, so Arshad asks, being new to ZFS, in this hackathon, could I do something like fix a simple spelling mistake? I would say absolutely. Yeah, I mean, fixing spelling mistakes, typos in documentation, in the code, in comments of the code, those would all be great things, great additions to the project. And one of the great things about this hackathon is that it's live. It's live. It's happening between people that are new to the project and people that have a lot of experience with the project. So you can what's involved with changing a spelling mistake might be conceptually very easy, but the process of actually making that happen with Git, with pull requests, may not be obvious to you, and we have folks on hand that can help with those kinds of things. So hopefully, we can teach you how to make those changes today, and then you can go on to make further spelling mistake improvements and other improvements in the future. Yes, so a couple of people noted there's a spreadsheet which is in the chat, linked in the chat, that has some ideas in there, both of things in the quality theme as well as new features and improvements. If you'd like to get a jump on that brainstorming, then take a look at that. All right. Well, with that, I will introduce our next speaker, Brian Atkinson, who's going to be talking to us about direct I/O on OpenZFS. Brian, can you share your? There we go. I'll ask you to unmute. Great.
I probably need to. Can everybody see the slides? Can you
Yeah,
hear me? I guess that's
I can hear you.
important.
Would you like to share your video?
Yeah, hold on. Enable start video. I think you have to allow that, Matt. When I
Okay,
click on start video, it says unable to start
here
video.
we go. Try now.
Yeah, keeps going to
Is it
unable
still
to
not letting
start.
you?
Yeah.
Oh, there we go. I think I did it the wrong way. All right, try it again.
Right. Mm.
No? It'll ask you to start your video. There we go.
Oh, there we go.
Oh yeah, I remember. This is a weird permission issue that where certain people can be applied different permissions than everybody else, but it doesn't tell me that. So, all right. Well, welcome, Brian, and I'd love to hear what you have to share with us about Direct.io.
Cool. Yeah, so I'm Brian Atkinson. I'm from the HPC DES Storage Design Group at Los Alamos National Lab. And today I'm going to be presenting on the addition of Direct.io to ZFS. Hello. Why can I not? There we go. All right. So I just wanted to start out with quickly going through what I'm going to go through today. I'm going to start out with quickly explaining what Direct.io is. Then I'm going to give a motivation for why we actually want to add this to ZFS. Then I'm going to get into the kind of the dirty details about how we actually implemented this. Then I want to share the performance results that we have with Direct.io and ZFS. And finally, I just want to conclude by giving the current status of the work as it stands today. And so I really just want to start out with what exactly is Direct.io, because oftentimes people don't know exactly what Direct.io is. And so a user will pass the ODirect flag to an open call. And when they do this, they're saying, hey, I want to use ODirect. And from the Linux man page, it says, try to minimize the cache effects of IO to and from the file. And the IO is done directly from to and from user space buffers. And so really what this means in Linux is most file systems will just directly map in user pages into the file system, and then they'll read directly in and out, read and write directly in and out of those pages. And by doing this, they're completely bypassing the page cache, so no copies are ever made of the actual buffers that the user is using. But outside of this, there's really loose rules and semantics around Direct.io. And if you look at different file systems, they'll have their own alignment restrictions, or even things like, do we want to be coherent with buffered writes and reads and all that kind of stuff with Direct.io? So really, it's very loose semantics outside of just that main idea of mapping in user pages and directly reading in and out of them. And so currently, ZFS actually accepts the ODirect flag, but what it actually does is it just silently ignores it right now. And really, if we wanted to have ODirect in ZFS, at a minimum, we should be bypassing the ARC completely and not making any copies whatsoever. And so this really leads to the question of why in the heck will we ever want to bypass the ARC? And have we completely lost our minds? And I can honestly say, while working on this code, I have felt like I was going crazy from time to time because the ARC is such an integral part of how ZFS works. And I wanted to start out by saying that in no way is this presentation saying never use the ARC. The ARC is super important to ZFS, and you can get great performance out of it. However, there are certain times where it is beneficial to bypass the ARC. One example is databases. Oftentimes they have their own caching schemes. And so if you have a database sitting on top of ZFS, if it's writing things down into ZFS, the ARC's going to cache that data. And that may not be what the database actually wants, and it may not actually benefit the database in some cases. But I also want to talk about just our workloads at LANL specific to HPC. And we have these long run parallel simulations. And these things can run for sometimes on the scale of weeks to months and highly parallel. And so often what these simulations will do is periodically throughout time is they're going to checkpoint their data. And this is just a write once situation in the hopes that we never have to read that data back. It's just merely to save the state of the simulation itself. And we call this checkpointing. And so if that's going into the ARC, there's really no benefit for us there because our intention is to never have to read that data. But unfortunately, we all know hardware failures happen. And in that case, we actually do eventually have to read that data back out of ZFS to restart the simulation, just get it to its old state. But this is a read once situation. We're really just reinitializing the program to get it kicked back off after a hardware failure. And again, we don't really want that data in the ARC. This is just a read once situation. It's not going to benefit us to keep that data hanging around in the ARC. And the last one that I wanted to highlight here is using low latency, high bandwidth NVMe devices as VDEVs. And later on in my presentation, I'll show that with DirectIO and ZFS, we can get 1.5 to 3x speed up with these devices. But I highlighted this case because this is actually the case that got this work kicked off, really. And this is because Lano was looking at its next generation of parallel file systems with Lustre, ZFS, and these NVMe devices underlying ZFS. And we started looking at actually NVMEs inside of these Z pools, we got really surprising results. And so the first thing I want to highlight on this graph is this top line here, this dashed line. And what this is the maximum amount of sequential read bandwidth we could get out of 12 Samsung PM1725 NVMEs. It's right around 42, 43 gigs a second. However, when we actually put these NVMEs inside of Z pool and we start use different configurations, either striping, RAID Z1 or RAID Z2, we found we were completely bottlenecked. And the bottleneck got worse as we continue to decrease IO parallelism, which is the x-axis here. So each one of these data points along the x-axis is sequential readers of just their own individual files out of the Z pool. And so in the best case scenario, which is the low IO thread counts, we're leaving about 48 to 57% of all the available NVMe read bandwidth on the table. And that's because the ARC was prefetching, it was doing a decent job, but we still were missing a ton of available bandwidth. And this got really worse as we continue to decrease that IO parallelism, because at that point we're thrashing the ARC. And so every read was having to be issued down to the VDEVs, the VDEVs themselves and the NVMEs. And in that case, we were leaving 70% of available bandwidth on the table that these NVMEs would allow for. And we also did this comparison with just sequential writes in these NVMe-based Z pools. And again, I want to point out these dashed lines at the top here. The main difference here is that the top line is for all 12 NVMEs, and this is for striping because we actually have all 12 NVMe bandwidth to work with in that case. However, when you go down to RAID Z1, you lose a disk worth of bandwidth for the writes, and then in the RAID Z2 case, again, you lose an additional disk worth of bandwidth for the writes. And we saw something very similar, just like we saw with the reads, is we increased IO parallelism, we just completely flatline. And in the worst case, we were leaving 47% of available NVMe bandwidth on the table. In the best case, 34. But in either of these cases, I mean, it's still a lot of available bandwidth that we wanted to capture. And so this actually led to a meeting back in August of 2019 between Cray, Livermore, Oak Ridge, and Lano, because funny enough, we were all investigating the same issue. And we had all tried different parameters. We had shared that with each other. We tried just doing small patches of code, but we can never get past these bottlenecks in ZFS with these NVMe Z pools. And so over the course of the week, we decided, all right, let's actually investigate this and figure out what are we missing here? Like, what's our bottleneck? And so we used a tool called flame graphs. And the way you read a flame graph is at the very bottom of the flame graphs, that's the beginning of the call stack. And as you go further up in the flame graphs, you're getting deeper and deeper in the call stack. And what you're trying to find with these flame graphs are these plateaus. And the longer a plateau is, the more execution time is being spent in that call. And so we found two places in particular where with the sequential reads for buffered ZFS IO, we were getting stuck in. The best case is the one over here on the right. That's where, okay, the data was in the ARC, we just copied out of the ARC and into the user buffer. But in the worst cases, which we saw, like we continue to decrease that IO parallelism, we were actually getting hit by 2 memory copies. And that's the one on the left here. That one is actually copying that data into the ARC. And then eventually we're going to copy the data out of the ARC and into the user buffer. And again, we did the same analysis, but this time with writes. And again, we found all of our execution time was being stuck in this memory copy. But in this case, it was just simply taking the user's buffer and copying it into the kernel space and into the ARC. And so when we looked at this, we're like, all right, there's actually pretty easy solution of this. We just need to actually implement direct IO in ZFS, and we can completely avoid these memory copies. And so I just wanted to first, before I get into the dirty details of how we got all this working, just go over the big picture. What do we mean when we say we added direct IO to ZFS? And I'm just going to start with the reads first. And I've got a really simplistic diagram over here on the right of the internals of ZFS. So on the left-hand side, we have the normal buffered path that ZFS does with reads. So when a read system call comes in, it goes through the ZPL layer, hits the DMU, and the first thing it's going to do is go, hey, is this data in the ARC? If so, go ahead and copy it out into the user buffer and return up to the read call in that case. However, if that data is not resident in the ARC, it then has to issue that request through the ZIO pipeline down to the underlying VDEVs, copy it into the ARC, and then eventually copy it into the user space. And so with direct IO, the big picture here is what we're trying to say is when we get that read system call come in through the ZPL layer, we'll enter the DMU, and we're just going to directly issue that into the ZIO pipeline and read that data off of the VDEVs. And we do this by mapping the user pages directly into an ABD. And I just want to quickly state this here, and then I'll go into way more detail about what I mean by this. There is, with direct IO reads, we can copy out of the ARC. We allow that because we have this thing called ARC coherency between buffered and direct IO. But again, I'm going to go in that in much more detail, but I did want to just quickly mention that here. So the big idea with the write side is that the typical write path for ZFS for buffered IO is a user buffer will come in and that's immediately memory copied into the ARC. Now, as soon as that copy is done, we return out to the write system call and we're done. And this buffer here is then assigned to a transaction group. And eventually after some time period or enough dirty data is accumulated into the ARC, this transaction group will transition to its sync phase. Once it's in that sync phase, it's going to go through the ZIO pipeline, any transformations that will take place, and then it'll issue that right out to the underlying VDEVs. With direct IO, what we're saying is like, take that user buffer, again, directly map it into an AVD, and then immediately send that through the ZIO pipeline. So we're still going to do all those transformations just as we do before. And then we're going to issue that right immediately down to the underlying VDEVs. And it's not until after we've put that data on disk that we return back to that write system call. And so at that point, we can guarantee to the user, okay, your data has landed on the underlying VDEVs. So now to get into the actual details of how we actually got all this working in ZFS, I just want to stick to general details, and then I'm going to actually go into much greater detail with the right side of direct IO. And just to start up front, I want everybody to understand ODirect does not imply OSync, and this is common with all file systems. And what we saying when we say this, what we mean is, even though we're guaranteeing that data has landed on the VDEVs with ODirect, that says nothing about the indirect block pointers and the metadata of that write. If you want that to go out with that ODirect data, you have to either tell the zpool sync always or pass the OSync flag. The other big thing is we have alignment restrictions with ODirect. For now, we've chosen the page size. It's common amongst a lot of file systems, but some can even go as low as the LBA. But for now, we stuck with page size. And if a user does request direct IO through the ODirect flag and it's not page size line, in that case, we're going to return EM val. The other thing we do is if a user has memory mapped any files, we're just going to silently ignore any direct IO request. And I know this may make people cringe because it's like, wait, you're silently ignoring this stuff. And that's why we actually added some accounting, and we have it both for Linux and free BSD. So users can actually verify how exactly did my request get issued out in ZFS. There's also, of course, ArcStat, and you can see through ArcStat how your data was delivered. But these extra accounting that we've added, they're much more fine grained if anybody wants to look at that while they're issuing their direct IO. The other big thing I wanted to mention is that all direct IO requests, they're issued as a sync priority down in the VDEV queues. So the ZFS VDEV sync max min, those are the parameters that apply to any direct IO reads and writes. And again, as I previously stated in that read, we keep ARC coherency with ODirect. And so I really want to dive into exactly what do we mean by ARC coherency. And so again, remember with the direct IO, right, we're just immediately coming in, and this is all going to be done in open context. We're going to come in, issue it through the ZIO pipeline. And once that data buffer is landed on the VDEVs, we actually have a little bit more logic to apply here, because there may be a case where there's an associated buffer, ARC buffer, with this data we just wrote out. And we want to invalidate that ARC buffer, because after we've set that data on the VDEV, we want all future reads to go down to the VDEV, because that's the most recent data that was issued through the direct IO. So in the case that for whatever reason you're just mixing buffered and direct IO operations, we do have that little bit of logic. So once the data is on the VDEV, in the best case scenario, we have no data or dirty data in the ARC. And so at that point, it's like, great, let's just update the block pointer. That means every future read's going to have to issue down to the VDEVs below. However, worst case, again, users sometimes they'll mix and match, buffer and direct IO. Although I don't suggest it, they will occasionally do this. So if we do have these dirty records, the first thing we have to check is, okay, are we actually syncing out this dirty record here that's associated with this data buffer? And if that's the case, we have to wait, because with DirectIO, we want to promise the same consistency semantics that ZFS normally promises. So we want that transaction, previous transaction, to go out and be written out to disk. And if there is no dirty record syncing, what we'll do is remove all the dirty records, remove the data from the ARC, and then we update the block pointer. And so we do have one other alignment restriction, specifically with direct IO writes, and that's for each direct IO write, it also has to be record size aligned. And there's a reason we do this. It's because we want to avoid a read, write, and modify cycle. And to explain what I mean by this, I wanted to show two back direct IO writes, one after the other, and explain what that means by the read, write, modify. So if we came in, we did the direct IO path, we went into the ZIO pipeline, we would calculate a checksum based on that user data, and we place that in the block pointer. And then that data will be on the VDEV. Well, let's just say a user wants to just modify a small portion of that data buffer, this red block here, and they want to use direct IO. What that would force us to do is, first, we'd have to go, wait, you have to go down to the VDEV, read that data off, bring it back up in the DMU layer, we'll modify it again, issue it back out to the direct IO or through the ZIO pipeline, because we have to recalculate that checksum and update it inside the block pointer, and then issue that back out to the VDEV. And honestly, we did implement it at first to do this. We allowed for the sub record size updates with ODirect. We found the performance penalties are so high between these read, write, and modifies that it just did not make sense to allow ODirect to do this. And so in the case that a user does submit an ODirect request and it's not record size aligned, we're just going to silently ignore it and go, hey, you know what? Go through the ARC. You're going to get better performance there anyways. And so we just silently ignore it in that case. The other thing I did want to mention is that for each block or first block that's written to a file, ZFS actually allows that first block to slowly grow up to a record size. And this is really entwined with how the ARC works. And because we already have this record size alignment restriction, we decided, you know what? While that block size is growing, just go through the ARC like you normally would. We're not going to issue that first request to the file using direct IO. But I just wanted to mention that so nobody's caught off guard when they see that. And the last thing I wanted to touch on was this idea of stable pages. And what we're saying here is we actually have to write protect the user's pages, because it's important to remember we've directly mapped in the user's pages with ODirect. And to explain why this is important, again, when we go into the ZIO pipeline, we're calculating a checksum and writing that into the data's block pointer. However, for some reason, the user just maliciously, let's be honest, as users with parallel, code, sometimes we just do weird things. If for some reason, after we've calculated this checksum, we set it in the block pointer, if we were to modify the contents of that buffer and write that out, I mean, everything's fine as long as it's just sitting there on the VDEV. But the issue comes in, well, when we go to read that data out, either because we've issued a read on it, or there's a resilver happening, or anything of that manner, what we're going to get is a checksum failure. And there's no way for us to actually fix this because our checksum was calculated based upon the original contents of the user's pages. So we have to protect the user's pages before we actually issue out the direct IO to the ZIO pipeline. And before jumping into the performance results that we got with direct IO, I did want to do one last note on direct IO and ZFS. We did add a new dataset property. It's just called direct. And the default is standard, and that follows all the semantics that I've outlined so far. But we also added always. And what this really allows the user to do is say, okay, I don't want to modify all my applications to use the O-direct flag. Let me just simply try it out. And always is kind of a best effort that we do here. So in the case that it's not page size aligned like we always require with O-direct, we're going to go, no worries, just fall back to the buffered path in that case. But this just allows users, hey, let me try out O-direct. Let me just see if it does me any benefits with my workloads. We also added in that same vein, direct disable, because if this patch gets merged, people that were passing the O-direct flag would be like, what the heck just happened? Because the performance may be all over the place all of a sudden. They're not getting what they want. And so by doing disable, it just means, hey, just ignore the O-direct flag, just how ZFS does it today. So it's basically fall back to the old version and just forget that O-direct flag was even being passed. And so now I wanted to actually show how we get our performance results with all these crazy additions of O-direct to ZFS. And so I'm going to start out looking at the sequential read results from the NVMe Z pools. And on this graph, I have the previous results that we had. Those are the light color lines here. And the O-direct results are the dark color lines. And again, I want to point out this dashed line at the very top. That was the maximum amount of NVMe bandwidth we could get with sequential reads. And so we actually see is that for each of the different VDEV configurations, striping, RAID Zs, we get pretty close to capturing all of that available NVMe bandwidth. And at the higher IO threads where we are thrashing the ARC, we actually get about a 3x speed up for the reads there. And in general, for all cases, the O-direct reads scale, pretty well, and they stay consistent as we continue to decrease that IO parallelism. And so with the sequential write results for these NVMe Z pools, it's again important to remember that based on the certain VDEV, you have a certain maximum you can achieve. So I just wanted to grab the one case where all three of the different VDEV configurations were at their maximum bandwidth. And that was at 512 sequential IO thread writers. And so for each of the different VDEV cases, I have a green bar that's showing this is the amount of available NVMe bandwidth we were able to capture through the buffered path. And then the blue bar is, okay, this is the maximum amount of the available NVMe bandwidth we were able to capture with O-direct. And so if we just look at the RAID Z1 case here in the center, previously we were only able to get 53% of all the available NVMe bandwidth. But with O-direct, we were actually able to raise it up to 93%. And in the RAID Z2 case, we were able to lift that number up to 93. And in striping, we're actually almost able to get 100% of the available NVMe bandwidth. But for all three of the different VDEV configurations, we got over 1.5x speed up. And I also just wanted to quickly state, unfortunately, I don't have enough time in this presentation to go over all the scaling results with O-direct sequential writes, but if anybody's interested in this data, I do have addendum slides. All that data is available. And I also do have O-direct write scaling results with D-RAID configurations. So anybody can look at that if they're interested. And there was one last performance case I actually wanted to go over here, and that was O-direct with disk. And the main difference between this graph and the previous graphs that I've shown is along the x-axis here, this is actually the number of sequential read IO threads per Z pool. And that's because we took a 90 disk JBOD and we broke it up into 5 Z pools. And again, we did the different VDEV configurations, striping, RAID Z1, RAID Z2. But really what I just want to highlight in here are the RAID Z cases, and that's the green and blue lines. And the darker color lines are the ODirect results. The light color lines are the buffered cases. And so what I really want to highlight here is that for all the ODirect cases, we're actually performing worse than buffered. And this goes back to what I started out the presentation with. Like, we're not arguing to never use the ARC. In fact, with ODirect, if you're looking at just from a performance perspective, there's a few things to take into consideration. Basically, you want to think about, what is my IO workload? Will I benefit from this? Even with that IO workload, what's my VDEV configuration? And along those lines, what is the underlying hardware? Because we can see here that even in the low thread IO thread counts, our prefetching is doing a pretty good job with this JBOD. And even though it does, flatline a little bit and come down, it's still really outperforming the ODirect results. So just as a caveat, ODirect, if you're just strictly thinking about performance, is important to really take into consideration all these different factors. So I just wanted to give a current status of this work. We do have an open pull request. People go out there, grab it, try it out, discover bugs possibly, give it a whirl. We definitely would like some feedback on the pull request for anybody who does try it. And we are aware of some bugs in the code. There's some corner cases we're still working through. In particular with Linux, the stable page stuff, the kernel doesn't really document stable pages too well. So we've been struggling to get that to work for all cases on the Linux side, but we're hopeful that we're getting close to getting that done. And in the FreeBSD, for some strange reason, with ODirect reads, I've been getting e-faults occasionally when mapping in the user pages. And really, anybody in the FreeBSD community, I'm more of a Linux person. And I'm trying to learn FreeBSD as much as I can, but anybody that could help out on the side, that would be greatly appreciated. In particular, getting us performance testing from FreeBSD would be great too. All my performance testing has been done on the Linux side. And the one last thing that we have talked about is actually getting DirectIO to work with zvols. Brian Bellendorf and I worked on this for a little while, but we kind of tabled it for now. But we would like to actually integrate DirectIO with zvols. We're just not sure if it'll go into this pull request, or maybe once this pull request is merged, let's go back and then get the zvol parts hooked in. And before I finish up, I want to give a special thanks to everybody that has contributed to this, because without them, none of this work would have been in the state it's in. Mark Mabey, who initially did the DirectIO implementation. Matt Ahrens, he really assisted in getting the semantics nailed down for how we wanted DirectIO work in ZFS. Matt Macy did all the FreeBSD ports for DirectIO, and I really appreciate his help there. And Brian Bellendorf has been great in helping me try to get this work across the finish line. A lot of the stuff with the ARC coherency and just general Linux side implementation details, including the stable page issue that we have right now. So with that, I'll take any questions anybody might have.
Cool. Sorry that I ran a little long with my presentation, but we'll give you enough time to do some Q&A here. If you would like to ask a question, you can start your video, you can raise your hand, or you can type it into the chat. So there's a couple in the chat. I see Mark has his hand raised. I'm gonna go ahead and you can unmute and ask your question if you'd like, Mark.
All right. Am I unmuted?
We can hear you.
Cool. So Brian, this is fantastic to see this work coming along. It's been a while, I know, since I was involved from the beginning.
2018 when we started.
So in your analysis, I mean, you already highlighted that, the DirectIO work is really a performance effort. And so, you have to be careful when you use it, because it may not pan out in all configurations.
Yeah.
And you demonstrated that obviously with your example running on disk rather than NVMe. Have you also done any analysis on small block versus large block workloads? Because I would assume that would be another category where you might not see the performance you might expect or naively think about.
No, I haven't done a full analysis there yet, but that is something we're interested in because actually Matt Aarons and I were talking about those JBOD results, and really I should have pressed up the record size, and I didn't say this. All the results that I shared were 1 meg record sizes and 1 meg request sizes. But if I actually pushed that, up to maybe say like 8 meg record or
Right.
60 meg, maybe there would have been a performance win. And really just that's what I was trying to highlight there is given a certain test case, you may not get what you
Yeah,
expect.
exactly. I think you have to be careful when we release
Mhm.
this feature to, in the documentation to be very clear about that obviously your performance it may vary depending on your work case, which
Exactly. And
we
that's why we
highlighted.
added that disable because again, people would be like, whoa, what the heck?
Yeah, exactly. Well, thanks.
Yeah. Oh yeah.
Cool, thanks. There were a few questions written here. You want me to read them out to you, Brian?
Oh yeah, because let's see, I was trying to see if I could see the
That's right.
chat, but
There should be some way. You can also stop your screen share
oh,
if you
here we
want.
go.
It might
Here we
make
go.
it easier to find it.
Yeah, I was trying to figure out how to stop that. Oh,
The
here we go.
first
Stop
question
share.
was from Joshua. He asked what tool you used for generating the load and then also for measuring the performance and generating the graphs.
So yeah, for the IO workload, we used the XDD tool. And the reason we use XDD is because with a lot of our workloads at Lano, we have an end-to-one situation, and that's extremely hard to mimic with FIO. For the raw test cases, we did use FIO to measure those, and I actually have verified the XDD results with FIO. That's why I also only presented multiple parallel readers and writers because we didn't want to just show those end-to-one cases because that's really specific to kind of HPC. But that's how I measured all the performance stuff. With the graphs, I used GNU plot to generate those.
Cool. The next question was from Saji. Oh, Joshua says thanks. The next question was from Saji Nair. He notes that, yeah, so ODirect doesn't give you OSync, which means that if you crash, you could lose the ODirect writes if they weren't synced.
Yeah.
Question/statement.
That's exactly right.
Yeah, and you can use the OSync flag and the ODirect flag if those are the semantics that you need.
Yeah, exactly.
Alan Jude asks, if you open a file with ODirect, do indirect blocks still get cached in the arc?
Yes. Yeah. Yeah, if you want to control the caching of any of that stuff, you'd have to say like what is it, metadata. You can turn that off, I believe, with the arc caching.
Yeah,
if
you
you
can use
want.
the normal properties to do
Yeah,
that.
but no, all that's going to be in the arc.
Cool.
With ODirect, we're strictly talking about the data's user buffer itself. We're not talking about any of those indirects, and that's again goes back to that OSync idea.
Cool. James Simmons asks, what's the timeline to getting this merged?
Hopefully
Perennially
soon.
great question.
Yeah, hopefully soon. I mean, the stable page stuff has definitely been frustrating on the Linux side. Every time we think we got it, it's like, oh, well, we just tested a case and now we're stuck waiting around, and just deadlocking. So really, I think that's the last remaining hurdle in the Linux side. Again, there's a few little bugs. We actually do have a random arc leak that can happen, which has been super hard to trace down, but it could be like 1 out of 100 runs. All of a sudden we leak an arc header. But that's only when you're mixing the direct IO and buffered stuff. The FreeBSD, again, that needs more love and nurturing care than I have given it. Unfortunately, I'm not an expert on FreeBSD. And Matt Macy was great with porting that over. But anybody that wants to really help out on that side, it'd be great because we definitely need to get all that done before we even think about getting it merged.
Cool. We have a few more questions, and I think we have time for them, so I'll keep going. Richard Lager asks, he's asking about when the page size. His question is about alignment. So if the page size is less than the record size, then what are the alignment requirements? Doesn't it still need to do a read modify write? And does that fall back to buffered access, or is it still going to be doing direct IO with if your record size is greater than the page size and you're doing just page size aligned?
So the
writes.
page size is less than record size.
Yeah. So like if the default record size is 128K and you do a page size aligned right, what happens there?
Huh. Well, maybe this will answer. So we actually do address the case where, say, if you have a record size of 1K, as long as you've issued the request as 4K, we will send that direct. We allow
so
that
he's
to
asking
happen.
about the opposite.
Yeah, and that's what I was trying to understand. So
I think that I thought that at one point we decided that if the request is not record size aligned, then we would not do it as direct IO.
yeah, we always bail back to the buffer in that case.
Very
Yeah.
cool. Rich asked a question that was answered on the chat about like, can you go back to the old behavior of ignoring the ODirect and just always have buffered? And the answer was yes, there's going to be a property to do that. Will Strickland says, great performance results. He has a question about the graphs. Am I reading correctly that direct IO will likely perform better with fast storage media or a fast backend like NVMe, but direct IO might be worse if you have a backend that's slower like HDDs?
I think that's too broad of a statement, to be honest, because again, Matt Aaron's, when we were going over the results, it's like, well, we should have gone with a bigger record size there. And so again, this is where I'd love for the community, like, get the pull request down, mess with it, give some feedback. We're obviously doing more in-house to get more results and interpret them. But yeah, I think it's too broad of a statement to say like, no, this is only going to be great for NVMe. I think there are cases where it could be beneficial. It just depends on the ILO workloads too. I mean, that's all I was trying to stress there.
Yeah, I agree. It seems like primarily you can think of this as like ODirect reduces CPU usage and reduces memory usage. And there's some latency trade-offs for making that happen in some cases. But if your workload is not super latency sensitive, then having more CPU is good regardless of the backend performance. Cool. Yuri Volchkov asks, how about the use case of virtual machine storage using a zvol? Would that benefit from direct IO, assuming that you carefully select the record size?
It could, and that's where the Bellendorf and I were talking recently. They've had a case come up at Livermore where they could have benefits with zvols and ODirect. So we definitely want to get that work in. It's just, again, I don't know if it'll be in this initial pull request or as a separate pull request when this gets merged. Without fully testing out, it's hard to say. We first would have to get everything hooked in. And actually, we thought we had it working at one point, but we were surprised. It wasn't as easy. Even though the hooks are there, it's like, okay, yeah, just put this in the zvol code. We ran into some weird issues, but we just did kind of bench that for now till we got everything working on the regular paths. But I would say it would take actually testing it out to give any clear statements on that.
All right. I just took time for maybe these two last questions that are here. A question related from YouTube. The XR3K is asking if the speedups would apply to special VDEVs as well.
Special
like
VDEVs.
Special VDEVs like those that are used for small blocks and RAIDs, like metadata, like dedupe metadata. I think normally those would not be storing like data blocks, so it might not.
Yeah, exactly. Yeah.
Okay.
That's what I would think. Yeah, because I mean, yeah, anything the indirect block pointers, we're not sending that through ODirect.
Ted Cabine is asking about, is this largely intended for workloads where the data being accessed is much larger than the memory available for the ARC? So in other words, it can't be cached, and the blocks being accessed are not accessed repeatedly. So yeah, he's basically asking like, is this for uncached workloads?
Yeah, it's kind of what our direct's implying. I mean, but and again, the reason we even got this work kicked off, I mean, between Cray, Oak Ridge, Livermore, and Lanall, I mean, sometimes our IO workloads are not common. We're sequentially streaming out large amounts of data, and that's where we saw the benefits of this. So for us, it's like, well, if we're not really wanting to cache that data, could we just avoid doing it? But in cases where, say, you are doing a lot of caching or anything like that, having like an L2 arc could possibly benefit you more than ODirect. I mean, if you really, that's your IO workload, that's what I'm saying. ODirect may not be the solution there, even depending on the underlying medium storage. It's just really the IO workload and what you're trying to do.
Right. I'm gonna make an exception because there's another question came in that I think is kind of interesting. From YouTube, Thomas Monroe asks, what happens if I write two non-overlapping record-aligned regions, so they're good writes, using ODsync and ODirect at the same time? I know if it's ODirect, then those will both be able to proceed in parallel concurrently.
Mhm.
I'm not sure what ODsync means in this situation.
Yeah, that would be fine.
Good.
I don't see whether, and I didn't stress this in the presentation, but ZFS has the range locks, out there. So that prevents a lot of bad things happening with ODirect writes. And because we have the record size alignment thing, it's like, all right, great. We can have multiple direct IO writes going to the same file. And in our end-to-one cases that we've tested at Linol, it works completely fine. So you're never going to have two direct IO writes overlap into the same record. The range locks are going to lock it out. It can't happen. They're going to proceed in an order that it's controlled by ZFS.
Cool. All right. Well, thanks a lot, Brian, for your talk.
Yeah, thank you.
So next up, we have a break. The break is going to be a little shorter than I had planned because I ran long. So I apologize for that, but we'll do a 10-minute break. So you're going to see something pop up on your screen. Let me go to my other screen. About breakout rooms, and you can choose which breakout room you like to go to. Let me share. You can see. All right, so this has some of the folks. So the breakout rooms are going to be Brian. If you have more questions about DirectIO or just want to chat with Brian, he'll have a breakout room. I'll have a breakout room. If you have questions about the state of the project or anything else, I'd be happy to chat with you. Alan Jude and Joshua Klula will each be leading breakout rooms. So feel free to join one of those. We'll have a 10-minute break, and then we'll come back for a talk about ZFS and object storage. So you should see something pop up. Let me see if I see it on my other screen. Oh, it's sharing. All right, I think that some people are going in. Also, one other note. So we're recording and live streaming the main room here, but the breakout rooms are not recorded or anything. So if you have any discussions that you want to remember for later, please remember to take notes because those aren't being recorded. Hey, folks who are still in the main room, I wanted to let you know if you were trying to join a breakout room, you may not have been able to figure out how. So I will give you the secret. So you go to breakout rooms and you probably see like a list of the rooms, and then you see like a number, that's the number of people in the room. So like I can see, Brian Atkinson, Direct IO, and next to that it says 10. If you hover over the 10, which is now 11, and then it'll turn into a button that says join. So this is a little non-intuitive because you don't see any button that says join until you hover over the number. But that is how you can join a room. All right, I see a few people were hopefully able to figure that out. I will go jump back to the room that the discussion that I'm supposed to be leading, and we'll see you all in just a couple minutes. Awesome. I think that we got everyone back here. So next up, we're going to have a talk about ZFS and Object Store. I'm going to ask for, thank you, everybody who was not giving the talk, to stop sharing your video. Let me make sure that I have the settings correct. Okay. All right. And I'll ask the other folks to share. All right, great. So up next from Delphix, we have a talk about ZFS and object storage by George Wilson, Paul Dagnelli, Manoj Joseph, and myself. So thanks, and take it away, George.
All right. Cool. Okay, yeah, as Matt said, we wanted to kind of talk about ZFS on Object Store. But before we do that, I kind of wanted to take us back in time, and I even wore my oldest OpenZFS t-shirt that I could find back to 2005. So some of you may recall some things that went on with 2005, like Hurricane Katrina, the cancellation of the NHL season, the first flight of the Airbus A380. But there were actually other things that were more relevant to us, and that was ZFS was introduced into the open source community by the open Solaris project. And one of the things that, if anybody ever saw this presentation, it talked about really just kind of blowing away 20 years of obsolete assumptions. And so as part of this, I was like, hey, it's the 16th birthday of ZFS. Let's, we want to celebrate that. Let's go get some reaction from some ZFS developers and kind of see if they knew what was so exciting and what they felt about that. Oh, and sure enough, we actually had some that were really excited about the project back then. Today, things have changed quite a bit, but I wanted to talk a little bit about some things that we looked at when ZFS first came out and kind of what they really meant to file systems. So in particular, it addressed this brutal to manage problem that existed and still exists today with different file systems. But, for those that were doing system administration in those days before ZFS, you had to deal with the partitioning of volumes and kind of labeling them and modifying a bunch of Etsy files and dealing with inode limits and how big do I need to make things. And it was really just kind of problematic. And so it was a wonderful breakthrough when ZFS came out and said, hey, we're going to go tackle this problem and tackle it and solve it. In addition to that, it was kind of breaking some of the rules that people knew back then. We realized that the way we would make file systems bigger, we would actually create this shim layer with volumes, and we introduced this abstraction of a virtual disk. And so now we would have a volume manager that was involved, and it was another headache that we had to deal with. And of course, it had its share of problems. We would leave storage stranded. So if I had storage in this particular file system that I needed somewhere else, well, I couldn't move it very easily. It was just a pain. And then of course I had to still deal with partitioning and growing and shrinking, all of that stuff being done by hand. And so when ZFS came out and introduced the pooled storage model, it was great. It was just a breakthrough in the way that we were going to manage storage back then. It introduced the abstraction of the malloc free, where I just add storage to the pool and all my file systems get to use it, and it's wonderful. So I didn't have to do any of these, all these system administrative tasks just kind of went by the wayside. So it really was a game changer. But if we kind of look at 2005, there were a lot of things that back then that have really changed. YouTube, first video ever published, 2005. Apple was just switching to Intel. Git, just came out as an open source project. Netflix was shipping DVDs, and of course ZFS was released. It's also interesting, the largest hard drive in 2005 that was shipping was 500 gig. That's nothing now. So as we kind of look at how things have changed, we see that YouTube now gets over 300 hours of video per minute that get uploaded. Apple has switched their processors once again. Largest hard drives shipping, 18 terabytes, soon to be 20. Netflix now drives over 11% of all internet traffic is Netflix traffic. And ZFS has kind of proliferated and now is available on Windows, FreeBSD, Linux, and Illumos. What's interesting is that one thing you don't see here is what was going on with Amazon. Amazon was selling books and videos. And now they're a huge retailer, a cloud platform, and a video streaming service. And it's this cloud that has really changed the way data centers now look and how they've evolved. So again, let's look at kind of how things have changed. back in the day when ZFS was coming out, we were talking about servers that were directly attached to storage. Then over the course of time, we started seeing these, virtual machines getting propagated everywhere, and VMware using NAS and SAN as a way to distribute storage to all these virtual machines that were running now on our servers. And they introduced the concept of a virtual disk and having this abstraction layer where we now had like a VMDK that was really some kind of, block emulation storage under the covers. And the cloud has just done this and kind of like proliferated this in a much larger scale. Now we have virtual switches and virtual machines and, instance types, and storage still abound. And we have a lot of virtual disk abstraction layers. But it's changed the way we kind of deal with things today. It's made life significantly easier for most people. We now can do like on-demand infrastructure, which is wonderful. Like, as developers or system administrators or any company that needs compute on demand, being able to like issue an API call or click a button, and now all of a sudden you get a machine, an entire network set up, your own virtual private cloud configuration. And you only pay for what you need. So, I don't have to worry about going and buying a huge rack of storage. I just simply create some EBS volumes and I'm good to go. And if there's a service that I need, well, there's a whole catalog of managed services that I can put around it and just, leverage them. So I get like instant scalability and unlimited virtual block devices. But unfortunately, it's not all rainbows and unicorns. There still are problems. And the problems that we tried to solve back in 2005 have now shifted. So this virtual disk abstraction that we had with the volume layer, with the volume manager, has now been pushed down into like an EBS layer outside of the virtual machine. You still have the possibility of having stranded storage. I can't move things out of this EBS layer onto another virtual machine. I now have introduced capacity limits, which are things that we were trying to like get rid of. Now I have limited controllers and number of drives that I can put on a virtual machine. And what's interesting is like cost has been a big factor. The cloud allows me to pay as I go, but it also means that I don't want to overspend. So the way that I build up my virtual machine is I assign a small number of gigabytes to it, fill it up, and then I'll buy some more, fill it up, buy some more, fill it up, which leads to imbalanced space and potentially some performance issues. So as part of this project, we wanted to kind of like step back and say, kind of, is there a fresh perspective to solving some of these things that we had solved in 2005 and are now having to solve them again? And we thought to ourselves, what about object storage? So with cloud, object storage just proliferated. The abstraction of abstracting out your disks to these objects where you just have like a key and can get access to any object was kind of interesting. It was totally scalable. So unlimited capacity, all great things that, especially for a file system that was designed to be scalable and have unlimited capacity, seemed to be a perfect marriage. And it was cost effective. You didn't have to pay for the huge infrastructure that EBS volumes provided, because these weren't always NVMe drives that are sitting behind some storage controller. They might actually be like spinning metal. And it was a very simple API to connect to. And in a sense, this was another way of looking at pooled storage. What Object Store has done is it's just pooled all the drives together and exposing this through a very simple API and making it accessible to the application. So we thought, well, could you marry those two things together? Could we create this architecture again where you have pooled storage on top of object storage, which is a pooled drive concept, and reintroduce the malloc-free abstraction layer that ZFS was built on in 2005. This was great because it means with object store, it's like there's no disk to manage. I don't have to go and say, hey, S3, give me some more devices. I don't have to go shrink anything. I just simply remove objects and I'm only paying for the space that I'm using. So instead of having to go allocate, a 100 terabyte drive and putting 20 terabytes of storage in there and still paying for 100 terabytes, if I put 20 terabytes in S3, that's all I pay for. and I could scale as much as I needed. But if anybody's looked at Object Store or done any research around it, you'll often stumble across statements like this that simply say, Object Store is great, except don't use it for highly transactional and low latency types of applications. Because one thing that we know about Object Store is tons of bandwidth, but it's slow. So we wanted to look at that and say, okay, could we actually overcome this? Are there ways to overcome the latency concerns? We could provide a read cache layer. Well, ZFS already has an L2ARC component, so great, we could leverage that. We need a way to buffer writes so that we don't have to wait for the long latency when we actually issue a synchronous write. Hey, we have a solution for that too. We can put a slog in. And then lastly, we need to talk to S3. Well, there's an open source project called S3 Backer. Couldn't we leverage that? Uses Fuse, ties in, lets us go kind of directly back to the S3 device, and we can talk to object stores. So this seems like a pretty good model because it gives us all the components that we think are necessary to overcome latency. But there's some problems. S3 Backer, as wonderful as it is, has the limitation that every ZFS block is one object, which means that if I'm using large ZFS record sizes, great. I can take advantage of the bandwidth by sending 1 or 2 meg or 16 meg blocks. But if I'm doing something where I need 4K, 8K blocks, it's going to be expensive. L2ARC, for again, as good it is with working with SSDs, we needed something that could scale, and it has a pretty high penalty on its memory footprint. And Fuse itself has some issues. In addition, one of the things that we discovered is if you try to destroy a pool that's built in this model, those blocks remain on S3. So even though you think you destroyed the storage, you're still paying for it unless you go to the AWS console and remove all the objects manually. And in the end, it was just another virtual disk abstraction, which is again, not solving the problem. And then when we stepped back and looked at kind of our problem at Delphix, we want to be able to handle extensive random reads and writes. We're dealing with databases, which is one of the no-nos for using Object Store. So we needed to be able to have small blocks, in our case 8K, which are typically average, when compressed, are average around 3K. And we wanted to take advantage of the lower cost storage. Again, pay for only what you allocate. We also have customers that aren't system administrators. So the thing that was so wonderful about Object Store is that it's got a simple management layer. You don't have to worry about add additional storage, remove this storage, move this over here, rebalance that. Again, a lot of the principles that ZFS was built on, Object Store kind of mimics. And by having that simple management layer, that also meant that we wouldn't have these user errors that can often crop up. So people may have, you may have seen cases where somebody inadvertently removes the wrong VMDK, or they think that VMDK is free and then end up using it somewhere else, and now you've corrupted it. We wanted to get rid of all those problems. So we needed to create something better. So for that, we set out on this architecture journey. We wanted to leverage the slog device because we felt that would work really well, but we needed a better caching model. We needed something that could scale and scale to extensively large. So if we wanted to have 100 terabytes of cache, great. We need something that can do that with a very small footprint. And we needed to be very smart about its eviction, which means that it also had to be smart about the way it allocates blocks. We wanted to use large objects, but small blocks. So this one-to-one mapping that S3 Backer had couldn't work for us. We needed something better. We need to pack as many ZFS blocks as possible into one large object block and then ship that off. So this is what our architecture looks like. So the things that I'll call out here are the things that are in blue are components of ZFS that are effectively untouched. Things that are yellow are things that we had to modify, and things that are green are all new components. All the red components you see here are external hardware devices. So we're using a slog, so we still have access to an EBS volume, although because it's just for slog purposes, it doesn't have to be very big. So again, cost savings there. I don't have to go allocate 100 terabytes for a slog device. The communication to S3 is now being done by this userland agent, which we call the ZFS object agent. And it's actually talking objects to S3, but it's interfacing with the kernel through a new VDEV layer, a new VDEV component, I should say, which is the object store VDEV. So everything in the kernel still talks about ZFS blocks. And it's when we actually ship these blocks to the object agent that we actually are going to convert these into S3 objects. And then the Zetacache, which is also a userland component, is also talking blocks. So we have the ability to like cache blocks, ship objects, and then the rest of ZFS kind of remains more or less untouched. So you may be asking yourself, why did we choose userland? Why didn't we just implement this in the kernel? Why did we put the object agent in userland? The biggest thing is we didn't want to go implement a bunch of HTTP and JSON parsing in the kernel. There's a lot of tools out there. We wanted to take advantage of that. We also wanted to kind of create fault isolation. So we built this agent that was able to restart, and it could crash, it could be upgraded, and it could change without impacting the rest of the system. So you can actually put in a brand new agent, restart it, and the rest of the kernel just picks up where it left off. And in addition to that, we wanted to take advantage of newer, richer languages that were available that aren't available in the kernel. And so we chose Rust. So then you're probably saying, well, why Rust? Well, the big thing here is Rust is fast. It's got a lot more semantics. It's much richer than a C programming language, and it gives us a lot of additional libraries that we can take advantage of. But the biggest feature is its safety net. So taking advantage of that has been huge for us, especially when you compare the number of lines of code that we've implemented in Rust versus C. And I show that on the bottom of the slide, where you can see we've had 1,700 lines of C code that we've introduced into the kernel, and also parts of userland, and then 13,000 lines of Rust code. But of those 1,700 lines, we've had to deal with data races, things in the IO pipeline, stalls, deadlocks, and they've taken us a long time to go solve. But we haven't had any of those issues in the userland Rust code. So it was a big benefit to us. But this talk isn't about Rust. I'm sure that there's a lot more features that are not covered here, and we have a lot of advocates that would be happy to tell you more about it. But instead, we want to talk about the design principles for the object store project. The biggest thing is the agent's independent. I mentioned that we wanted to have some fault isolation. So having the ability for it to die and restart was key for us, which also means that the kernel has to be able to resume and detect when the agent has died. So if you're in the middle of the transaction group, you need to be able to say, oh, I noticed that the agent didn't finish my, pushing out all my transactions. I can't assume what it knows or what it went out to do or how far it got. So I just need to push it all again. So it picks up and remembers where it left off. So in a way, it's kind of has this concept of communication is kind of out of band, that knows when to send data, what parts of data to send, where it needs to restart, and so forth. We also came up with a very simple block ID allocation scheme. Since we're actually just allocating and doing I++, that meant that we would never overwrite any given object. So when we allocate a block, we're never going to reuse that block ever again. This allowed us to make some very interesting things and simplify things like in-sync convergence. We now don't have to worry about multiple passes over the data, waiting to do things like don't compress during this pass, overwrite blocks during this pass. All that got simplified. We're able to simply say, we're going to allocate a block, we're going to ship it to the object agent. The object agent's going to put it into an object, and from that point forward, if we ever do another update on that, it just simply gets updated. We don't ever reuse the block. So the three big architectural components here are the object store in the VDEV layer, the Zeta object, and the Zetacache. The VDEV object store is using a Unix domain socket to communicate from the kernel to userland. It's the one that's going to be responsible for taking offsets, which is what the rest of what ZFS uses, or DVAs, and convert that to block IDs, which is what the object agent wants to talk about. And it's in this layer where we do all our, our resume logic. So if we get a disconnect, we simply pick up and resume from there. It's worth noting that in this object store, there's a lot of room for improvement. So today we're copying the data from kernel to userland, but we recognize that we can make, share those pages, avoid the copy, and even change the data format that we're using. So at least at this point in time, we've kept it simple primarily to get this project off the ground. And the performance numbers actually look pretty good, and I'll talk about those a little bit later. As far as the Zeta object agent, it will then take these block IDs and convert them to object IDs. And Matt will talk a little bit more about kind of the details of how it does that. It's also totally responsible for all the object management. So it knows which objects are currently cached, which objects it needs to go fetch, how it maps from block ID to object ID, when it has to do consolidation, when it actually has to do freeze, and is responsible for all the S3 communication and authentication. And then the new Zeta cache is a simple implementation of an on-disk LRU cache. And this afternoon, there'll be a whole talk that describes the details of it. So with that, I'm going to turn it over to Matt to talk about the key data structures.
Thanks. One thing. All right. Yeah, so I wanted to talk about how we implemented this. What are the on-disk data structures, or maybe I should say on-object data structures, and what the implications are for performance of the project. Oh, wrong side. There we go. All right. All right. One thing that we could do is we could say every object in the object store is one ZFS block. So each block, ZFS takes it. Let's say you have record size 4 meg. It compresses down to 1,234 kilobytes. We take that and we write that out into one object. We call it object ID 2. It contains block ID 2, and we put it in the object store using a key that looks like this. So everything goes under ZFS / and then this number is the pool GUID. So all the objects related to this pool will be under here. Data for data objects, and then object ID number 2. And then the next block that the kernel allocates, maybe it's bigger. We put it into a bigger object, give it block ID, the next block ID 3, and the next object ID 3, put it in there. So this is really simple. As long as your record size is pretty big, then this is going to probably work just fine, and you'll have performance that's kind of theoretically should be similar to S3 Backer. In practice, we saw it's actually quite a bit better. But obviously it'd be a lot easier to manage than using S3 Backer because it's all native ZFS. The space is coming and going as you're doing those block allocations. So if all you care about is large blocks, then that's pretty much it. Like, talk's over, you all go home. So why that caveat? Like, why does this only work for big blocks? Well, it's because we need to use big objects to get good performance. So this graph is showing us how throughput changes, maximum throughput changes as we increase the object size. And we want to be up here at, where basically this is the network throughput limit of about 25 gigabits. But the problem is that the object store is dominated by latency. So put object latency is around 50 milliseconds. And that's kind of true regardless of object size up to some point, but it's at least 50 milliseconds. So in order to get good overall throughput, you need to either increase the object size, which is like moving to the right on this graph, or you need to have a larger queue depth, so have more put objects operations going on concurrently at the same time. So that's like switching from this red line, which is 100 puts concurrently, to this blue line, which is 1,000 puts concurrently. So we saw that kind of for the parameters that we cared about around 1 megabyte makes sense as kind of a starting point. Maybe 2 megabytes would be a little bit better, depending on the queue depth. But the key thing here is that we want to be able to get good throughput when we're writing, and we don't want to have like a ridiculously large queue depth. I mean, 100 is already like pretty large. You run into limits like number of file descriptors that you can actually have open in a process, and other things that impact efficiency when going to really, really huge queue depths. All right, so that works fine as long as you have big objects, but sorry, as long as you have big blocks, you can just say 1 block per object. But what if you are storing databases and your database has an average of 3 kilobyte compressed block size? Then that's not going to work. 3 kilobyte object sizes would have very, very poor performance. So what we're going to do is combine a bunch of blocks into one big object. So in this example, we have like around 300 blocks being combined into one roughly 1 megabyte object. And again, we're going to store it. We're going to have this concept of object ID. We're going to use that to generate the key that we use to store the object in the object store. But the mapping from object ID to block ID is less obvious here. So as we're writing, we're going to write out, the kernel is going to be sending us a bunch of blocks. It's going to be sending them in sequential block ID order. So first it gives us 123, 124, 125, etc. And the agent's going to be batching those up until we get about a megabyte of data, and then do a put object to store that into one large object. And the object contents are self-describing. So if we look at what's actually in this object in the object store, it has the data and it also has a description of what the data is. So it says, I have block ID 123 and it's 3.5 kilobytes and it's at this offset within the object. Right, and the block IDs that we're talking about here are allocated sequentially and they're never reused. So once we've written block ID 124, the kernel's never going to come back and say, hey, like change the contents of block ID 124. It's just always increasing for forever. So hopefully this, the right code path kind of makes sense here. You're just batching it together, splitting them all out. But what about reads? So if we want to do a read, the kernel is going to send up a request saying, please get the data for this block ID. And we need to figure out which object has that data inside of it. So the way that we do that is by keeping a mapping in memory that maps from the object ID to the minimum block ID. So we want this data structure to be really compact. So because the object IDs and block IDs are both sequential and increasing, if we get, say, for example, a read request for block ID 400, we can look through this table, do like a binary search and see that, okay, 400 falls between 346 and 667. So it must be in object ID 5. And we can go read that object ID and see that it has block ID 400. So there is obviously some memory cost to this. In kind of the current naive implementation, it's about 16 bytes of memory for each 1 megabyte object, which comes out to, if you have 100 terabytes of data in your pool, in your storage pool, then it's about 1.5 gigabytes of RAM, which is like, maybe that's acceptable. I mean, 100 terabytes is, pretty big, at least for databases. But we think we can do a lot better than that because, like, if you look at this table, you can see, the object IDs, we allocated 8 bytes for that, but really each one is just sequentially the next number. So maybe we can just get rid of that entirely. The block IDs, they're not sequential, but they can't differ by, 2 to the 64. Maybe they differ by, 2 to the 10 at most or something. So maybe we can get away with just like 10 bits of information encoding the delta between each next entry here. So I think all things considered, we should be able to get this down to about a quarter of that, which is even more reasonable, 400 megs of RAM for each 100 terabytes. And of course, we need to keep this mapping on disk as well, or in the object store, I should say, persistently, so that if we crash, we're able to regenerate this this in-memory table. And by crash, I mean if the object restarts. So it might not be a full system crash, but it might just be that the object process, the agent process is restarted. Then we need to read this back into memory. So how do we store the mapping on disk? Basically, we store it in a log. The log is just, logically speaking, it's like an array of entries. The entries are going to tell us what's the object ID and what's the block ID associated with it, the minimum block ID. And this is going to be split into a bunch of objects. The objects are going to be numbered sequentially. So in this example, we have like chunk ID 0, which basically means like the object ID 0 of this particular object-based log. It'll be stored in the object store, again, with the key, something like ZFS / the pool GUID. Now we're in the object block map namespace, and then this is object 0 of that. And that'll contain maybe the first 10,000 entries and the next 10,000 entries in object ID 1. You know, what it comes down to is basically every transaction group, we're going to be appending a new object or maybe a couple objects to this log that indicates what other objects, what data objects were allocated and which blocks they contain. And then periodically we're going to have to, these objects might be kind of small, so you might end up with a lot of them. And so periodically we might want to condense these by rewriting this log more compactly in big, large objects. Similar idea to what we do with ZFS's space maps, if you're familiar with those. All right, so that kind of covers like what happens when we're writing, what happens when we're reading. There is one other operation that we might want to care about, which is freeing. So how do we reclaim space that's no longer needed? So there's a couple problems that come up when we think about this when you have a bunch of blocks within one object. So in this example, we have one object, object ID 4, and it has a bunch of blocks. And the kernel says, I'm going to free block ID 125. So what the free means is, it just means I promise that I'm never going to read this block ID again. And so FYI, you can do whatever you want with that. Preferably, maybe you use less data in the object store so that Amazon charges you less. So what we want to do is, in order to actually reclaim space from the object store, we're going to read this object and then write out a new version of the object that omits the block that we don't need anymore. So this works, and we're overwriting the object in place. So we're basically replacing its contents with the new contents. And because the object contents are self-describing, it's pretty cool that there's no race conditions here. So like if the reclaim is going on in the background and we don't have any locking and somebody else, some other thread is trying to read block ID 128, then they can do a get object. And if they get the old object contents or if they get the new object contents, it's going to work either way. So because the object is self-describing, whichever one they get will tell them where to find block ID 128 within the object, and that's fine. But it does cost us a lot of throughput. So to process this one free of 3 kilobytes, maybe for example, we were doing a logical overwrite of some random block of our database file. And we wrote a new 3 kilobytes somewhere else, some new object, and we're freeing this old one because there wasn't a snapshot of it. So we wrote in order to write those 3 kilobytes, we had to write the 3 kilobytes of new data into some big new object, but then we also had to read a whole megabyte and then write almost another megabyte. So, you know, we're talking about 600x IO inflation with this naive implementation. So the solution to this is batching. So when the kernel says, I no longer need block ID 125, we say, that's great. I'm going to remember that, but not do anything about it right now. And I'm going to wait until hopefully we get a bunch of other frees of blocks that are also in the same object. And then I'm going to process those all at once. So maybe we get 200 out of the 300 blocks in this object are freed eventually, and now we can read this megabyte and then write out a smaller, about half a megabyte, less than half a megabyte. So we've improved the situation a lot. It's 170x better than the naive implementation on the previous slide, but there is still some I/O inflation because we do have to read this and then write it out. Even though it processes a lot of frees, there's still some costs associated with it. So the key to getting good performance out of this reclaim process is to make sure that when we're rewriting an object, it has lots of frees. So how do we find the objects that have lots of frees? Well, first of all, it would be nice if we could just wait a really long time for lots of frees to accumulate in all the objects. But we can do better than that by sorting the objects by how many free blocks are within them, and processing only the ones that have only the best ones, the ones that have the most frees within them. And then we'll save the others for later, hoping that they accumulate more frees in the future. There's a bunch of tunables here, and we can probably be smarter about this in the future. But right now, there's a tunable that says what's the that basically tells us how long do we wait until we reclaim, and that's just a percent of the total pool size. So we say hey, whatever your pool size is, having 10% of it free but not yet reclaimed is okay. Basically means you're going to be paying 10% more for your storage costs than if we were extremely aggressive about reclaiming the free space. But the trade-off is that the reclaim is much more efficient and uses less throughput. So how do we keep track of? We keep track of the blocks that have been freed but not yet reclaimed in this reclaim log, which is basically just an array of this is the block ID and this is the size. The sizes are used to go in to find the objects that have the most free space when we go to do the reclaim. So the reclaim log, as we're getting frees, we're appending to it. Then we need to load that reclaim log into memory in order to find which objects have the most free space. So that uses up some memory. Actually, we want to be able to have as much outstanding frees as you want to set that tunable to without having an impact on the memory requirement. So what we actually do is we break up the reclaim log into several logs with different frees to different object IDs going to different logs, and that limits the amount of memory required to process the frees. So this example here is to load 10 million frees, but we can have as many logs as we need so that no log has more than 10 million frees, for example, to limit the memory used. Limit the memory used to a constant regardless of the pool size and the amount of outstanding reclaimable space. All right. So there's a couple more problems. First off, the object block map memory usage is going to keep growing and growing over time. So as we're doing writes, we're allocating new objects. We're appending new things to the object to block mapping. We're keeping track of those in memory in the table that looks like this. And the issue is that if you're just writing and you're not really freeing much, then it's not a big deal. But if you have a lot of churn, say because you have a database and the database is randomly overwriting lots of different blocks in the database files all the time, and writing its logs and then overwriting its logs at the database level, then you're gonna have a lot of churn, meaning a lot of the data that's present in the pool now won't be present in the pool a month from now, but it'll be replaced by new data. So the size of the total amount of data in the storage pool might remain relatively constant or be growing slowly, but the total amount of data ever written to the pool is very, very large. So for example, if you're writing at 100 megabytes per second on average, then this table might grow to be 12 gigabytes of memory for every year that you've been running this pool. And we have customers that are writing at this rate, at this average rate with our block-based solution. and that have pools that are many years old. So that seems like not a great use of memory. And the other problem is that the objects are going to get small. So as we rewrite each object, omitting the freed blocks, it's going to get smaller, and then maybe we do that again and again until it's like very small. And that means that if we need to like do a table scan or read through a whole file, getting all of its blocks, now we have to read a whole lot of small objects, which has the same problem as large objects to a little bit lesser degree. It's also latency dominated. The latency is kind of at least 20 milliseconds. So that's less than half of the puts, but it's still pretty significant. And again, you want to be using large objects to get very good throughput with reasonable queue depths. All right, so how do we address that problem? We address it with object consolidation. So when we're processing, when we're doing reclaim and processing freeze, we're going to look at several adjacent objects and the frees that are associated with all of them. And we might see, okay, in object ID 4, we're freeing most of it. The yellow blocks are the ones that are being freed, and the blue blocks are the ones that we need to retain. But maybe there's only a few of them. Those don't add up to a megabyte. They add up to like some small fraction of a megabyte. So let's look at the next sequential object ID, so object ID 5, and see what needs to be freed there. Okay, a bunch is being freed. We need to retain a little bit here. Let's add those to this object. And as long as it's not a megabyte yet, we keep on doing that, accumulating more and more, consolidating the retained blocks from more and more objects into this one object that's going to replace them all. So to do this, we can kind of figure out all of this based on the in-memory metadata without having to read any of the data objects. And then we need to read, all three of these data objects, and then write just the one new large one, and then eventually delete these object IDs 4 and 5 that are no longer needed at all. Or sorry, object IDs 5 and 6 that are no longer needed. After we've persisted the object to block mapping change. So in the object to block mapping, we're going to remove the entries for object IDs 5 and 6. In the on-disk log, we're going to add a free type entry saying that these are no longer needed, and then we're going to remove them from the in-memory table. So now, there'll be some object ID 7. You'll have an entry for object 4 and object 7, and then we know that all of the blocks between them are in object 4 because 5 and 6 aren't there. Cool. So this works pretty well. There's a lot of work that we can still do in the future to improve this even further. So like one of the ideas is right now we're kind of batch processing the reclaim. So it's like we start reclaim, we do it as fast as possible. We stop doing the reclaim, we wait until you hit the high water mark and then do it again. We could probably improve on the behavior of that by chipping away at it, like every transaction group little by little, and then having like some kind of feedback mechanism that tells us like how fast we need to be chipping away based on how close you are to getting to the high water mark. You might also want to have different kind of controls over like when this happens. If it's impacting performance, you might want to only do it at night or on the weekends. You might want to have some like minimum efficiency setting where you're like, yeah, I don't really mind paying for that extra storage space for a while, but I really don't want to impact my network throughput by doing lots of gets and puts. So I want to say like only do it when you're able to free like 90% of an object or something like that. But absent those future performance, how does it actually work today? So this is a graph showing the x-axis. The x-axis is time. This is about 30 seconds here, and the y-axis is well, the green, red, and blue are network throughput, and then the magenta here is amount of space that's allocated in the storage pool. So what's happening is we're going along. TXT sync is putting data to the object store at about 700 megabytes per second. Then we start a reclaim, and then we're going to be reading and writing data. We can do that very quickly. And then we go back to that's done, and we reduce the amount of allocated space. So the workload here is random writes, about 15,000 IOPS into a 1 terabyte file, completely random locations with record size 8K, and the average compressed block size is 3K. So this is what I would consider a very demanding test. The only way that I might make it more demanding would be to increase the file size, which serves to scatter the writes even further, and the indirect block updates become even more expensive. So on this very demanding workload, we're seeing that we're still able to process freeze at about 1400 megabytes per second, versus the writes are about 700 megabytes per second. So it kind of makes sense that like half the time we're reclaiming and half the time we don't need to be reclaiming. For our workload, which is this pretty demanding workload, because we aren't reclaiming all the time, we're able to keep up, and we can see that the impact on the rate that we're ingesting data with TXT sync writes, it goes down a little bit, but not that substantially while we're in the middle of the reclaim. So the kind of conclusion for us was there's spare network bandwidth, and we're able to do this in parallel with ingesting the writes, still at a good throughput. So even despite not having some of that feature work, it looks like it's good enough for our workloads. And for more typical workloads where you're like, the record size is the default, and most of my data is in large files, and they have the record size of 128K or maybe even more. Mostly what I'm doing is accessing files sequentially. Really, this solution is vastly over-engineered for that kind of use case. And the impact of reclaim is going to be negligible on that kind of use case. But we wanted to make this work for our use case. And it's also really satisfying that this works for a wide variety of use cases. We don't have to say like ZFS on object store, as long as you're just using it for archival or backup or whatever. This is really, it's usable for general purpose workloads, even including some of the most demanding ones. Obviously there's performance concerns there, but the ultimate, the bottom line is that the performance is very good. All right. Cool. Let me turn it over to Manoj. Would you like to can you unmute yourself? If not, I will. No, I'm going to let you. You should be able to unmute yourself and show your video and show your screen, and Paul as well if you'd like. Cool. So Manoj is going to give us a little demo of how you use this.
Hopefully you can see my screen. Okay, so let's take ZFS on object storage for a spin.
Do you want to full screen it?
Yeah.
It's like in the lower right.
The Zoom thing comes in delay. Okay.
Right. Yeah, that was great for us.
Okay, so as you've been told, the ZFS object agent is a userland thing. So we'll start by kicking it off, and we'll let it run on that window. So we are invoking the ZFS object agent, and off it goes. And now we are ready to create a Z pool. So as you might imagine, we have to specify additional parameters so that we can specify where the pool is going to be created. So we need to specify the endpoint and the region where the S3 bucket is going to be, the pool name, obviously. And we have, as George mentioned, we have a new VDUB type, the S3 type, and we have to specify the bucket, the place where all the objects will reside. And in this case, I'm going to add in a log device as well. And so the pool is going to get created. And so that's the pool for you. And if you notice, just like the device is specified, the bucket is specified here. And you can see the NVMe log device there as well. So I started off the agent by hand, but you probably want to be using some system management service like systemd to run this. So let me pause the video just a second again. So as George and Matt mentioned, the agent is designed such that it can be killed and restarted, or it can crash and come back up and things are still going to be fine. So it's resilient. So that's exactly what I'm doing here. I'm killing off the agent. The pool is still online, and I'm going to start it off as a systemd service. So the systemd service is on, is going, and let's take a look at the log on this window, the debug logs, while we proceed with the demo. All right. So now the agent is running as a service, which means it will get auto restarted in case something goes wrong. So Matt talked about workloads where you have a 8K record size, compression is turned on, and you have a large file and you do random writes. Let's do just the same thing. Okay, let's create a large file, and we have a ZFS file system with 8K record size, compression turned on, and let's go do some random writes. So we're going to first create a large file, and I'm going to speed this up. All right, and next, let's do some random writes. And then we are going to use IOStat to see how it looks. And IOStat has been improved or enhanced with the -o option so that all object stories things are listed. So if you look at the first column, that's the traffic between the kernel and the agent. The second column tells you about the traffic between the agent and S3, the object store. The metadata traffic is captured, and reclaim happens. Matt went over that quite a bit. So reclaim happens as well. So the thing to notice here is that we are doing about 100 meg of throughput, and the throughput between the agent and the S3 is also roughly close. But the number of objects, the operations, there is a significant difference, about 100, 150 operations from the agent to the S3 bucket, but about 36K of operations is what the kernel is doing. You also notice that the reclamation, the object reclamation is also going on, and it goes in bursts, and we keep reclaiming objects. All right, let's kill that workload and let's look at something else. So import export. Now export is fairly straightforward. It's you export a pool and you're done. Nothing special about this. But import, as you might imagine, like zpool create, it needs additional parameters. It needs to be told where to go import stuff from the endpoint, the region, and the bucket, the S3 bucket. So the -d option specifies the bucket. Think of it's similar to the -d option for block-based devices, where you specify a directory to go look into. That's the bucket equivalent. You specify the region, the endpoint, and then the pool name, and zpool imports it for you. It takes a little bit of time. We'll talk about that in a bit. About 5 seconds, and we should be done. Yeah. So we are done. Let's take a look at the zpool list. So pool 1 should be there. Yeah, it's there. And we can also do a search import where you tell ZFS import to go look for pools. And so let's try that on our bucket. And interestingly, we have a pool that we did not create on this VM. Pool 2. So why don't we just go try doing a zpool import on that? Pool2, let's go try and import that. And we hit a failure. Specifically, it says that the pool can't be imported because it's currently hosted on a different host. It's imported on a different host. What exactly happened here? Hey, Paul, can you walk us through this?
Sure thing. So this is an example of a feature called multi-modifier protection, or MMP. ZFS already has this feature implemented in the kernel. It's useful for situations where you have storage area networks or network attached storage where multiple systems could potentially try to import the pool at the same time. We re-implemented this in the agent for a very important reason, and that's that it's extremely simple in the cloud and object storage use case for multiple systems to be accessing the same bucket, to be accessing pools within that bucket. And with some pretty easy misconfiguration steps, it's very simple to have multiple systems try to import the same pool at the same time. ZFS is an extremely reliable file system, but multiple people trying to write to a pool at the same time is a very fast way to data loss. So for that reason, we decided to re-implement MMP in the agent, protecting both the ZFS data and the agent's own metadata. The checks take slightly longer. As Manoj pointed out, during the import process, it takes anywhere between 5 seconds and 20 seconds in a contended use case. But it's designed in such a way that it is almost impossible for multiple systems to end up succeeding at an import. It would require very extreme networking configurations on multiple systems happening at exactly the same time. And so the additional time cost was deemed worth it given how important it is in the cloud use case to prevent multiple systems from accessing the data at the same time.
All right, thanks, Paul. So let's do a little more of the MMP stuff. Let's go over to the host where the pool2 is online. Yeah, it's right there. And instead of cleanly exporting it and importing it on the other pool, let's do something more interesting. Let's just power off this this other VM, and we power it off, and then we are going to see if we can import it safely with MMP on the other VM. So let's try that again. But this time, it's going to take a little longer because, as Paul said, it takes a little longer for the negotiation to happen. And I'm going to speed this up. All right. It took us about 34 seconds here, but the pool has been safely imported and it's online. So let me pause the video again to talk about something else. If you noticed, we had multiple pools on the same bucket, and that's part of the design. That's very much how we wanted this to be. The bucket is can be shared by multiple pools across multiple hosts, and each pool has its own namespace into which all the objects go. So they don't clobber each other, and you could have a shared bucket, or you could have different buckets if that's the configuration that you want. But shared buckets are totally okay. So if you look at the status, yeah, they are both on the same bucket. Pool 1 is there, pool 2 is also on the same bucket. Okay, so next up, let's take a look at some of the zpool properties. We have a new object endpoint property, the region, the credentials profile. We'll talk about that in just a bit. And so those are the new properties that an object store based zpool has. Next, let's talk about zpool destroy. Zpool destroy for object store based zpools are slightly different. Different because we or the customer is paying for these S3 objects, and unlike a block-based zpool where you destroy it, the blocks stay there. It's marked as destroyed, but the blocks just stay there. we don't want that behavior for object store. When we say destroy, we want the objects to go away so that we are not consuming space on S3, right? So when you destroy a pool, what happens is the agent kicks off a background task that goes and cleans up all the objects, destroys them, and reclaims the space. So zpool status, while the pool is being destroyed, will tell you that it will list the pools that are destroyed. And once the pool has been completely destroyed, you have an additional flag, the -- destroyed option, that can give you a list of pools that have been destroyed, so that you can confirm that your pool has indeed been destroyed. And if you don't want to see that anymore, you can use the -- clear and it will go away. Now, I very cleverly did not deal with credentials so far, and let's now talk about that. So if you have used the AWS CLI, then they take as credential sources, they can take credentials from a variety of sources. And for this demo, I used the AWS identity and access management roles that are associated with an instance profile. And that means that, or what that gives you is that you don't have to deal with credential rotation and things like that. It's done for you. You could do that. And all the various sources that the AWS CLI takes as input, the ZFS object agent can as well. So you can use instance profile if you like, or you can use environment variables, AWS credentials in environment variables, if that's your preference, or you can specify it in the .aws credentials file. You can also have multiple of these credentials as profiles, so that in case you want to have pools, different pools on different buckets with different credentials, you could do that as well. So here is an example of how you would do that. Fake credentials, but you have profile 1 with one set of credentials, profile 2 with another set, and you could use a third one, which is the EC2 instance metadata. And that's all I had. Thanks.
All right. Thanks, Manoj. Find. Okay, let's go back. So what I wanted to talk about now is a little bit about performance. So when we, I mentioned before that we actually started off kind of looking at like S3 Backer and L2ARC and some of the existing components. So it made sense for us to kind of see where do those things stand today. So like we ran some tests, some performance numbers just using S3 Backer and trying to get like its raw throughput. So what you see here is the raw throughput of sequential reads and sequential writes. And I'm using FIO and the ZFS perf test to actually generate these numbers. So this is using 128K IO block size. So I'm going relatively large, but not as big as maybe we would necessarily need. But what's interesting is it gives us a baseline. So then we wanted to see like, where do we stand with our current implementation of object store on ZFS? You can see that we're right around the 3 to like 6x range of performance numbers. So we're getting a lot more read throughput and a lot more write throughput. But that's great because like S3 has a lot of throughput to give, and you're going to be limited by how much bandwidth your instance type has. But what we really care about are what are the IOPS. So again, I wanted to start off with like S3 Backer and kind of what does that give us in kind of the configuration that we had. And I started off without an L2ARC. So this is just going straight to the S3 device. You can see that the random reads are just kind of horrible. And random writes are all right. But nonetheless, this would not be something that would satisfy us. And the latency for S3 Backer is actually really bad when we talk about reads. So we needed to kind of look at this was kind of a non-starter for us. Again, looking at the comparison with just using ZFS and our implementation of object store, we see that at least in this case, we're able to lower the latency of random reads from 346 milliseconds to 89 milliseconds. So still not great, but a big improvement overall on kind of where we're headed. So we kind of knew we were on the right trajectory. So what if we added an L2 ARC device? And again, comparing both S3 Backer and ZFS with an L2 ARC, the good news here is that we're actually now getting latencies in a more acceptable range. And I mark it here as yellow. So 17 milliseconds for random reads. Okay, it's probably like, comparable to like, maybe some older spinning disks, but not necessarily what you would need for like high transaction rates. So this was kind of like our starting point. And again, our starting point was really based off of, taking ZFS and making a more integrated solution to talk to the object store. But as I mentioned in the talk, like we needed something better. And that's where Zetacache is going to pick up. So we'll talk more about that this afternoon. But is there more to like what we've solved here? Like as you start thinking about kind of some of the techniques that we use to implement object store, can we go beyond that? So I wanted to kind of like throw out some kind of crazy ideas of like, where do we go? Can this be leveraged in other ways? For example, could we use this for shingle media? Could we define an object to now like define a track on a shingled media drive and then use some of the techniques of like actually knowing a block to object mapping to define and move regions around when you're actually going to do writes? Maybe this replaces the need for BP rewrite. We've talked about that for many years. Could we abstract the block pointer? Now we have the ability of having the block pointer just be more, virtualized, and it doesn't matter where its location is because, again, using the object map, could we actually determine where its new location should be if we need to move things around? And there's many more. There's many things that you could think of. The other thing to think about here is, what would you do with ZFS if you had unlimited storage? What if you could like store anything on here and not have to worry about those capacity limits? I think that's the era that we're kind of going into, and that's what makes this a really interesting thing for us. And hopefully it sparks some ideas in the community. And with that, we thank you and we'll open it up to questions.
Cool. You probably unshare your slides. There were a bunch of questions asked in the chat that have been answered. We can reiterate those for folks who are listening. But first, let's see if anybody would like to ask questions now or live. I think that you should be able to share your video and audio if you would like, or if not, then raise your hand and I'll fix that for you. Mersin, go ahead. I see you unmuted. We can't hear you if you're talking. Oh, is he muted again? Okay. Yeah, anybody else who would like to, if you feel to jump in, I'll start going through some of the questions in the chat. All right. So there's a question about Scrub, and then a couple of kind of related questions about Scrub and how does like z equals status dash v work. At a high level, I mean, ZFS is still maintaining a checksum of each data block stored in the block pointer in the indirect blocks. And so you can run z equals scrub. It'll go read every data block off of the object store and verify that the checksums match. And if they don't match, then it'll be reported in the z equals status dash v, just like normal. Right now, the performance of that is not great because we don't have the like sequential scrub optimization hooked up. It needs to be updated to know about like block IDs versus VDEVs and offsets, because we've kind of shoehorned the idea of the block ID like into the block pointer, but like a naive interpretation of the block pointer that doesn't know about that would think that there's overlapping allocations. So we need to teach that code about the block ID stuff. But otherwise, works naturally. And
yeah, it might be worth mentioning, Matt, too, that like although we didn't talk about it here with Zetacache, is we have taught Scrub to know about Zetacache,
yeah,
and have the capability of scrubbing the blocks that are going to be stored on the cache. You know, for those that are kind of familiar with like the way the cache normally plumbs into the rest of the stack, it's like this is kind of, it's living below the IO pipeline, so it's in a different location, which meant that we had to kind of treat it a little bit differently, but it actually worked out really nicely for us.
yeah, I think that's a great point. It does integrate with the Zetacache that we'll hear about this afternoon. There are a couple of questions that haven't been answered yet here. So from Thomas Wagner, are there any active use cases for S3 already? I assume you mean like anybody using ZFS on Object Store on S3? We haven't put this into production yet. We're still working on implementing it. But you know, the use case is the one that we've described of you know, storing databases in our Delphix you know, data virtualization product.
Yeah, the one use case that I found very commonly when we kind of were getting started is there are a lot of people that are using the S3 backer implementation. I found people both on Linux and FreeBSD that have been using this, and they're using it primarily for backups, right? Like because, you know, as I mentioned, like any of the literature you read, Object Store is just not really designed for, you know, for low latency, you know, high transaction type applications. And so the applications that are out there are not pushing that limit. We're kind of venturing in that. And, you know, from what we've been able to find and the performance numbers we're getting, we feel that this should open up a lot more use cases if we can get to that kind of low latency, high transaction rate.
Cool. The next question from Powell is asking, what happens if you allocate an object in S3, but then the system crashes, or maybe the agent crashes? Is the object leaked, or do we somehow figure out how to delete it? Yeah, that's a great question. So you can imagine something here where we're writing out these data objects, we're doing a TXG. I mean, so first I'll cover the case of like the system crashes. So like, let's say we're in the middle of a TXG, we've written out object A's 5 and 6. Those are part of the next TXG. The whole system crashes, the kernel crashes, we come back up, we open the storage pool. How do we find objects 5 and 6 to delete them? We do. So we do find them and delete them. And the way that we do that is, so I simplified the key here a little bit. We've actually like forward padded each of these object IDs with like it's actually, you know, 00000000005. And the reason is that then it lets us easily find, we know what is the last valid object ID that's basically stored like in the equivalent of the Uber block, like in a per TXG data structure. So when we open the pool, we're like, okay, the last valid TXG is 192. In that TXG, the last valid object ID is 4. And so we can do a list objects and list all the objects that are in this prefix after the one that's 0000004, and that list will contain, you know, 5 and 6, and then we'll delete them. So that's actually a very quick and efficient way to take care of that. There's actually a much more interesting and tricky use case where you're in the middle of a TXG, the agent crashes or is exited and restarted, and then you need to pick up where you left off in that TXG. So we've written some objects. The kernel doesn't know about that because it doesn't know about objects at all. It's still running, but it doesn't know about it. The agent has been restarted, so it doesn't know about them. So in that case, what we do is we do the same thing of like, okay, the last TXG that I wrote out has the last object ID 4. Let me list what objects are after it. But those objects, we don't necessarily delete them because we might be in the middle of writing them as part of this TXG. And we may have already told the kernel that all the writes to those have completed because like it was persisted on disk, it persisted into the object store. And as far as the agent was concerned, like everything was done and it told the kernel, great, those writes are done. You don't need to hold on to that memory anymore. And so the kernel's like, great, like I freed that memory. The kernel doesn't have any way to replay those because they aren't in flight anymore from its point of view. So, but then there might be other outstanding writes from the kernel's point of view that do need to be replayed. So basically we have to stitch together um, what was left on disk, like what objects are there, and the outstanding the ZIO writes that were outstanding when the agent crashed, which the kernel can replay into the agent, and then we can stitch that together and fill in, any missing objects that hadn't been persisted.
Can you hear me now?
Yes.
Perfect. First of all, awesome talk, awesome functionality, which I was waiting for since the leadership meeting it was introduced on. And on that leadership meeting, I shared my use case for that, and that would be ability to mount to import pool on multiple hosts and mount data sets on those multiple hosts. And I have a volume migration of containers in mind for that. I know that writing to the same pool on multiple hosts, as was said on the presentation, is questionable. But can we imagine a situation when hosts are allocating specific data sets and block the access to specific data set? And when it was unmounted, it is allowed to move on to the another host. Right now, for the containers that have less demanding workload, I'm using S3FS Fuse implementation that allows this quick switching between hosts. For the more demanding containers, we have ZFS send receive and the classic data set on the each host. But switching those workloads is challenging in matters of time that is used to send and receive said data set.
So one question, Marcin. So in the case where you're using it, are you kind of envisioning like moving the storage pool to another host, or how are you actually, you're replicating the data completely?
I have in mind the one storage pool imported on multiple hosts and data set that are dedicated for each host.
Yeah, so effectively you want a kind of like an active type of high availability, yes, type of
yes, but with exclusivity on the dataset level.
Yeah, I think that's a neat idea. It doesn't fit exactly into what we've done here. Because there's still pool-wide metadata that all of the hosts would need to access and update. Like, for example, the last block ID that was allocated, right? So we maybe during the hackathon or the discussion afterwards, we can bounce some ideas around of like what could be done there. But I don't think that it's like it doesn't just work. That's for sure.
Right. Okay. Second question: have you in mind optimization for the use case when we have our own implementation of S3, let's say min IO, when there is no impact on the amount of the API calls you are allowed to use?
We got a related question on YouTube actually, which is, do we have any tunables around controlling API calls to limit costs for the services that provide that?
Yeah, we haven't thought extensively about like what exactly you would want to optimize differently. We do have extensive tunables to control all this stuff. So like average block size, average object size, the reclaiming, how all that stuff works. Hopefully, the fact that S3 is like more restrictive in terms of like you have to pay for every little thing means that it'll work fine, and we kind of try to make it work well in that environment. It should work well in less restrictive environments as well. if there's some other cloud provider that like charges you for something that Amazon doesn't charge you for, then that would be interesting to know about, so that we could think about, how what costs might be incurred there given the design.
Yeah,
Um,
and definitely with like MinIO, I mean, we've tried that out. It works just fine. But yeah, there might be cases where we could make a different design decision, knowing that we don't have to pay, the per egress, ingress, operation type costs. Yeah, that's something to definitely think about.
Yeah. And then a related question that we also got on YouTube was a number of people were asking about stuff at the VDEV object store layer. Do we support clouds other than S3? Would it be possible to have multiple clouds backing a pool in like a mirroring configuration? And is it possible to have disks combined with object storage as the backend? And I answered all those there, but I figured I'd just repeat the answers here. Right now, we support any cloud that provides the S3 object storage API, which is a number of them. But we do plan to add support for more things in the future, like Azure, I think, has their own API, and we would like to add support for that as well. Currently, there's no capability to mirror between multiple object stores as the backend, but again, it's not precluded at all by the design. It's just something we would need to actually work on and implement. And then the question around having disks combined with object storage and possibly as a tiering solution is an interesting idea, like having disks as your primary store and then migrating data back to object store to save space and stuff like that. We haven't done any design work on it, but it is definitely something that would be interesting to work on in the future, I think.
Stay tuned for the Zetacache talk.
Yeah, it's kind of related to that.
Yeah.
I mean, we kind of need multiple tiers, but we design it as a cache rather than a tiered kind of thing where tiering usually means that the data might live in exactly one place and you can move it from here to there and it doesn't exist here anymore, which we didn't see as a requirement for our use cases. Caching is good enough. There were a couple other questions on the text that I think are interesting. I'll repeat. From YouTube, Rahul asked, how does reclaim happen if you're using S3 tiering or lifecycle policies? So the free space reclaiming that we're doing doesn't interact with those S3 level things. Basically, we're kind of assuming that only one copy of an object is retained. In terms of in terms of if you're using S3 lifecycle, keeping old versions of it, versioning. We don't take advantage of that versioning, and we kind of assume that you don't have it. You could probably use that to roll back your pool really far or something, but we haven't tested that out. In terms of tiering, the tiering, I mean, it's going to kind of just work and do what it does, moving stuff from the S3 normal tier to Glacier or whatever. Of course, if we go and do reclaim and that needs to read some old object, then that's going to bring it back from the Glacier tier to the main tier. So you would probably want to configure the reclaim and the movement policies such that normally you wouldn't normally stuff wouldn't get moved into the Glacier tier until most of the freeze had already been processed. I suspect that it'll kind of if you have those kind of workloads for which the tiering is useful, then it'll probably just work fine anyways, because you're probably using big files and big blocks, and the reclaim is really not an issue in those cases. In theory, I think we probably could add some smarts to say before doing, you have different reclaim policies for stuff that's in the Glacier tier versus in the normal tier. And we can query and find out, has this object already been moved to Glacier? If so, then let's not bother reclaiming it maybe at all, or not until it's 99.9% free or something like that. That would be an interesting extension.
Mm-hmm.
Jorgen, do you want to ask your question live?
I suppose I could. I don't really know much about S3, so I don't know if there's a particular limit to it, but all your examples you had, the key count IDs counting, I mean, your example there is 4, 5, and 6.
Yeah.
And then you have the object mapping to take the block number and a map into which ID goes to that table. Is there any particular reason you couldn't, instead of using 4, 5, and 6, use 1, 2, and 3, 3, 4, 5, 3, 4, 6, and so on?
Yeah, like
the lowest block.
Why not just use the object ID equals 123, right?
Mm.
That
Can you not list what you have, perhaps?
I mean, you can. I think that a solution along those lines, we considered that. I'm trying to remember all the shortfalls. So essentially what you're saying is like, take this table, but get rid of the object ID column, and then just have the min block ID and use that as the key.
Essentially, yeah. Saving the memory and so
on. I think that might work until you do object consolidation.
Yeah, it does fall apart then.
Because let's see.
It should work for consolidation as long as you always consolidate to the left. Yeah.
Yeah, since we're always consolidating to the left, it might work.
Yeah, it's an interesting idea. I mean,
it makes finding the orphaned objects after you do a reboot. You have to, I mean, you're not just going like, iterate through the next objects. You have to like scan upwards, but it should still be pretty doable. I don't think that should.
I actually had the design that way in an earlier version. And now I'm trying to remember, like, I'll have to go look through my notes and see why I changed it. It might be that I just changed it for ease of comprehension. Because like, it's a little bit hard, it's like hard to wrap your head around, like, oh, there's like this object whose ID is, 346. And that tells me something about the contents of it versus this more abstract, more cleanly abstracted layering. But yeah, we should go look at that again and see if there's a memory savings that we could have by doing that.
Okay, thank you.
Did you have another question that you wanted to ask?
Not me.
Okay.
There was one other question from YouTube, which was about the MMP stuff, which is, would it be possible to have one modifier and also have readers operating in parallel with the modifier? The answer to that is yes, except that once blocks start to get reclaimed, you can run into some issues. So you could potentially use something like checkpoints for that, which would prevent the reclaims from happening and should make it possible to do reads of things like snapshots safely, even if the active system could be destroying those snapshots or whatever. And checkpointing is implemented for the object store as well. We do have that working.
Yeah, the behavior would be like at one level kind of similar to having a block-based pool that has one writer and multiple readers, where it's like, yeah, like as long as the reader starts from a given snapshot from a given TXG and those blocks aren't freed or overwritten, then it'll continue to work. And you could use checkpoints to ensure that that's the case, where you say like, okay, like multiple readers open the pool from the checkpoint, that's totally safe. But if you want a more like arbitrary thing, then you might get checksum errors or on critical metadata and things might blow up. For object store, it's kind of similar, but it's a little bit safer because you aren't going to get like checksum errors on weird things. The only error that's really possible is like I'm doing a read, the block should be in this object, but it's either not in that object or the object ID doesn't exist anymore. So it should be like a little bit easier to handle that error maybe. But you would still have that problem in the kind of general case if you weren't using the checkpoint like Paul was saying. All right. I think that was all the questions. So let me stop the share. All right, cool. Thanks. thanks everyone, including myself, I guess, for the talk. In the break now, so this is the lunchtime US West Coast break. We're gonna have an hour break. During that break, we're gonna have the breakout room right now for about 20 minutes, maybe a little less to get us back onto schedule. So we'll have like 15 minutes break now, during which we'll have the rooms hosted by members from the team that just did the presentation, and then and also by Jorgen, who was asking those questions there. So maybe he also has some ideas about how we could improve this project. And then at 12:20, sorry, at 12 o'clock, so in about 15 minutes, we'll have the first optional discussion led by Brian Bellendorf about volunteer opportunities. So I'll do the breakout rooms for like 15 minutes, and then I'll close the breakout rooms and then create new breakout rooms. I'll have one that's for that discussion and one that's for other socializing conversations. Thanks, everyone. And reminder that in order to join the breakout room, you need to like mouse over the number of people in the room, which I guess is probably 0 initially, and then click on join, the join thing that pops up to get into there. And you might also have to click on like, if it didn't pop up for you, or if you lost the window, you can click on like more breakout rooms, and then that'll bring up the selector for you.
You might have to combine the first 2 breakout rooms.
Yeah, everybody's joining George's. Yeah, if maybe we should do that. Maybe that's just something that came up first. All right, so let's do that. I don't know. I'll join that room and then tell people to go over. All right, thanks for the Q&A session, extended Q&A sessions. I'm gonna recreate the breakout rooms. So there's gonna be one for socializing and one that Brian is gonna be leading a discussion about leadership opportunities. So we will see you there. We'll do that for 20 minutes and then we'll have another 20 minutes hackathon planning. Hey everyone. In just a minute, we're going to, we just had a discussion about volunteering ideas, and we're just about to open a discussion about planning for tomorrow's hackathon in 30 seconds when everybody's forced to come back here, and then I can recreate the breakout room.
Matt, we're going till 12:40 to get back on schedule, right?
Yeah, we'll do that.
Okay.
Hold on a sec. Oh, wonderful. All right, well, let's see if I can do it from here. All right, here we go. All right, welcome back to the OpenZFS Developer Summit. Had a great little lunch break there with some side discussions on volunteering opportunities and getting started organizing the hackathon and what we can do to improve quality and fix bugs. Next up, we have a block with 2 talks. The first talk is by Imtiaz Mohammed, and he's going to be talking to us about ZFS performance on Windows. So I'm going to ask other folks to turn off their video and audio. Very nice. Hold on just a sec. I see somebody has stepped away from their desk. I have to find their name. There we go. All right. Great. Take it away, Imtiaz.
Yep. Thanks, Matt. Let me share my screen. I hope it is live now.
Yeah, that looks great.
Awesome. Thanks, guys. Welcome. This is Imtiaz. I work with DataCore. I've been managing a team in Bangalore, and they've been working on ZFS performance on Windows over the last 18 months or so. So I'm going to give a quick snapshot of what we have done there. All right, a bit about DataCore. We've been doing software-defined storage for over 2 decades now. Among other things, we have Windows server-based solutions for block storage. So that is what triggered interest in ZFS specifically the ZWalls around Q4 of 2019. Now, we've been working with Jorgen since then. We have received great support from him. Along with him, we managed to stabilize ZFS which is the Windows port of ZFS, of course. We made ZDB functional. We expanded the ZWall size. So there was some sort of a limitation in data types, which didn't allow us to create ZWalls more than, I think, 2 terabytes or so. So we could go up to 7 exabytes with that change. And then we did confirm the integrity of data that we are writing to ZFS using tools that are homegrown at DataCore. And that has kind of laid a good foundation to pursue the performance experiments that I'm going to talk about in this talk. And alongside, we did manage to introduce Perfmon counters. So Perfmon, as you might be aware, is a very popular tool in Windows ecosystem. So we were able to add a bunch of counters to it. And then we also instrumented the dprintf API, which is used for tracing. We use the WPP framework for doing the tracing. So I'm going to talk about that as well a little bit. And then at the bottom, you see the repo. So that is where you could get a copy of ZFS that we have been using if you were interested in checking it out. All right, so this has been the focus for us for the last 18 months or so. So measuring performance of ZWalls, especially when deduplication, compression, and encryption are turned on, and then identifying the bottlenecks and of course, fixing the bottlenecks. So how did we measure the performance? So we use this Dell EMC server, which had 128 GB RAM, 16 cores, 4 SSDs of size 370 GB each. And the repos that you see there, when I show you the slide where we compare the performance with the OpenZFS on Linux, so that's the repo that we used. And on Windows, of course, we've used the repo that I just talked about. All right, so so this is how we configured our pool and wall. We used up the 4 SSDs, and on the wall side, we chose to have only metadata cached, and we turned on the dedupe. We used LZ4 for compression. We used sync always. We used a block size, wall block size of 128K. Turned on encryption. We used the AES 256 GCM algorithm. The size of the wall happens to be 500G. And then we used disk SPD. It's a nice tool which works for Linux as well as Windows. Again, the links at the bottom, they can reveal more information. So it has a bunch of options. So you can see, you can specify the block size of the workload, the duration of the test, whether you want to disable the write caching, the latency, whether you want to track latency or not, the outstanding IOs per thread, the number of threads, you want to do random IO or sequential IO, the percentage of writes versus reads, the warm-up time, whether you want to randomize the content in every write, and of course the target, right? Typically a very standard set of parameters that you would expect to see in any IO tool. All right, now this is how the performance of ZFS Syn was a year ago. The first row is deduplication plus compression turned on ZWall. It was okay. I mean, you can see 128K sequential write was giving us around 400 Mbps. But then the problem started when we added encryption to it. So you can see that pretty much it has become unusable, and that is what kind of triggered the next set of experiments that we did. So how did we identify the bottlenecks? Well, one tool we used quite a bit was dtrace. I think it is something that is well known in Solaris and Linux community as well. Again, it has been there on Windows for a while, so the links at the bottom can give you more information about the tool. So using that tool, you could find out where is it that you're spending most of your time. So you could use it for tracing kernel code as well. So that gave us quite a bit of insight into what was happening. And then, of course, zpool iostat, arcstat. So those have been very well used tools for measuring the performance or doing the analytics as far as performance is concerned. The only challenge there is it may not be easy to do the charting or the graphing there, and that led us to integrate the output of zpool iostat or whatever zpool iostat does or whatever arcstat does in perfmon. So you can see those three highlighted counters there: OpenZFS cache, OpenZFS VDEV, and zpool. So those are the three counters that we added to perfmon. So that made it a lot easier to capture the output in the form of graphs that I'm going to show in a while. Again, if you want to read up a little bit about what is zpool, what arcstat does, there are a couple of links at the bottom. So this is how you could choose the VDEVs. They are qualified along with the pool name. And of course, you could choose the pools themselves. If you have multiple pools, you can see all of them here and choose whichever you want. And this is how the output will look like in the tabular format. So we have neatly prefixed the counters with arc, L2 arcs, log, and zil, as you can see here. And then VDEV. So again, you can see there are active async read writes. There is pending async read writes, reads, wait count, wait time, and so on and so forth. All of them neatly organized. And if you want to get the counters at the pool level, this is what you could do. And this is the charting that I was talking about. So you could collect all that information over a period of time and zoom into a particular window of interest. And you can select whatever counters you want to monitor. And this is a very valuable way of looking at the performance and looking at what is possibly causing the bottlenecks. So this really helped us quite a bit, along with the dtrace tool that I talked about. And then, given that we were just ramping up on ZFS, we also wanted to know how the code path is hit, what code paths we need to really monitor. How do we learn more about the code, right? So one great way is to do tracing, but then we didn't want the tracing itself to hurt the performance. So that is where we used WPP tracing. It's a very efficient way of doing tracing in Windows, very lightweight. So we did modify the ZFS installer.exe. You can see there. The options here that we added was the trace command. -LOX4 basically says I want to trace anything, and that is at level 4 and below. And the -S250 says the size of the file, the trace that we want to collect in MB. And of course, -P is the path. So basically we are saying, hey, I want to turn on a session where I can log the traces at level 4 or below. And it's a circular tracing of size 250 MB. And here is where the file resides. And when you're done, you can just delete the session using a -D option. So we added a trace event function. So you can see there are a few flags here and also an example. So this is how you could say, this is again a Windows specific code. So you could say, you could specify the level here and then the string that you want to print the parameters, just like you would use in, printf statement. And alongside, we also instrumented the dprintf function, because there are a lot of dprintfs already in the code, and they map to a default level of 4. So that means, like, using this command here, ZFS installer trace -L0x4, we could just see all the traces that were coming from dprintf, as well as any new traces that we have added. Again, if you want to explore WPP a little further, there are a couple of links in the bottom that you could pursue. All right, so WPP actually, it doesn't write the entire string or whatever you specify in the trace event or dprintf. It just does a mapping. It puts a GUID and the parameters. And later, when you want to actually view the ETL file, you could open it in one of the tools like TraceView. And at that point, it actually asks for the PDB, which has the mapping, the GUIDs. So that's how you decode the messages that are there in the ETL file using the PDB, and then you get these nice traces. All right, so now that we knew what was causing a problem using those mechanisms, it was time to remove them. The first thing we tried was to use the Intel's ISL crypto library, specifically the AES-256 GCM algorithm from it. It's an open source solution. The link at the bottom talks about that. So that has given us a significant performance improvement. It actually leverages the processor advancements, the AVX2 instructions. And along with that, we made a small change in the store port area. So basically, we tell store port, hey, if you have writes of 128K or more, you could give them in one shot. So rather than chopping it into 64K, we are capable of handling 128K writes at a time, because that's what the wall block size we used underneath. So it kind of aligns well. So that change also helped us a little bit. And then we did borrow a couple of changes from upstream. And just to remind, we started working on this a couple of years ago, and we didn't have OpenZFS 2.0 back then. So we had to borrow some nice changes that we learned from upstream into the ZFS in repo. So a couple of things that helped here were the Metaslab unload delay. So Metaslab, as you may be aware, is a way to keep track of the free or allocated spaces on the disk. So basically, you take a VDEV, you chop it into about 200 chunks, and you want to keep track of where is the free space in each chunk, right? So you do that using Metaslabs. So earlier the default was 8, and which means if you have not seen any activity happening to a particular Metaslab in the last 8 transaction groups, then you want to flush that data structure to disk. And that was kind of causing a lot of disk activity. So we bumped it up to 2048. So that kind of locks the Metaslabs longer in memory. So we don't do a lot of IO. So that really resulted in good performance improvements there. And then we actually again borrowed the dirty data sync % from upstream. So earlier it was 64 MB, so which means every time you have a 64 MB of dirty data, you would just flush it to the disk. So we bumped it up to 20% of 4 GB, which is kind of a configurable number. So that gives us more leeway to collect more data in the transaction group before writing it to the disk. So those are the bunch of changes that we did in ZFS in, and that is what the performance gains look like. If you look at the top 3 rows, we made significant gains there. And the bottom 3, although the percentage gains are there, but the base is so small that this percentage gain is not really very helpful as far as the practical usage of the driver is concerned. So there is still some room to improve here. So the top 3 are essentially larger block sizes. This is the size of the data, so 128K blocks, whereas the bottom 3 are smaller writes and reads, 4K and 8K. So I think that is where still there is a room for improvement, even in the current state of ZFSN. Now, how does it compare with OpenZFS 2.0 on Linux? That experiment was done, and you can see that the top 3 rows are still okayish, not bad. But then again, the bottom 3 is where we still think OpenZFS is doing much better on Linux, and definitely there are some bottlenecks in ZFS in that need to be removed. And it's possible that when we port OpenZFS 2.0 to Windows, those bottlenecks still exist. So that's something that we continue to look into. All right. So I talked about Jorgen. He's been fantastic in extending support Now we've already migrated the changes that I talked about, the performance counters, the WPP tracing, the store port change, all of them to a Windows branch of that repo, OpenZFS on Windows / OpenZFS. So the idea there is it's kind of a stage. So Jorgen takes all these changes, he reviews them, he requests any changes that are required, and then he bunches them up and upstreams it to the 2.0 whenever the time is right. So that has that model has helped us move at the pace we all can move at. So that's the model that we are following right now. And then going forward, we want to look at the 2.0 code base for Windows. Basically, try to stabilize it and then work on the performance improvements, just like we did for the ZFS in code base. All right, so that was the prepared notes. I would be happy to take any questions at this point.
Cool, thanks. It looks like there was one question typed so far. Paul is asking, did you run any performance tests without using dedupe?
Yes, we did try a lot of combinations, but then I don't have the data. Of course, we have limited time to talk about it as well. And we did run a lot of other tools as well. Like, this was not the only four corner test that we did. We ran tests using VDBench, HCA Bench, HammerDB, a lot of stuff. But is there a specific question around it?
I was just curious because I know that dedupe has its own bottlenecks associated with it, and if if we got markedly different results without dedupe enabled, it might point to different priorities for bottleneck resolving.
No, yeah, the latest test that we did was without dedupe, without compression, just 128K writes, and we still see some issues in ZFS compared to OpenZFS 2.0, especially when you're running it on NVMEs. It's not scaling the way we expect it to scale. So yeah, I mean, we have been running a bunch of tests, a mix and match of these features. What is ZFS in? ZFS in is the Windows port of ZFS.
Cool. Anything else to add? I see. Is Jorgen there? Did you pop your head up?
What's up?
Thanks for all of your work on ZFS on Windows, both Jorgen and Imtiaz.
Thank you. It's been great to watch data course progress.
Awesome. Thanks, guys.
All right. Thanks a lot, Imtiaz.
Thanks, Matt. Thank you, guys.
Yeah. So up next, we have Christian Schwarz, and he's going to be talking about a new ZIL that's much higher performance. And he pre-recorded his talk, which I'll play, but he's also here with us live. So if you have questions, feel free to type them. Christian, I don't know if you want to introduce yourself live before I start the video. If so, go ahead.
I think I introduced myself in the video. Actually, didn't think about that. So yeah, let's just start with video and then
all right, cool.
I come back.
Imtiaz, could you unshare your video and audio, please? All right, just a sec. I need to. All right.
Hi, I'm Christian. I've been around the community for a few years now, and some of you may know me from the work on zRipple. And this summer I graduated from university and I joined Nutanix to work on the Nutanix Files product. But today I'll talk about what I did in my master's thesis, where I looked at how we can make the ZIL faster so that it can keep up with persistent memory. But before we come to that, let's have a short recap on the ZIL's role in the larger ZFS architecture. As most of you are probably aware, the ZFS on-disk structure is a tree of block pointers, and whenever we want to update a file in that structure, we are going to modify a leaf block within an object, And since the block pointers checksum they're pointy, we have to propagate the change up the tree up to the uber block. And to make out of this crash safe, ZFS uses a copy on write mechanism. So as a concrete example, if we modify a level 0 block and we'd actually allocate a new level 0 block that contains our changes, and then we would need to modify the block pointer for that block in the parent level 1 indirect block over here to point to that new allocated block. And so we don't modify that block in place, but create a copy of that block again. But this time we reuse most of the block pointers except for the block that we just modified. And this will go on up to the uber block. And once the new uber block has been written, it's the new root of the on-this tree structure, and some parts of the old tree are now obsolete and we can get rid of them. Now, this is quite beautiful to look at on itself, but we can't really afford to do this dance for every single VFS operation. It would just be prohibitively expensive, both in terms of CPU time and write amplification. The solution that ZFS takes is to batch the changes of many VFS operations into transaction groups, and by batching these, we will amortize the cost for this full bottom-up update. However, with these transaction groups, we just got ourselves a new problem, because to make the batching work, we must wait for changes to accumulate in DRAM, but at the same time, it's not reasonable to block every VFS operation that happens until the batch is large enough. So what we do is we let the VFS operation return to user space immediately, and the TXG will then be written out in the background. The advantage of this is that all the VFS operations now operate at CPU or DRAM speed, and the downside is that the change will only be durable eventually. And there's not really a hard guarantee on when that will be or whether that will ever happen, or the ordering in which that will happen. And some apps just need that to function properly. For example, apps like databases need a mechanism for fast and immediate durability for the files that they modify. So they just can't wait for the current open transaction group to sync out, because in the end, there's a human waiting at the other end of the line. So the solution that ZFS takes for this is the ZIL. The idea is to extend the on-disk structure with a linked list head for each object set, and the nodes on the list that starts there are self-checksumming. And that means that we can append to the list independent of the transaction groups being synced, because we don't need to update any parent block pointers that point to these nodes, because they are self-checksumming. Now, when a VFS operation needs immediate durability, it will append a log record to that list that describes what happened in that operation at the logical level. And if everything goes well and the system doesn't crash, then the change is going to be written out in a transaction group as an update to the on-disk tree. And as part of the new transaction group, we write out a new list head that pops off all those log records from the list that are now obsolete, because they are part of the tree structure proper. But what happens if we crash before we finish writing out transaction group 5? In that case, the pool is in the state of transaction group 4 plus the log records that were written to the chain since then. And what we are going to do once we reboot is that we re-import the pool, and then we remind the block allocator that we actually handed out those log blocks for use by the ZIL, and this phase is called claiming. And later, once we get around to mounting the file system, we can then walk the chain of log records and reapply each log record to the data set. And the end result will be that the file system state, once we're done with this, contains all the changes that we promised as durable before the system crashed, and we can then mount the data set and let the application observe its state. Now, things are not as simple as that in reality. There are a bunch of complications, and I'm going to limit myself to the two important aspects that are relevant for this talk. The first is LWBs. The ZIL actually doesn't write individual log records, but it batches them together into so-called log write blocks. And so this linked list is actually not a linked list of records, but it's a linked list of LWBs. On blocks, we need those LWBs for block alignment, and because the log records themselves have variable length, as indicated in this sketch here. And also the batching can be used, and the batching of multiple log records into LWBs can be used to do some tricks on high latency hardware to make the ZIL a little less expensive. The second thing that complicate things are ITXs. The VFS operations actually don't write the log records directly to the on-disk list, because often the VFS operation doesn't even know whether it's synchronous or asynchronous. This is determined later when we call fsync. So instead, the VFS operation only creates DRAM log records, which we call intent log transactions, or short ITXs. And after creating those ITXs, the VFS operation will hand those ITXs over to the ZIL using the ZIL ITX assign API, and then the ZIL keeps track of those ITXs internally. And when user space actually does request immediate persistence, for example through sync or fsync, then the ZFS POSIX layer calls another ZIL API called ZIL commit. And the ZIL commit's job is to figure out which ITXs need to be written out to the on-disk log as log records, so that they are so that the semantics of the system call are actually met. Great. So we've covered the very basics of the ZIL. Now let's talk about ZIL performance on modern hardware. The basic principle is that the latency for synchronous I/O operations is the time that is spent on doing the VFS work plus the time that is spent on ZIL ITX assign and ZIL commit. Now, VFS and ZIL ITX assign are purely CPU and DRAM bound, but ZIL commit is a little more complicated. It does the work of figuring out which ITXs need to be written out to disk. So that's building the ZIL commit list, and then it has to take those ITXs from the commit list, convert them into log records, and pack them into LWBs. And then it uses the ZIO pipeline to write out those LWBs to the actual storage hardware. Now, and all of these are software steps that add overhead to the actual hardware latency for each LWB that is written. And historically, software overhead wasn't really a problem because the hardware latency dominated every other component in this equation. But with modern hardware, for example, the 3D crosspoint stuff for that is used in the Optane, NVMe, and PMEM drives, we get single-digit microsecond latencies for 4K synchronous random writes. And this means that even a few microseconds of processing time can easily become the bottleneck for ZIL performance. And we can actually observe this by configuring Optane PMEM as a slog device with today's ZIL. And in that experiment that we did here, we used FIO to generate 4K synchronous random writes onto a Z pool with separate datasets for each FIO thread. And then the pool had 3 enterprise NVMe drives configured as top-level VDEVs, so plenty of I/O throughput performance, and a single PMEM DIMM configured as a slog device. Now what we measured was the void clock time that was spent in each of the latency components. And what we could observe is that the vast majority of the time that is spent per IOP goes to LWB and ZIO overheads. Only about 20% of the time are spent on DMU and ITX work, and only 14% of the void clock time are spent on the actual interaction with the hardware and waiting for the hardware to store the data. And if we look at the what is being written to the disk, we could also observe that the LWBs are actually suboptimally sized. There's about 3 times write amplification going on per random write. So the LWBs that we're actually writing out are 12 kilobytes in size, whereas the actual payload is little more than 4 kilobytes. So there's a lot more nuance to this analysis that I'm not really able to present here due to time constraints. And it's also certainly not a workload that is representative of every use case for ZFS. But it's a good example for what is wrong with the current ZIL and why I believe we should re-architect the ZIL for modern hardware. And to summarize, there were 2 conclusions that I drew from this experiment. The first was that batching log records into LWBs is not necessary, at least not always. On PMEM, which is byte addressable, we don't need to adhere to the block boundaries. And even if we do, because we are on NVMe drives, for example, tricks like the batching and LWB timeout and all that stuff that we do for high latency storage hardware doesn't really buy us a latency advantage anymore. It's more of an overhead at this point. The second conclusion is that the ZIO pipeline adds much overhead for very little benefit. The problem is that all the connect switching that's going on in there adds latency and latency noise, latency jitter, and most likely it's also not particularly helpful for data locality. Essentially, the entire design is more geared toward high throughput than latency. So given these observations, I think that a new ZIL design is needed, and it should have the following properties. First, it should abandon LWBs as a concept and store individual log records instead. It may or may not do some batching under the hood to optimize things, but to get the lowest latency for fully synchronous workloads, we should just store individual log records. Second, we should no longer have pointer chains on disk like we do with the LWBs today. Instead, we should defer the serialization work, at least of the I/O operations, as much as possible to the time of replay, and this will enable more parallelism on the write path for independent operations. And third, we should bypass the ZIO pipeline to avoid its overheads and write directly to the storage hardware instead. We have seen the benefits of direct access to NVMe drives last year in Saji Nair's presentation, and we'll see later that they are even greater if we apply this to PMEM. So given these goals, I now present my proposal on how we can actually achieve them. The main architectural change that I'm introducing is that we should use the slog VDEVs in a different way. We don't give the slog VDEV space to the SPA, but instead we let the ZIL consume the space of the hardware directly. And the ZIL then constructs a storage substrate on top of it, and that is used to store all the log records of all datasets in the pool. And that storage substrate behaves like an unordered set of log records. You can put records into it, and you can iterate over it in an arbitrary order, and it will automatically garbage collect itself in the background to avoid running out of space. And we'll use the log records last sync transaction group to determine which log records need to be garbage collected. And on top of this very, very minimal interface, we then implement the actual ZIL functionality. The idea is that each dataset adds a bunch of metadata to each log record, and if we should actually crash, the replay code will then use that metadata to figure out which records need to be replayed and in what order. Here's a quick visualization. So at the time we write the ZIL commit will be writing the log records in some logical order, but the storage substrate is free to organize this log space however it sees fit. So it just has to ensure that it will find those log records again if we crash. And while we are writing new log records, the garbage collection will kick in the background, and yeah, this will just be how the thing operates all the time. And we hope that there's free space on the physical level at all times. Now let's assume that we crash. Then the replay code will scan through the storage substrate's contents to find records of the data set in question. It will filter out obsolete log records and then reconstruct a replay sequence. And that replay sequence is then applied to the data set to recover the committed state, just as it is with the current ZIL today. And if the storage substrate detects that if the storage substrate loses some log records, for example due to bit rot or data corruption, then the replay algorithm will have to deal with the fact that those log records won't show up when it scans the storage substrate. So data integrity is also covered here. So why is this more performant? There are two main reasons. The first is that we've eliminated write after write dependencies on the I/O path for independent writes. Of course, like if the writes actually depend on each other, they must have a mechanism to wait on each other so that replay can succeed. But at least we have the option to do independent writes fully in parallel now. The second advantage is that the storage substrate is just an interface. And this enables us to have a custom lightweight implementation that is specialized to the particular storage stack at hand and to the particular hardware. So for example, for PMEM, I implemented a custom allocation scheme and a data layout that is optimized for the ZIL contents, and I use PMEM native I/O instead of using the ZIO pipeline. So now that I've established the high-level idea, let's make things a little more concrete with an example. What we are seeing here is a visualization of the storage substrate's contents and the metadata of each log record. On the x-axis, we have the generation number, and we use it to encode logical dependencies between records. On the y-axis, we have the transaction group of the individual records. And the name of the records, for which we use a letter right here, is also a piece of metadata. It identifies the entry uniquely within a generation. And for clarity, we are using unique names for all log records in this example here. So at the beginning of our example, the source substrate was empty, and now we've added a log record, which we call A, and it's for a change in transaction group 4 in generation 11. And now we write another record for transaction group 5 in generation 12. And this record is called B, and its generation is higher than A. So this expresses a replay dependency of B onto A right here. Then we write another record C into the next generation 13. And while we are writing new records, garbage collection might kick in the background and remove records for transaction group 4, because transaction group 4 has been synced in the background. So this will happen, but the garbage collection is fully independent of the write path. So even while garbage collection is going on, we are still writing another record D. And D is actually for the same generation as C. This is new, and what we've expressed here is that D has a replay dependency on B, just like C does, but D does not depend on C for replay. Now we continue to write records, E and F, which also share the same generation number 14. So E and F don't depend on each other, but E and F both depend on C and D for replay. And finally, we'll write records G and H into a new generation and also starting some new TXGs. So the number is going up there. Note that at this point, we can observe that garbage collection is going to kick in pretty soon, because at any given point, there can only be 3 unsynced transaction groups. So at this point, it's clear that transaction group 5 has synced out, because otherwise there wouldn't be an entry for a log record for transaction group 8. So now let's recap and see what metadata we've observed here. We have seen the transaction group, we have seen the generation numbers, and we have seen the unique IDs for each entry, which are represented by the letters. However, this is not really sufficient to detect lost entries at replay time. For this, we use a counter per transaction group that, and to explain how these are computed, we're going to run through the example again and show which counters each individual log record has. So for the records of the first generation, all the counters are set to 0. And after we are done writing a generation, we sum up how many records were written in each transaction group. And this running sum is kept in a table called the counters table. Now, for the next generation's records, we will then use the counters table's contents as the counter values for each individual log record over here. So we can see this with entry B. We've copied the table into the entry B. And now again, after B's generation, so generation 12 is done, we do the accounting and account for the fact that we have written another log record in transaction group 5. Remember, this is a running sum, so we don't reset the table after a generation. Now, if there are multiple records in a generation, like generation 13, we use the same table in every record of that generation because, as we'll see later, these don't depend on each other, so they only depend on the last generation and every generation before it. So again, we just copy over the table, and at the end of the generation, we account for the records written, and this time we've written 2 records, so we have to bump 2 counters here. Now, and this will be, like, again, it's the same procedure for generation 14. We do the accounting again, and we write records for generation 15. Now, there's one interesting property here. The table that we store for generation 15 only contains the counters for transaction groups 8, 7, and 6. So we've dropped the counters for transaction group 5 and 4. And the reason is that we know that these have synced, so we know that we won't have to validate the counters later during replay. Okay, we've seen how the counters are computed. Let's now put them to use to exercise the replay code path. Let's assume that we crashed after we've written out transaction group 5, but before it was garbage collected. Then in that case, the records that need replay are the records D, F, G, and H. We ignore B and E, even though they are still present, because their change is already part of the main data structure. And if we attempted to replay them, the replay callback would fail because the replay actions that are encoded in these log records are not idempotent. So our plan is to replay D, F, G, and H, and then use the counters to detect lost records along the way. Let's first cover the happy case where we haven't lost any record. In that case, we initialize our counters table to 0 during replay, and then look for the first record's counters. And for each counter that is greater than the transaction group at which we crashed, the counters must match what we have in the replay table. So these counters are all from generations that are 5 or older, so there's nothing to check here, and we can just replay it. And after doing the replay action, we update the counters in our count so after we've replayed all entries in a generation, we update the counters table just as we would do on the right path. Now moving on to F, the counters for transaction group 5 and 4 can be ignored again, but the counter for transaction group 6 must match what we have in the table, and that is in fact the case. So we can replay F, and we can do the accounting and move on to entry G. And again, we compare the counters and can observe that these match. So we can replay G as well, and H, we can replay that as well. Great, so that was easy. Now let's look at the case of actual data corruption. Suppose some bitroid has corrupted and records E and F, then the storage substrate would not show them to us when we scan it to construct the replay sequence. We wouldn't even know that they existed in the first place because the storage substrate doesn't tell us about them. So for now, our replay sequence is going to look like D, G, and H. Now we want the replay algorithm to replay record D, but we mustn't replay records G or H because they depend on F, courtesy of the generation numbers. So let's see how this works out. We'll initialize the counters table and compare the counters for record D. They match, or they can all be ignored, so we can replay D and do the accounting. Then we move on to G, and the counters for transaction group 6 don't match in this case, so we cannot replay G. Now, since H has no logical dependency on G because it's in the same generation, we try to replay it as well, but its counters also don't match, so we cannot replay it either. And we'll stop replay at this point because we've reached the end of our tentative replay sequence. The end result is that we've replayed as much as possible given the constraint of the generation numbers over here. Great. And like what's important, like the important thing is that we can actually present witnesses for a missing entry or for a missing record. So G and H serve as witnesses that record F has been missing. If this was a little too fast or you want to revisit this later, I'd encourage you to either read the chapter in the thesis or look at this slide and the next, because they are basically summaries of the voice track. But what we are going to focus on right now is the concrete implementation and then later on benchmarks. So the short name for this entire project was ZIL-PMEM, and it's the product of my master's thesis. The goal of the thesis was to design a system that makes synchronous I/O in ZFS as fast as possible using persistent memory. So this was really a no-compromise approach on making synchronous I/O as fast as possible. We've already covered the high-level ideas and so on and the algorithms, and for the rest of the talk, we are going to focus on implementation and benchmarks. And there's a bunch of more material in the thesis if you're interested, in particular testing, validation strategy, and so on, and a lot more details about the benchmarking setup. I've already mentioned persistent memory a couple of times, and until now it has been more or less sufficient to think of it as a very fast type of storage, but to really appreciate the value that it brings to the table, we should have a more elaborate introduction. First of all, you might know it under a different name. There's non-volatile main memory or storage class memory, and these are all like this. The naming depends on which branch of industry or academia you're following. In the case of persistent memory, it's a concrete product name branded by Intel. So the idea is generally always the same. The idea is that instead of speaking a storage protocol like NVMe, you map the PMEM directly into the address space and then use normal load and store instructions and maybe some cache flushes and so on to perform I/O to it. So there's no storage protocol anymore. Essentially, your microarchitecture is what you use to talk to the storage directly. So this is a pretty different model of doing I/O than what we are used to in the storage space, but the PMEM has some very appealing properties for the ZIL that makes it worth taking a closer look. So first, it's very fast because there is less overhead than with something like NVMe, even if it's the same storage media underneath. So in the case of Optane, both the Optane NVMe drives and the Optane PMEM drives use 3D crosspoint media underneath. So basically, there's the opportunity to pass on those additional efficiency gains by avoiding the protocol overhead all the way up to ZIL commit and make this really, really fast. The second advantage of PMEM is that it's byte addressable. This is ideal for the ZIL because the ZIL log records themselves have variable length and are often very short. So with the ZIL on PMEM, we don't really have to worry about padding or block alignment or the space wastage that might result from padding up to a certain alignment. I've put some links up here if you want to learn more about the basic technology, but for us and for the purpose of this talk, these are really the most important characteristics. What we haven't covered yet is how we can actually reach that hardware in something like an operating system like Linux. So first of all, there are several operating modes for PMEM, and we're going to use the app direct mode for PMEM in the fstex configuration here. You can just ignore those details if you're new to the topic. What's important is that in that mode, the PMEM will show up as a block device node in the device.fs. And the kernel driver that provides this device node will then implement the block device I/O using the PMEM native store and cache flush operations and so on. And this will enable existing block device consumers to take advantage of PMEM performance without any modification. So for example, in the experiments on ZIL performance that I presented earlier, I just used the devPMEM as a slog device with the current upstream OpenZFS. But the idea behind PMEM really is about direct, byte granular, and transparent access to the persistent storage. So essentially, it's a full bypass of the operating system storage stack. And in order to support this, Linux provides the direct access APIs. In that case, the block device consumers can use these APIs to check whether the block device is actually PMEM, and if that is the case, then they can establish a direct memory mapping to the PMEM. And once the mapping is established, the consumer then can issue load and store instructions and cache flushes and so on directly to that memory mapping, and the operating system is completely out of the picture. So what we see in this screenshot here is an example from the ext4 source code where there is conditional optimization for PMEM or a different implementation of how we read data from a file if the file is actually on an ext4 instance that is deployed on PMEM. Great. So given this framework, the goal for the PMEM was to make it fully transparent to the user. So there should be no change in the zpool CLI, because in the end, like the devPMEM device still looks like a normal block device from the user's point of view. And ZFS should just switch over to the new ZIL architecture that I proposed and do the right thing if the stock is actually persistent memory. So now, how does this fit in the overall system architecture of ZFS? The PMEM will be added as a slog VDEV to the zpool, and then we'll implement our new ZIL stack on top of it. Now, we can't throw away the old ZIL code for a bunch of reasons. So the first step was to refactor the ZIL so that the different persistence mechanisms could coexist at runtime. And the result is that we have this thing called ZIL kinds, and I'll give more details about this in a minute. After that, I actually implemented the high-level ideas that I presented earlier. If you remember, we need a storage substrate for PMEM and an implementation of the higher-level algorithms. And the storage substrate in the PMEM is called PRB. And the high-level algorithms are implemented in a code module called handle. And the data structure for this handle, like, it exists once per ZIL instance. Now, to make these data structures easier to test, I implemented the PRB and handle as quite integral modules, and so there is some glue code necessary to integrate them into the ZFS code base. That's the yellow spot over here. And also I had to teach the VDEV layer at the lower layer about PMEM and initialize the PRB on top of it and so on. So there's some glue code involved there as well. Let's look at the ZIL kinds first. The idea here is to split up the ZIL code into two modules. There's the ITX module, which deals with anything that is happening in DRAM. So this would be the code that keeps track of unwritten log records, the code that figures out which records need to be written to the on-disk ZIL chain during ZIL commit. And the other module that I have is the persistence module. And that is all the code that actually writes the ZIL to some form of stable storage, determines the persistent data structure, and so on. That code is also responsible to read the ZIL after a crash, to interpret its contents, and to drive the replay process. So now with this refactoring, I could then introduce a vtable that decouples this persistence API from the general ZIL API. And like we can now have different implementations for this vtable coexist at runtime. And the name for these different implementations is called ZIL kinds. So now any ZIL kind will need some place to store information that is per dataset, like the LWB list head for the ZIL LWB. And the place for this, and ZIL PMEM will store some metadata in there so that it can find the log records again. So basically, we needed a place for this, and the ideal place for this is the ZIL header. And so with ZIL kinds, the ZIL header now becomes a tagged union, and the union tag is the enum value that represents the ZIL kind. So this also means that when we need to decide which vtable to use at runtime, we just refer to the union tag that we find in the ZIL header. This design is also backwards compatible because if the zpool feature for ZIL kinds is not yet active, then we can just assume that the dataset uses the old LWB-based ZIL kind and also use the old ZIL header layout. Now, I also want to spend a few minutes on the storage substrate implementation because I really think it highlights how simple that layer can be. When PRB is initialized, it takes a PMEM mapping and it partitions it into equal-sized chunks. Each of those chunks is then an append-only sequence of log records. So that when we want to write a record to PRB, we can just pick any record that has sufficient space and insert the log record at the tail of that sequence in a crash-consistent manner. And for garbage collection, we'll just wait until the chunk is full, then wait until all the entries in it are obsolete because the transaction group has synced out. And then we'll just reset the entire chunk sequence to 0 to the beginning, and then it can be filled again. And if we have a sufficient amount of chunks, then this can be a quite performant implementation. For example, we can have one open chunk per CPU so that there is no contention between parallel writers for access to the chunks. And if we make the chunks large enough, then we also minimize the need to coordinate different writers when they need a new chunk or when garbage collection runs and so on. And this is really all there is to it. To this design, of course, there are some DRAM data structures for bookkeeping and garbage collection and so on, but these are really boring details and they don't have much overhead. The key observation is that, at least for PMEM, the storage substrate implementation is very, very thin, easy to understand, easy to audit, and most importantly, has very, very low overhead. Yeah, sorry about bullet points here. Okay. So the next step was to wire all this up into a prototype that could be used to run the actual benchmarks. If you remember, the goal was to automatically activate the PMEM when we add a PMEM stock device. The problem with this was when the pool is already instantiated, then we'd have to switch over vtables while they are potentially in use. And I didn't have the time to cover this during the thesis. So the workaround was to determine the ZIL kind ahead of time when we create the zpool. So we have this ugly module parameter here where we, when we set it to PMEM, to the PMEM, and then create the pool, we'll check that the VDEV config matches and contains exactly one PMEM stock device. And once that's done, we set the root dataset's ZIL kind to the PMEM. And now, whenever we import the pool, we look at this root dataset ZIL kind and recover the pooled ZIL kind from that field. And of course, we'll check that the VDEV config still matches and then instantiate PRB on top of the PMEM stock space, and then the individual zlog t instances and the ZIL commit routine. If you just use a pointer in the spar to access the PRB. And obviously, we also need to prevent operations like zpool remove of the stock device, because we don't want to pull out the PMEM from underneath PRB while it's still in use. So all of this is quite hacky, I will freely admit that, and it probably needs more refactoring, but it was sufficient to get the job done in the sense that we could run benchmarks on top of it. Now, before we come to the benchmarks, let's take a quick look at how ZIL commit works in the PMEM. The first thing that ZIL commit does is that it acquires a mutex that is per data set, and then it uses the ITX code to get the commit list. Then it walks over the commit list, and for each ITX on the commit list, it will convert it into log record representation and then write those log records into the handle PRB data structure, so into the storage substrate. And we'll pick a new generation for each record. So at replay time, the replay dependencies are fully sequential. And this is just exactly what the same kind of dependencies that we have with LWBs. And this was just the safest choice to use here. Now, when we are done with this, we release the mutex, and the next ZIL commit call can start writing. And of course, if the datasets are independent, then they only need to coordinate at the storage substrate level, and we've seen that this can be made very efficient. Now, there are some points where we can improve this here. So one is to use something like ZIL commit waiters so that we can get a little more parallelism. We can do this by pre-computing the generation ranges that will be used writer, and then have the writers do the writing in parallel. The problem is that we need to change the APIs a little under the hood. So this can be done, but just hasn't been done yet. The other thing in the thesis, and I have some backup slides on this as well, is that I experimented with bypass TX layer completely to enable even more parallelism than what we can have with the commit waiters, but we don't have time to cover this here. So yeah, let's look at some benchmarks. We start with the primary workload of the thesis that were 4K synchronous random writes with a separate data set per thread. Again, like, I know this is not really representative for most ZFS workloads, but it's surely a torture test for the ZIL. So in this experiment, I compared the performance of 4 different configurations. The first configuration was the FSDEX configuration in yellow. And this configuration writes directly to the PMEM from user space. So we only have the raw hardware latency plus some syscall overhead. The other 3 configurations were ZIL LWB, ZIL PMEM, and async. They were all on a zpool with 3 enterprise NVMe drives and 1 persistent memory DIMM slog device. The ZIL LWB and ZIL PMEM use the respective ZIL kinds, and the async configuration has sync equals disabled set. So this is meant as a estimate for the upper bound of how efficient what we could achieve if the ZIL persistence code was maximally efficient. Okay, so now let's look at the results. What we can observe is that the PMEM achieves 130,000 IOPS with a single thread, and that is this purple curve over here, and that is about an 8x speed up over what we can achieve with ZIL LWB on the same hardware. It's just a software change. And we can also observe that the PMEM scales up fairly well to 400,000 IOPS with 4 threads, and this is still a 5.5x speed up over what we can achieve with ZIL LWB. Now, for higher thread counts, we see it to align with the FSDEX curve over here, and the async curve actually shoots up way higher. So what this means is that we are reaching the PMEM throughput limit at this point, and that if we had higher PMEM bandwidth available, we could increase we could potentially land even higher IOPS. I actually did that experiment in the thesis, and we reached about 900,000 IOPS with 4 interleaved obtained DIMMs. So that's pretty good. If we look at a little deeper at how the latency is distributed, we can observe that the PMEM the ZIL persistence now only takes about 25% of the void clock time of each IOP, whereas it was about 80% with the LWB-based ZIL. And in turn, this means that the asynchronous part of the ZIL, so DMU and the ITX work, now become the dominant components in the latency equation, and we need to optimize there. I also did some more realistic benchmarks. Most of you would probably call those still fairly academic, and I would agree, but it's really the best I had. I'm not going to go into each of those in detail. The gist is that they are all doing synchronous writes in one way or another, either through write-ahead logs or metadata-heavy sync operations and so on. And in contrast to the previous workloads, those all ran on one data set, so we can actually observe the impact of the mutex that is held in ZIL commit. In the comparison between ZIL LWB and ZIL PMEM, I could observe that the like single-threaded workloads, so RocksDB, Redis, and so on, they achieve pretty good performance, 5.8x speedup over ZIL LWB with Redis at 2.7 speedup, MariaDB at 2x speedup. And there were some workloads that didn't benefit as much, but in general, this is a pretty good result. If you crank up the scaling factor, so the number of threads that are simultaneously doing requests to these types of servers or doing put operations and so on, what we could observe is that the PMEM doesn't really scale linearly. Like if it would, then the bar in the orange bar for scaling factor 4 would need to be 4 times as high as the bar in scaling factor 1. But there's still a substantial improvement, so there is some scalability there. And the PMEM still performs better than the LWB in most of the workloads. The other interesting comparison is that between the PMEM and DM write cache. DM write cache is a device mapper target in the Linux kernel that you can use to configure a write-only cache for any block device, including other device mapper targets. And what's so appealing about this is that it has been explicitly designed for persistent memory and fast NVMe drives. But it uses a different architectural approach because it's a write-back cache, whereas the PMEM is really a write-ahead log. And the write cache is more of a block layer volume manager type of approach versus the PMEM, which is very tightly integrated into the ZFS file system. So it's exciting to observe the different performance of these different architectures. And what I could observe is that in the workloads that I looked at, the PMEM always lands within plus minus 30% of the throughput that could be achieved with DM write cache if we put XFS on top of it. So this is good because in contrast to ZIL LWB, we can actually be a serious competitor to this technology in terms of performance. And there are some benchmarks that perform very small writes, so RocksDB and Redis, and these performed better in the previous benchmark as well. But in this one, we also see a big advantage for the PMEM here, these workloads over here. And I think that the reason for this is that we have less write amplification in the PMEM because like XFS will see a block device underneath and will blow everything up to 4 kilobytes, whereas the PMEM will use the PMEM natively and write small log records directly. Now, these numbers are quite impressive. We should talk about some of the drawbacks of the PMEM before we wrap up, although we're running short on time, so I'll skip over some of those. First, the prototype that I developed in the thesis has a bunch of weaknesses. In particular, we only have one implementation of this architecture, so we don't really know whether it's a leaky abstraction. Then there's a problem with workloads that only do occasional f-sync operations, so we haven't really looked at those in the benchmarks, but there are a bunch of inefficiencies in the implementation, and we could work around those, but haven't done that yet. And there are also problems with, or at least unaddressed performance issues with parallel f-syncs on the same file, because we could get some performance improvements there if we use something like the commit waiters. Then there are some features that are missing, so support for native encryption would be a must, I think, if we upstream this, or if we consider something like this upstream, and mirroring of PMEM so that we get some redundancy for this log that is also not implemented yet. Also, the glue code is quite hacky, as you might have noticed, so we should probably revisit some design decisions there. And more importantly, the design has also some inherent weaknesses, and I would like to thank Alexander Moten specifically for his feedback on this. So the first thing is that it really doesn't address the elephant in the room, which is that the ZIL is very, very sequential and very strict about the guarantees it gives toward user space, and the PMEM provides those same guarantees. But if we were fine with relaxing those guarantees, we could potentially get a lot more performance, and maybe we can discuss this in the breakout room, whether relaxing the guarantees is an option for us. Another aspect is amount of DRAM allocations and DRAM to DRAM copies that are happening in the ZIL. Those don't show up with 4 kilobytes synchronous writes, but they do show up if you crank it up to 128 kilobytes writes or even higher. Then there's a bunch of mem copies going on that are not really necessary and could be optimized away. We don't have more mem copies than ZIL LWB, but we don't have less either. Also, like, there are some maintenance concerns. So if we have this custom space allocation going on in the source substrate, then we need to double think every time we do any tricks with space allocation. So for example, zpool checkpoint is a candidate where generated some headaches during the design phase. There's also no graceful fallback mechanism if this lock is full. So if datasets cannot be replayed immediately, this is an actual problem on small persistent memory devices like NVDIMM. It's not so much a problem on Optane because the smallest unit for Optane is 128 gigabytes. And the last thing is that the Linux DAX APIs are GPL only, so we cannot actually use those APIs in the ZFS module upstream unless you set the meta license to GPL. I'm happy to discuss ways how we can deal with this in the breakout room. And with that, I'm done with the talk. Regarding upstreaming, the PR is out. I've done my best to break the changes up into commits that can be reviewed independently. Regarding my personal commitment to all of this, as I said, that is all content from my master's thesis, and my employer is not involved with any of this at this point. So currently I'm only able to contribute to this in my spare time. But I'm quite eager to explain stuff to people and help if there's any interest in upstreaming some of the work. So yeah, thanks for your attention, and I'm looking forward to discussions in the breakout room.
Cool. Thanks a lot, Christian. We might have time for like one question now before we go to the breakout rooms. Joshua, I see your video. Did you have a question?
Well, I was gonna, would it be possible to do this in a MetaSlab instead of a VDEV, conceivably?
What is this question
specifically? Like if you had a pool which was a single VDEV pool and you didn't want to have a slog, but that pool was on a very fast storage device, could we do some of these optimizations, but within a region of the pool rather than in a slog?
We have this optimism, like upstream ZFS has the like dedicated MetaSlab allocation class right now. So in theory, like we should be able to change this so that we pre-allocate space from any VDEV. That should work. The problem is it needs to be directly addressable. So essentially, we would need to like do large allocations like SPA max block size allocations, and then we'd need some way to ask, given this block pointer to this SPA max block size allocation, please give me the memory mapping if we want to do this for PMEM, right? So yeah, at some point we need to bypass the I/O pipeline. If we implement an alternative scheme for NVMe, then things might be simpler. But at some point, like we need broad hardware address, whether that is a virtual memory mapping for PMEM or the NVMe logical block addresses.
Right, for the logical block addresses, that sounds a lot like the crash dump to zvols or swap, where we kind of allocate all the space and we can just say you're just allowed to go scribble on this part of the disk and go around the rest of the pipeline.
Yeah, it's going to be same problem that needs to be solved. Or is it solved? No, I wasn't aware. Like I know FreeBSD has something like that, but I don't think.
I
German
know Illumos
supports it, but I
has
might be
crash
wrong.
dumps working, right?
Ah,
Illumos
To rate-
has something like that, but I think not on the other platforms. Cool. I think we're just about out of time. So thanks a lot, Christian. And we'll have the breakout rooms now. Let me get it going. So in the breakout rooms, we'll have one led by Imtiaz if you want to talk about Windows stuff. One led by Christian if you want to talk more about ZIL and ZIL-PMM stuff. And then one led by Alan, who is an expert in FreeBSD, and one by Joshua, who's an expert in Illumos and other stuff. So you should have the pop-up now or be able to join a room. And remember to like mouse over the number of people, and then you should be able to click on join. All right, welcome back, everyone. Hope you had a good break. Next up, we have Mark Mabey and Seraphim Dimitropoulos talking about Zetacache, which is kind of related to the talk we heard earlier today about object storage. So if I could remind folks that are not presenting, Josh and Powell, to turn off your video. Let's see, is Mark, hopefully Mark is there.
I'm here.
There you are. I'm asking you to start your video.
Yep, I got it.
Sorry if permissions got messed up. All right, take it away.
All right, let me bring up the talk. All right, let's talk Zetacache. So as you heard this morning about a little bit about Zetacache, but most about the Zeta object store, I want to start actually by sort of reviewing a little bit about the object store, sort of set context here. As you heard this morning, we use cloud as a backend and have sort of infinite capacity because of that, but we trade that for high latency. Now this works really well for large block streaming workloads, but as we saw this morning, conventional wisdom says that's not a good model for highly transactional latency workloads, such as what we want it for, and mostly because of latency. But we know how to deal with latency in ZFS, right? You can mask your synchronous write latency with a slog. You can add a cache to mask your read latency like the L2 arc, and you should be good to go, except for those troublesome workloads. And that happens to be the Delphix use case. We have a small block size, average of 3K, means that a high proportion of metadata to data. We're talking about random IO workload. That means little IO consolidation or streaming. We're talking large working sets. So for example, a 50 terabyte working set, which would mean upwards of 18 billion blocks that we need to keep track of, and want to operate in a constrained memory size, right? Something on the order of 128 gigabytes. That means we can't keep all that metadata in memory. So the L2 arc is simply not going to do the job for us, right? It can't support the target working set, at least not in 128 gigabytes of memory. Those 18 billion blocks, on average, you're going to see almost 100 bytes of metadata per block in the cache. Means you're going to need on the order of almost 2 terabytes of memory just to manage the blocks in the cache. In addition to that, it has a FIFO eviction policy, which can be and is very ineffective when trying to size your cache. So even if you get a lot of data into the cache, you can't depend on unused data not clogging things up, right? It doesn't get evicted effectively. And in fact, you can have frequently used data that's in your cache that can get evicted and will be evicted eventually, just as it works its way through the FIFO queue. So you really can't size the cache to guarantee that you're going to get your working set to stay there. So we want something a little different. Our goal here is to get performance comparable to ZFS on EBS. And that means ZFS backed with S3 with a Zetacache based on EBS storage. And we want to reduce that 20 millisecond latency to 2 millisecond latency. So the high latency from the S3 needs to be averaged out to be a nice 2 millisecond latency, hopefully from our Zetacache. We want to support very large caches. We want to do that with small memory footprint, so on the order of 2 gigabytes, less than 2 gigabytes for that 50 terabytes of cache. So that means it has to be persistent by design, not as an afterthought. And we need an improved eviction policy. Rather than FIFO, we're looking at LRU. We want to be able to understand the cache size and its effectiveness. So let's talk architecture. So this is what the object agent looks like in ZFS, right? It's as George talked about it, it's ZFS object VDEV communicates through to user land to talk to the ZFS object agent. And within that, we have the Zetacache, which is where the ZFS will look first. The IOs will be looked for first. And if not found there, it goes off to look in the cloud. Why did we put the Zetacache up with in the user land as opposed to embedding it in the kernel as our other caches are? A few good reasons. One, this architecture, we wanted to keep Zetacache very close to the Zeta object agent for efficiency's sake, right? It's the primary consumer of this, and it made sense then logically to put it up there. It keeps us separate from the bulk of ZFS, so we could develop without having to inject a lot of new code path or changes into the ZFS IO pipeline or other parts of ZFS architecture. This is a separate entity completely. So it really gives us an easier environment to do our development because it's in user land. We are not dealing with a new kernel every time we make a modification. We are also able to develop in Rust, which is really nice. So it's helped us do our development cycle to be much improved. We can cycle things very quickly. I think I talked about these points, but one of the questions you should probably have in your mind right now is it going to perform? If it's in user space, can you perform? And the answer is, for us, at least right now, absolutely. Our needs really are only to be able to drive an AWS instance efficiently. Sorry. And most AWS instances do less than 20K apps to an EBS storage. And so we can do that now easily using a simple pread pwrite interface. So it certainly meets our needs, and we believe that it will meet our any needs in the future because it's possible to go in user space as almost fast as kernel using userland NVMe drivers, for example, or the IO ring interface. So we don't believe this is going to be a bottleneck to our performance here. All right, design. Basic components of the Zetacache are an index used to find data in the cache, some form of allocator to store data in the cache, and a checkpoint mechanism to create recoverable state. Now, if you're looking at this picture on the right, you might be thinking to yourself, you know, that looks an awful lot like a diagram of a file system. And file systems are hard. And if you're thinking that, you're right. That's true. Both those things are true. It does look a lot like a file system, and file systems are definitely hard. I know. As part of the team, we spent 50 engineer years before ZFS went to first customer ship. So it was a big effort. So we need to simplify our requirements. We aren't actually going to develop a new ZFS here. We're developing a cache. So we should step back and say, all right, what are the actual requirements we have for this storage? And that is a persistent searchable index that doesn't need to, it can't in fact be fully cached in memory, but that can support lookups in at most one read, right? Remember our goal here is to be able to satisfy or to emulate ZFS on direct storage. We need a block allocator that has a small memory footprint as well and is resistant to performance impacts from fragmentation. And we need some sort of way to transition from state to state so we can atomically update our on-disk state and maintain consistency. We use checkpoints for that. So let's look at some simplifications. One, we're only going to have one block pointer for each block, right? We don't need any snapshots or other, most of our metadata needs are pretty simple here. And in fact, we can store all our metadata in logs, right? There's no logical overwrites of data. We only have to do logical appends. And our logs are stored as lists of extents of large allocations so that we don't have a lot of blocks involved in our logs. Large log blocks where we simply add log elements to it, and we need to track sort of where the end of our last element is within the extent. And there's no need for a lot of indirect block structures to manage that information. So we're really developing a new from scratch simplified block storage here. And we also have a very simple interface, right? Our operational flow is lookups. I'll look up something in a cache, so you can look it up, query the index. If you find that, that entry in the index, then you're going to read that block from the cache. Or insert a new block where you're going to look it up, query the block, get from the block allocator a new space on disk for that block, and that block allocator will then insert a new entry in the index to say, here's that new block on disk. So I want to talk about the specific elements there, the index and the block allocator, because those are the most interesting pieces of the current design. I skip one, sorry. So the index is just a way to map a block ID to a disk location. And if you think about ZFS today, for example, in the ARC, we have a large hash table that does that for both ARC and L2 ARC. But that's a little bit of a complicated data structure to manage persistently, to have a persistent representation of. So we've chosen a simpler data structure to represent it, which is essentially a log structured merge array, which is a mutable ordered array or run of entries that we store persistently, and then we track pending changes in logged in memory, right? So whenever we want to transition from one index to the next, we apply our set of pending changes to the old run to produce a new run. So the old run is ordered by index ID, and we apply our pending changes to produce a new run on disk. In addition to that, oops, sorry, we skipped 2. So how does that look on disk? What does that run look like on disk? The run on disk is actually an array of chunks, where the chunk is sort of our logical I/O unit, and it's a large list of an array of entries, where each entry is that mapping of a block ID to a disk location. And then in order to be able to achieve our ability to read from this or look up an item in this with only a single read, we also keep stored a summary of the mappings, array of mappings, which map the first block ID in each chunk to its location, to the chunk location on disk. So that, and then we keep that mapping in memory. So that's our first lookup point. So when we want to look up a block in the index, we consult our in-core summary. We find it from it which chunk that block ID would be in if it existed in the cache. Then we can read that chunk and look in the chunk to see whether or not we actually have an entry for that particular block ID. All right. Now, pending changes are kept in memory in a pending changes tree. That's for efficient lookup and inserts. But we also need to keep that persistent. All right, we don't need that persistent because we don't want to lose pending changes when we panic or exit from the log. So we need to maintain a persistent version of that, which we call the operation log on disk. So whenever we adding entries in the pending changes tree, we add entries to the end of our log. This is a simple list of entries on disk, append only, and we can, this is allocated in large chunks, large extents on disk, and we are simply adding new entries as we add them to the pending changes tree. So to move from state to state, we simply create a checkpoint about every minute where we persist the pending changes. That means we make sure all our entries in the pending changes tree have been written out to the operation log. And then we store in that checkpoint a pointer to, or basically the metadata necessary to find that pending changes list, as well as a pointer to the index, which is already persistent on disk. So if we do have a crash, we lose less than a minute of cache data in the crash. This also represents sort of a unit, a point of consistency within the cache. So each checkpoint is a consistency point for the cache itself. So how does that work? Well, if we have to, when we reopen the cache from any point at any point, we first read the super block in a well-known location, which points to what the current checkpoint is, the current checkpoint block. We read that checkpoint block. A checkpoint block has essentially our metadata. Within it, it has a pointer to the index and summary, index run and summary, as well as the operation logs. These are all the components that make up our index. So what's going to happen is it's going to simply read in the summary into memory and ingest the operation log and replay it to reconstruct the pending changes tree. Once that's completed, we're now able to operate the caches normally. But we can't accumulate these pending changes forever, right? Pending changes represent a set of deltas to the index. And if we just continue to change and accumulate entries in there, it's going to get too large over time. So we need to merge those pending changes periodically into the current run to produce a new run, as I illustrated in an earlier slide. We trigger these periodically when we sort of accumulated on the order of tens of thousands of pending changes. And we run this as a low overhead IO task in the background, so it doesn't interfere with normal cache activity. So we read the old index in order. We apply the pending changes to it. When we come across, for example, an insert, we insert a new entry from the pending changes into the index, so the index grows. If we find a remove request, we remove that entry. Or if we have an access to a block, then we update the A time. I'll talk more about A times a little bit and how they're used. But the index also itself cannot grow forever. If the index grew forever, obviously the index is a mapping of where all the blocks are in the cache, and the cache is finite in size. So eventually you're going to have an index that represents a full cache, and we'll need to start evicting data from the cache so we continue to grow and absorb new entries into the cache. So we need to evict periodically. As I mentioned earlier, we'd like to evict based off an LRU algorithm. So this is where we use our A times, our access times. Every block has a last access time. This is incremented every 10 seconds. So the access time is really a measure of sort of artificial time from when the cache was first created. Every 10 seconds it increments, and every block that is inserted into the cache or read from the cache during that 10-second period is marked with that particular access time. This gives us sort of an approximation of an LRU if we create this histogram that you see on the right. Every time we ingest a block, we add the size of the block to a histogram at that A time. So on the diagram on the right, the numbers in this diagram represent gigabytes of data. So for example, at A time 1, we ingested 20 gigabytes of data. At A time 2, we ingested 30 gigabytes of data, and so forth. If we access a block For example, we are, let's say, at A times 7 and we access a block at A times 2, then that read causes us to change the A time of that block. And so we would, and say it was a 8K block, we would decrement our slot 2 of the histogram bucket 2 by 8K and increment slot bucket 7 by 8K, and that's how this particular histogram grows and shrinks and changes over time. Now, when we want to evict, all we need to do is look at this histogram and count up the space of the amount of data of space used by the blocks with particular A times. In particular, we look at the current A time in this diagram is A time 9. Count back until we have the size of the cache size that we want to try to maintain. In our example, we're trying to maintain, say, 300 gigabytes of data within our cache. So everything before A time 5 is now evictable data. That's the old data. It's A time of all those blocks are older than we want to keep around any longer. So we can evict based off of that. So that cutoff, that A time 5 represents our sort of a cutoff for eviction, which we will now leverage during merge. So remember, merge was already going through all of the blocks, all the index blocks, and all of the changelog blocks, pending changes blocks, to create a new index. And so it can also examine the A times while it's doing that job. And so it can, if it sees a block that it has an A time before our cutoff, that's an evictable block, and it becomes evicted. So you can see in this example here, we have a set of pending changes, we have an old run, and we're generating a new run, and we see that we have blocks at 4, 5, and 9 that are all have an A time of before 5. And so when we write our new run, we're going to come along and say, all right, 4, that's evictable, 5, evict, 8, 9. Well, we don't actually evict 9 because we also have a pending change for 9, which has a newer A time. So that takes priority. It says, all right, we actually have modified 9 since our eviction cutoff, and so 9 goes into the new index. All right. So now what's really kind of cool that now that we have this sort of mechanism for evicting blocks or for managing blocks based off of A times, this A time histogram, is we can actually leverage that same histogram to answer the age-old question of how do you want to size your cache? How effective is my cache at a particular size? So we use that same eviction, same A time histogram to generate a new histogram, which we call the size versus hits histogram. So size versus hits histogram leverages that eviction model. And so whenever we get a hit in the cache, we can say, all right, this block we just hit in the cache, what was its A time? Its last A time, not the current. It's about to be updated, of course, because we just did a hit. But what was the hit, the A time when we actually found it in the cache? That tells us essentially the A time which it exists, the latest A time it could exist in the cache. And now we could count up all the space that was before that A time, and includes that A time, and say, all right, that would be the minimum cache size we would need in order to guarantee that we would have hit on that block at this time. So that happens for every single hit in the block. We maintain this new size versus hits histogram, and using this, leveraging this information, we can generate a report that looks like this. So on the right, you see output from our Zcache report hits command. And this represents a little bit of a toy example. It's a small working set, but we're getting about 98% hit rate in this cache. But 97, look at the data on the right, you see that 97% of those hits are occurring within the first 3 gig of the cache, according to that graph on the right. So we could take a look at this and say, hey, you know, if I was to have the size of this cache, I could still retain and maintain a 97% hit rate. That's pretty cool. So it could actually tell you that I am, based off this particular workload, I have more cache than I need. I can get by with less cache. Now we could also now extend this idea and say, all right, not just maintain this information for the current cache, but if we extend our A-time histogram data, we don't throw away sort of the historical data that's contained within it, because we have, remember, we have the A-time histogram data records it for all of our A-times. We can choose when, if ever, to evict information out of that log, that data. We can use that history of size to actually say, well, you know, I looked up this block. Now, we also have to keep a little bit extra data in our index, of course, which are the ghost entries for blocks which we've evicted recently. But let's say we keep another cache size worth of data around that way. Now, when I look up that block, I can say, all right, the index, I looked up that index, that block in the index, and it said, no, I don't have that block, but I used to have that block. And when I had it, it was marked with this A time. So from our previous example, say it was A time 3, and I evicted at A time everything before A time 5. Now I can count up all the data in the A time histogram and say, all right, well, the cache would have been this big at this A time. And using that, I can predict then, all right, if I had a cache that's a little bit larger, I could have kept this in memory, and you would have had a hit. And that could generate a graph that looks something like this on the right, where we see that, yeah, the same cache size, same 7 gig cache, but now we have a larger working set, and we're only getting about a 68% hit rate in our current cache. But if we project it out into our ghost cache, we see that around 10 to 11 gig, we're getting up to 97, 98% hits. So this tells us that, all right, I could potentially get better hits. I get potentially up to 98% hit rates if I was to double the size of my cache. And that can be very valuable. Again, all this depends on being able to run this data for a period over which you're actually operating sort of with normal working sets to understand how your hits are going to work within your cache. All right, at this point, I want to change gears a little bit, and I'm going to turn things over to Seraphim to talk about the block allocator. Seraphim.
All right, can everyone hear me well?
Yep, sounds great.
Mark, are you going to be sharing your screen, space or mine?
Oh, sorry. Yeah, I need to stop share, don't I?
There we go. Okay. One moment. Cool. All right. So let's jump right in. So first of all, what does a block allocator do, right? The block allocator is a subsystem that determines where data should be placed on disk. And when designing one, there are like multiple things that we should be taking into consideration. Things like runtime performance. How quickly can we satisfy allocation requests? Storage utilization, basically making sure that we are making the most out of our hardware and minimizing any wasted disk space. Other factors like contiguity of allocations, where some devices like hard drives get a big performance boost whenever we try and allocate blocks contiguously on disk. And finally, the memory consumption of the block allocator's metadata. Basically, the block allocator needs some kind of in-memory structure to keep a track of what is allocated and free on disk, right? So we want to make sure that these structures don't take up too much memory and we play well with the rest of the system. So before I go ahead and go over what we ended up doing, I'd like to do a small recap and look at what ZFS already has in terms of block allocation. So the block allocator in ZFS is part of the storage pool allocator, or what we call the SPA. And what the SPA does is basically dividing each VDEV into 16 gigabyte regions we call metaslabs, from which we allocate and free blocks of arbitrary sizes. Now, these metaslabs are represented in memory with something we call range trees, and you can think of a range tree as a standard tree data structure where each tree node, it basically represents a free region on disk. Now, these range trees can get pretty big, especially for big pools, but even for smaller pools, depending on your workload or the history of the pool. So for that reason, we only keep a subset of all these range trees, metaslab range trees, loaded at a time on our system. Specifically, we only keep loaded the ones that we are allocating from, so we can find where the free space is on disk. But as I said, we only keep a subset of them loaded because we want to conserve memory. So this is more or less the scheme that the design that we have currently today, and it has served us well, and it continues to serve us well. But it doesn't mean that it doesn't come with its own flaws. Specifically, within Delphis, what we've seen is on our database workloads, which are mainly characterized by small and compressed random writes, we see that our pools over time having free space scattered all across their metaslabs. And because these writes are compressed, fragmentation is pretty high because we allocate all kinds of block sizes. And when capacity gets at pretty high percentages, it's just hard to find space. So distilling these kind of like samples into like actual problems, what ends up happening is that we're spending a lot of CPU runtime and a lot of disk IOs just constantly loading and unloading metaslab range trees. And the memory overhead is high because these range trees can get pretty big. And again, reiterating on the high capacity part, where allocations can start failing and gang blocks may kick in, which make fragmentation even worse and kind of create this vicious cycle. That's not to say that because of this, the SPA design is not good. It actually satisfies the requirements of a file system like ZFS pretty well. But for the Zetagas, we're designing a cache, which is different from a file system. So we went back and kind of reconsidered some of these trade-offs. Specifically, things like the contiguity of allocations, right? This is something important for hard drives, and file systems need to support hard drives. But now we're talking about the cache, like the Zeta cache, where we most probably going to be using something like SSDs or NVMe devices. So contiguity of allocation of this kind of device is not as important, and therefore it doesn't need to be a major factor in our design. Second part is the disk space utilization, right? We were talking about the SPA, the file system. We strive to make the most out of our hardware. Our goal is, 100% utilization. But for something like a cache, yes, disk space utilization is important, but it's not the main factor in the design. Everything is the hit rate, right? As long as your hit rate is high, as long as your hit rate is good, it means that your cache is working, it does its job. And finally, memory consumption. ZFS is a file system, and basically what the SPA tries to do is manage unlimited storage with limited RAM. Basically, so you can keep adding more storage to your systems without having to think about the RAM that you're actually using. And this is the whole reason why we do the whole dance with loading and unloading meta slabs. Now, for a CAS, this is still a very important concern. This is part of the design because it's a valid concern. But our goal is not as strict. We can be more flexible because we're talking about a CAS, right? Unlike a file system, you can actually blow up the CAS, not lose any data, take a temporary hit in latency, and potentially reconstruct your CAS in a manner that's more efficient for your system. So here's what we, after considering all of these trade-offs, here's what we ended up doing. Basically, block allocation on the ZCAS works like this. We take the CAS and we divide it into 16 megabyte regions we call slabs. And there are three types of slabs. There are the bitmap-based slabs, which are kind of like modeled after a true slab design, where all blocks are of the same size. And I have on the bottom left an example image of a bitmap-based slab, I say 5K blocks, where you can see like each slot is of equal size, regardless of its whether it's allocated or free. And then we have the extent-based type, where it kind of resembles meta slabs, and it's mostly used for block sizes that are bigger, but they basically contain variable sized blocks. And you can see on the bottom of the center, there's an extent-based slab picture with 20K block that's allocated, a 50K block, some free space, and a 31K block. And finally, the last type is the empty slab type. This is the completely unallocated slabs that can be converted on any of the other types on demand as we see fit. Now, I'd like to talk a little bit more about that. Basically, how do we decide what kind of slab types do we want and need? And what exactly is our allocation scheme on top of these structures? So what we do is we group our slabs by block size into what we call a slab group. Now, for any incoming allocations that are less than 16K, we have the slab groups that are backed by bitmap-based slabs, basically the bitmap-based slab groups. And we have a group for every multiple of 512. 512 bytes, 1K, 1.5K, 2K, all the way up to 16K. Where basically when I say it, the 2K slab group, I mean the group of slabs that are bitmap based that support 2K allocations. And then for more than 16K allocations, we have two extended base slab groups, one group for less than 64K and one group for more than 64K allocations. Now, this distribution of like block sizes into groups, it's not set to stone, it's actually tunable. But regardless of that, each slab itself may change its type and migrate between groups during the lifetime of the CAS. So just to give an example, it really depends on the workload. So let's say you just created your pool, you have your data, and you put your CAS in action, and the CAS in the beginning is empty. You start reading, let's say, a data set that has a lot of 3K blocks, and we start casting those blocks in the ZCAS. So we go to the block allocator and we keep requesting blocks of 3K. So what the block allocator will do is convert all its empty slabs to 3K bitmap-based slabs, put them into the 3K group, and start allocating and using the space in those. And then later, if for some reason your workload changes to 6K blocks, what the CAS will do, it's basically gonna start casting those and evicting the old 3K blocks, basically slowly freeing over time all these 3K slabs that it made, converting them to empty slabs, then converting them to 6K slabs to satisfy the 6K block allocation. Now, this was more of an example to just kind of like describe what the runtime of this scheme would look like. Most of the time in the real world, the things are not as black and white. Basically, you won't just have 3K incoming blocks or 6K, but most probably you're going to have like all kinds of block sizes being requested by the block allocator, effectively distributing all these slabs into all these different slab groups. And another thing that I simplified a little bit was that you won't as often see slabs getting completely freed up. Most probably you will see something that looks like the first row on this image here, where we basically have some slab groups that are like pretty full and other ones that are not as full. And in this specific case, I'm highlighting this kind of like new perspective that we have now on fragmentation. Basically, before with the meta slabs, we had this block level fragmentation where because meta slabs had variable length block sizes, we will have fragmentation at the block level. But now we've kind of like traded off that problem from fragmentation at the slab level, where we can have underutilized slab groups leading to stranded space. In this example, the first row, we see that the 3K slab group, has a lot of slabs, but it's not actually using the space within them that efficiently. And that's a problem, right? But for our CAS, our block pointer kind of like scheme is a lot simpler, right? Unlike the SPA and ZFS, where we have, this kind of like complicated graph structure of block pointers and direct blocks that's impractical to move around. Our blocks are fully indexed, meaning we have exactly one pointer for each block. And that can make it easy for us to defragment our data and free up slabs. And basically, when I say defragment, I mean literally locate the underutilized slabs, let's say these 4 slabs in this example, move their data around. In our case, we just moved them in this first slab right here. And we ended up freeing them to be used for another slab group, potentially the 5K or the 6K one, because these look almost full. So that's kind of like an overview, a high-level overview of our design. And that's more or less what I wanted to cover today for the sake of time. I just want to spend one last minute comparing our new design for the CAS to like what would have been if we were actually using the SPA allocator for the CAS. And with our new design, we get greatly reduced CPU and disk IO activity because we don't spend time loading and unloading the block allocator's metadata, specifically the meta slab range trees, right? And in turn, our performance is not affected at high capacity or even high fragmentation. Moreover, our memory overhead is greatly reduced because on average, we'll be using bitmap-based slabs and effectively representing a block on disk with only 1 bit in memory, right? Versus the 8 to 12 bytes that we are currently using today per range tree segment for the metaslab range trees. And finally, I just wanted to highlight that overall our design is a lot simpler, right? We have our requirements for a CAS that are in comparison a lot less than the list of requirements that you need to implement a file system. So it's not that we had this genius idea, it's more like we looked at our requirements and we came up with a simpler design. And reasoning about its performance is a lot more straightforward, and we hope that it's going to be easier to debug in production too. That's all I wanted to cover today. Mark, would you like to take it from here?
Yeah. Let's see. Let's go back here. Bear with me while I find
42.
The final slide. There we go. All right. So that's pretty much is it for the bulk of our material that we had to present. But I would like to leave you with a couple of thoughts. One is, could you modify Zetacache to work with traditional block-based storage? And I talked about our architecture and the fact that we had chosen to implement Zetacache in user space to be tightly integrated with the object agent. But I think, and I believe it is still possible that you could leverage Zetacache from in a sort of typical block-based storage configuration by injecting the cache check into the ZIO pipeline, so that at some point, once you're past the ARC and L2 ARC checks in the pipeline, and you're actually going out, starting to go out to disk, you could query even an up call up to Zetacache and say, is this block existence in some sort of fast storage there, and get a response back. So I think it is possible. Perhaps a more radical and interesting thought experiment is how could you use Zetacache as primary block storage and not just cache? And as I mentioned, and as Seraphim mentioned a few times during his part of the talk, we made a lot of simplifications, and those simplifications are dependent on the requirements of cache, which are things like, yeah, if we don't ingest that block, that's not a big deal. It's not the end of the world, because we're just a cache, and so you'll just get a miss and you'll go to the backend storage. Well, obviously, that's not going to be practical for primary storage. You have to ingest all blocks. So there'd be a lot of issues to work through, but it is kind of an interesting experiment to think about. And I think it's something we do think about occasionally. I think that's pretty much all we have for our slides here. Are there any questions we can answer?
It looked like there were a few that maybe you already answered, but maybe you want to retread those or summarize your answer for folks on the call.
Yes, I'll do that. So I got a question from Alan, and he was asking whether or not we could apply, when I talked about the A-time histogram and hits by size histogram, whether we could move that same concept into the existing ARC and do something similar there to be able to generate interesting reports and information about it. And initially I thought, yeah, that seems plausible. But then Matt pointed out that there is more complexity in the ARC. The ARC isn't just an LRU cache. It's much more sophisticated balancing cache between MRU and MFU data. And so it's going to be quite a bit more tricky to be able to do predictive analysis. I mean, you could do the analysis, I think, fairly easily on either the MFU or the MRU sides of the ARC, but the fact that it's constantly shifting back and forth based off workload, I think makes trying to reason about the whole thing much more complicated. So I'm not sure how easy it would actually be to try to do something like we've done for the Zetacache there.
The other one was about like when we're doing rebalance, is it better to just evict stuff?
Sorry.
The next question was that Paul asked was about like rebalancing versus evicting.
Oh yes, and the reason we prefer to rebalance there is again back to being able to reason about the cache. If we were just, it is simpler if we just say, yeah, we have 4 blocks in this slab, so let's just chuck it because that's only 4 blocks, right? And this is a cache, we don't care. And that would be an easier way to empty that slab out and free it up, rather than finding locations for those 4 blocks that we're trying that are left in there. But it's suddenly doing something like that begins to introduce more uncertainty now about how to reason about your cache, because now you're no longer maintaining a strict LRU policy in terms of evictions. And so if you're doing a lot of this kind of work of throwing away blocks like that whenever you need space, you really don't know how your cache is behaving. It's not even FIFO, it's just kind of a random eviction pattern. And so it kind of breaks our ability to predict. So it is certainly more efficient, but it's better if we can retain those blocks that are not eviction candidates yet.
Yeah, I think it's something that we could consider. The trade-off would be, obviously you're doing less IO. So
right.
I think that we need to, we haven't yet got performance results from how much eviction is really needed under, even hypothetical workloads. So, once we see that, how much rebalancing is needed under workloads and how big of a performance impact is that, maybe we'll have to reevaluate if we see that that is more impactful than we predicted.
Agreed.
Other questions for Mark and Seraphim? All right,
Yes.
Alan has another question. Yeah, so I think Alan's basically asking Seraphim about, could we apply the block allocator that you designed to regular ZFS meta slabs with having strict slabs and all that stuff?
And why haven't you done so yet?
I mean, I think one of Mark covered that a little bit on potentially using the Zetacache as backend for an actual pool, but actually changing the meta slab design right now. I mean, yeah, obviously we could try and doing that, but also things are a lot trickier. I would say on the SPA right now. So I can definitely see the benefit, but trying to have it depends on a lot of things, right? Sure, for some workloads it would be great, but we would have the design wouldn't be able to be the same. Because what kind of would you have slabs within the meta slab? What?
Yeah, I think that even if you let's say that you work through those problems of fitting the thing A into thing B and the complexity of modifying the current code, that's all theoretically doable. I think that one of the big challenges would be rebalancing.
Yeah.
Right, because with the cache, we can avoid most allocation failures by doing rebalancing before they occur. And then, if we really didn't want to avoid allocation failures, you could bump things up to bigger sizes. So I do a 3K allocation, but there's no free slabs and the 3K slab group is full. Well, try doing a 4K allocation, try doing a 5K allocation.
Right, or go to extents, yeah.
You could do that and it might give you some kind of weird results in terms of space usage, but that seems doable. The problem is that, and you can go the other way using gang blocks, which the kernel, already knows how to do. But the problem is, I think the problem would be that you might be able to get into a case where that is common rather than rare, where you might commonly have to be ganging, or you might commonly have to be bumping up to an allocation that's a much larger size. And to get out of that, you'd have to do rebalancing, but rebalancing is extremely non-trivial with ZFS. That's the BP rewrite problem.
If we had BP rewrite, we could do that.
But the rebalancing is almost trivial because with Zetacache, because we're already rewriting the whole index every once in a while.
Right.
So it's just while you're writing the index, you just look up and see oh, what should I be remapping this? Oh yeah, okay, great. I'll store that new location in the new index.
Exactly.
any other questions. We actually have gotten back on time, I think.
Yeah, I think we're
So we
close.
have time for questions. All right. I don't see any. Cool. Well, thanks, Mark and Seraphim, for that talk.
Thanks.
So we'll go to breakout rooms now for 20 minutes. After that, we'll have 3 more short talks. I adjusted the breakout room slightly from what I had published before, based on the fact that it seemed like there was a large concentration of attendance in a few break rooms previously, so I've slightly reduced the number of break rooms. But we'll see you back here in 20 minutes. All right, welcome back, everyone. Mark, you're going to turn off your video, I assume. There we go. Cool. So next up, we have 3 shorter talks in the last block of the day, and then but stick around for those talks, and also for after that, we'll have a socializing time that'll be breakout room roulette, where we'll just get hooked up with random people and share a virtual drink after the conference. So next up, we have Jitendra talking about improving ZFS send and receive.
Okay, and I would share my screen. Hello everyone, my name is Jitendra Patidar. I have long experience working on file systems. My learning on ZFS started around 2.5 years back when I joined Nutanix Files team. Nutanix Files is a scale-out file server solution built on top of Nutanix Core SCI platform. On top of Nutanix file servers, different type of file shares can be destroyed, can be deployed, and with respect to different use cases and workloads. So the file share level replication solutions this product has, and for that product, ZFS and receive is used. So today I'm going to talk about a couple of 2 optimizations we done for share level replication solution. So one of the optimization which we done around ZFS send block traversal, and the second optimization is for share level replications on the ZFS receive side. So I'm going to cover these 2 optimizations in today's talk. Yeah, before jump over to optimization, just brief of ZFS send receive. So ZFS send is a replication tool. It traverses through the block tree for given snapshot. It does searches for all the blocks for full send and change blocks for incremental send. And for those blocks, then it dumps records on send stream or the wire for receiver side to process them and replay on the target. So ZFS receive basically receives those records from stream and processes them and dumps, applies them on the target. So that's a brief. Now I'll talk about first optimization. So ZFS send basically, as I said, traverses block tree from the root of given snapshot. It traverses through corresponding objects, and for each of the objects, then it traverses down to the indirect blocks, non-L0 blocks, and then finally reaches to the L0 blocks. For L0 blocks, then it prepares corresponding DRR records and dumps on the send stream. Okay, so while traversing indirect blocks, basically ZFS traversal does prefetching. And it's basically to make traversal faster. So while traversing indirect of 128K size, it points to max 1024 blocks underneath, as each of the block pointer it has of 128 byte. So the current traversal code does prefetch of all these 1024 blocks. So this is too aggressive prefetch. So that's a problem, because if you are doing too aggressive prefetch, then it could have basically performance impact on other active workloads running on your system. And also it's possible that if you are doing very early and aggressive prefetch, the blocks which you prefetch for the benefit of send traversal, those itself get evicted. And so it's not much beneficial for traversal itself also. So the aggressive prefetch is not really helpful. Now I talk about the solution. So the optimization is in aligned to the controlling basically this aggressive prefetching we have in the traversal. So while traversing indirects, and we know it could have max 1024 blocks pointed underneath. So in place of doing bulk prefetch of all those 1024 blocks, do controlled prefetch in different slots. So like while you are traversing going to traverse first block, do prefetch of next 32 blocks starting from second block, and then when you go midway traversing these 32 blocks, like around 17 blocks, then you trigger another prefetch of next 32 blocks, and so on, so that you are doing a control prefetch, and the prefetch which we are doing primarily with the purpose of making traversal fast is still remains intact, and it still benefits. And other side, the other workloads which are running parallel in system has minimum impact. So that's optimization I have want to enable defined like ZFS traverse indirect prefetch limit is by default defined to 32, and it can be configured with respect to if any workloads have need of changing it to lower or higher value. Yeah, so I already have this these optimizations pushed to upstream. So this is part of the upstream master. Thanks to the reviewers, Brian and Amotic. Sorry if I named wrongly. So I'm new to the ZFS world. But thanks a lot for doing review, and this is part of upstream code. Let me go back to the. Yeah, so, and it is also part of ZFS 2.1 release. Yeah. Yeah, so that was the first optimization. Now I'm going to cover the second optimization. Before detailing on second optimization, just brief on the distributed share. So basically on Nutanix file servers, we support different type of file share. So one of the type of file share is distributed share. So distributed share is consists of multiple Z pools and data sets, and these Z pool data sets scattered across multiple file server VMs. So this is primarily built for home directory use case, and it's later expanded for other different industry enterprise workloads. So as you can see in the diagram, the different users' home directories are getting distributed across different file servers, and they are baked by underneath the Z-pool datasets. So that's a brief on distributed share. So I'm going to talk about second optimization, which is basically replicating these distributed shares from source to target. So as explained, distributed share basically consists of multiple data sets, Z-pool data sets, which are scattered across different nodes. So like in this example, I have distributed share with three dataset, dataset 1, dataset 2, and dataset 3, and each of these have. So basically, while replicating this share and corresponding data sets, it's possible that the change set to be replicated for this data set is not same. It could vary. So like in this example, you have 10 MB for dataset 1, and then 100 MB for dataset 2, and then around 1 GB for datasets 3. So now based on the replication throughput for send receive, which you get on the wire, for example, in this example, it is, I'm saying like we have like 10 Mbps throughput. So in this case, what would happen is replication of this data set would complete in different timelines. So like for first data set, it would complete around 1 second. Then for second data set, it would complete on around 10 seconds. And then last one would complete around 100 seconds. So the point is basically the replication of this data set would complete in different timelines. And if you are talking about share level consistency, because this distributed share on the source side is basically made out of these 3 data sets. So on the target, if you see the view of this share on the target side, it's basically all that particular snapshot which we are replicating in current timelines, that point of image on the target side. So basically, if these are completing in different timelines, the target side we see not a complete view of that particular snapshot. So basically, it's temporarily inconsistent. So this share level consistency is temporarily compromised basically for this use case. So now. So now I'm going to talk about this optimization. Before I jump into details of optimization, I would just cover a brief overview of ZFS receive, which would help us understanding the optimization. So ZFS receive basically in the begin part, it creates a temporary clone from the existing data set or the base snapshot for incremental, and from existing data set for the full receive. It creates new data sets as well if the data set doesn't exist. So and then it basically receives on the temp clone or newly created data set. So that's the receiving part is basically reading from the stream and then processing those records and applying on the target. Once receive processing is done, where all your change set is available on the target in the temp clone or newly created data set, then the last part, at the end part of receive, it just switches that temporary clone with a live data set and makes that received snapshot changes available on the live. Or in case of newly created, it marks that data set consistent and make it available. So the point is, as soon as you receive with respect to receiving and applying on the live, so as soon as your receive completes, your changes gets available on the live with a receive workflow. Now I would jump over to the optimization and the solution. So with respect to the problem, as I described for distributed share use case, which is consist of multiple Z-pool data sets and their replications completing in different timelines. So primarily we wanted to have the receive of these different data sets corresponding to share complete in same timeline, and we wanted to have availability of corresponding content change set available on the live in a controlled manner. So as a solution, what I have done is, as explained, the receive has 3 parts: begin, then receive stream processing, and then the end part. So basically after stream receive completes and all change set available on the target, just the end part is left to do. In that stage, I'm basically in the solution I'm proposing to break the receive, and breaking a receive is built on top of existing feature like receive resume token we have. So I'm using that functionality and building on top of that. So basically generate a token from that stage where we are just going to end the receive. So the token is generated such that it has, along with the existing content, it has additional fields to indicate that this is an activate token. Basically all the content has received on the target, just the activation part is left to do. So you can just, whenever needed to activate this snapshot which you have received target, you can do a later point of time. So, and then few other additional fields in the token, because we are going to activate this use this token for activation directly on the target. So we could need certain information which is coming from the source. So we keep it those flags and necessary info in the token itself to keep it handy while we are going to activate this snapshot later point of time. So with respect to distributed share use case, we would break basically all the receive for all the data sets, corresponding data sets. And once all those data sets replication completes, then later point of time when we want, we could activate this. it's also possible with this infrastructure and this optimization built in. Like if you are receiving a large number of data sets corresponding to share, and if any of the data sets completes in different timelines, you could delay activations to make sure the consistent view on the target. And also you could decide on if for any reasons, if transfer of any data set fails or any problem happens, and if you decide on not really activating the content received, you have control of that as well, because you could abort the data sets for which receive completed, but it's not activated. So you have, this gives basically control way of activation. Yeah, so with respect to implementation, I have two CLIs defined. One is in aligned to the breaking the receive at the end part. So -p is an option here, ZFS receive side. It's used along with -s, which is basically receive resume token functionality. So this optimization is built on top of that. So when you give -p along with -s, the receive breaks at the end. So workflow is like DMV receive begin, DMV receive stream them, and then at the end, DMV receive end, the receive breaks without activating, without switching the changes with the live. So, and it generates the token, which is, I called it resume receive activate token, because this is used to activate the resume and activate the snapshot which we have received on the temporary clone. So, and then finally, once you have those activate tokens available, you could use those, not token, but the target itself you can give with -a option. And internally, ZFS would do this optimization, would internally fetch the token from the target, and then prepares begin record and goes through the receive begin and just receive end workflow, which was left over to do with when we given -p option. So in our use case, as I said, we have multiple data sets underneath share. So those are scattered across different Z pools. So we can't do them, activate them within same transaction group, because they are scattered across the Z pools. So we needed a controlled way of activation on top of this infrastructure. So we have infrastructure layer which does control activations, and if necessary also does basically if any problem happens and don't want to activate, it just aborts the remaining data sets and so on. So I also have these changes available in my upstream ZFS repo. So this builds and functionally works as well, but I still have to clean up and do more testing to make it available master OpenZFS master pull request. Yeah, and yeah, so this is basically help doing a controlled activation of for our use case of distributed share, and it could be helpful in generic use cases where the shares are created with multiple set of Z pools and data sets. Yeah, so this is a diagram with respect to the problem. So now we basically receive on temporary clone, and once the receive for all corresponding data sets complete, and then we have control, and we know that we can activate this and make it available on the live. So we have control to activate this and get it available on the live. So that gives a consistent view for the share on the target side for the end consumers. And this also gives control to drop if anything happens on the wire, and if you not able to receive any of the data sets out of all underneath out of the shares, then you can drop the remaining ones and keep it consistent on the target side. Yeah, so that covers both of the optimizations which we have done around send receive. I can take any questions.
Cool. Thanks a lot, Jitendra. Questions? One comment from Dan saying, nice work in presentation.
Yeah, thanks, Dan.
Paul raised his hand. Let me see. Paul, did you want to ask a question?
Yeah. So I thought that the first optimization was definitely useful, especially on systems with lower memory count. Having access to sort of the capacity to limit the depth of that prefetch is a really good idea. I had some questions about the second portion of the talk. So as I understand it, the different data sets that are being used as part of your sort of notion of a share are potentially striped across different pools, which is why you can't have them all as like one data set and then just send them as a single unit.
Yeah.
And so my question is, why add this functionality to ZFS send rather than doing something at the orchestration layer where you like receive the data sets as clones and then swap them into the active position once all of your data sets are ready? It should be, I think, the same level of atomicity. Either way, you need to sync out a transaction group across multiple pools to get them all to be exposed at the same time.
Yeah, so basically you could have the workflow, as you're saying, driven outside, but while we are basically receiving, we have the mappings created from source to target, and we have already existing source shares and then also deployed. So when we are doing pool or then later on incrementals, I built on top of the existing receive framework which we have in the kernel. So it actually has the clone infrastructure, temporary clone infrastructure only. So I'm just building on top of the existing infrastructure, but similarly, you could do cloning outside, then receive that and then switch over to that one. But then you basically, I'm not sure it could become complicated with respect to the existing
Jitendra, can I pitch in just to answer Paul's question? So
yeah,
Paul,
sure.
I think that's possible, but we had a couple of other underpinnings there. For example, the FSID is something that we construct internally. So there's a lot of other things. For example, the dataset names that we pick are based on the share UUID and stuff like that. So a lot of other things had to be reworked if we went down the clone and promote sort of a thing. So it is possible, but the amount of work that we needed was much larger compared to what we have here.
Yeah,
I feel like there should be a way to do it where you don't have to have the new names be persistent, but it's possible that in your design, even having them ephemerally would be too much work, and I understand that.
Yeah. I mean, it's definitely possible because I see what you're saying, that you receive it in a clone and then you just flip it at that point. Yeah, it's possible, but yeah, this one gets a little tricky with the way we are handling the shared UUIDs and the
yeah, I think that's
file system.
It's an interesting idea, Paul. I don't think that it's possible with the functionality in ZFS today, because like you could do the receive as clone, like you said, but then if you have an existing share on the original one with the original name, there isn't a primitive that would let you like do the.
There's no rename. You can't do the % receive internal swap as an external consumer.
Exactly.
Yeah.
But I mean, it might be that would. I mean, maybe it would be better to have that be a first class thing where it's like, oh, I have a file system. It has a clone. Neither of them have any snapshots. Just like swap the contents of them, which is exactly what happens. When the receive completes. I think that the way that Jitendra's done it is a little bit more like it probably provides like a more complete.
It's a slightly nicer abstraction, probably.
Yeah.
Yeah.
And the general thing, like it might have so many restrictions that it ends up feeling kind of forced.
Mm-hmm.
and you have all these error modes, right? Where it's like, oh, like you tried to do the promote, you tried to do the swap, but there was a snapshot. Versus like with the receive, it's like, well, you already have to decide, are you blowing away snapshots after it or not? And then you either get an error or not. But if there are other use cases, I think that would be really interesting to have the more general one.
Doing it inside, it also gives control of not allowing snapshots in between the receives. So you can, because if you are one snapshot you're receiving, and if you allow creating another one, then you have to decide on which one to keep on top of base. If you are, so this doing internally, it also gives control of like not allowing new snapshots on target while you are receiving. Yeah.
Cool. Thanks. Sure. I know we went a little bit over time there with the Q&A, but one of the things I really like about the conference is that people get to talk about this stuff that wouldn't necessarily otherwise come up. So thanks for the time, everyone. And thanks, Jitendra, for your talk.
Yeah, thank you very much. Thank you very much, Matt. Yeah, and everyone.
Cool. So next up we have Sanjeev, and he's talking about adding logical quotas to ZFS.
Thanks, Matt. All right. This is something that came up as part of the files solution that Jitendra was talking about earlier. Earlier we were not using compression, so we had not enabled ZFS compression, because for us the compression was done at the back end on the Nutanix EOS platform. But then at some point we figured that it might be better for us to enable compression in files rather than doing it on the back end for various reasons. So as part of that work, one of the requirements that came up was the quotas need to be on the actual size and not on the compressed size. So if we look at the current the default implementation that we have on ZFS, the quotas are applied on the compressed size. So if compression is enabled, the quotas are applied on the actual blocks that are written to disk and not prior to the compression. So that was the thing that came in as a requirement, and we were trying to figure out how to implement that. So before we jump into the actual implementation or the changes that we made, let's take a look at what the default ZFS has in it. So each D node keeps track of the blocks consumed by that D node in DN used. So if you look at the D node fizz, it's essentially keeping track in DN used. And also in the block pointer, we have all the sizes. We have the logical size, we have the physical size, and A size, which is the allocated size on the disk. So the block pointer is fairly neat because we have everything that's needed there. Whereas at the D node, we don't necessarily have the logical size on it. What we have is the physical consumption on disk. So that was one shortcoming that we have to achieve what we wanted for the logical quota. The other thing that if we look at the user and group consumptions, those are maintained in the special D nodes that we have, which is -1 and -2, where we keep track of the blocks consumed by each user. It's an indexed access. It's essentially a ZAP where we index based on the UIDs and GIDs. Not exactly them, but yeah, sort of that gives you an idea of what's happening there. So, and for the dataset consumption, I think we are fairly covered, because at the dataset level, we keep track of both the compressed and uncompressed count. And we in fact use this for, ZFS uses this for the compressor ratio computation. And the space calculation itself is updated as part of the TXT sync done by these two routines, which is dnode did use space and do user quota cache flush. So these are the routines which are responsible for doing the updates in there. So that's some background on what we did, or rather what's present in there. And moving on to what we modified. So the changes that we needed were one, like we saw earlier, the D node, we need some field to keep track of what its logical size is. And we also needed to keep track of the logical consumption for the UIDs and GIDs. So those are the two changes that we needed. So for the D node, what we chose was the DNPAT3 in D node Fizz. So we picked that field to maintain the logical size. So we call it DNL used instead of as in drawing parallels from DN used, we call it DNL used, which is the logical used of that D node. So that's a new field that we added in there. And for the user and groups, so the user and group was essentially one value that we maintained earlier, right? It was just one value which told us how many blocks or how many bytes each of those users consumed. So I extended that, the value field, and added a second value in there, which is another 64-bit value, which sort of keeps track of the logical use. So that's an additional field that we added to the ZAP. Now this, there's a good chance that that the ZAP, which could have been a micro ZAP if the number of users is limited, definitely switches to fat ZAP in this case. But for all practical reasons, or for all practical users, you may not really have a micro ZAP there if in a real world case. So the number of users could be much larger, and hence it would already be a fat ZAP. So this was not a problem. Couple of reasons why. So that was one of the reasons why we decided to go down this path. The other option that we were looking at is probably use a different D node to keep track of the logical consumptions, but decided to go with the existing one, which is simpler and fairly less amount of change. So what we did in addition to these two things is added a dataset property, which is just a binary switch, flip on or flip off, so called logical quota. So if you say logical quota is on, all the enforcement code, which is when you're trying to do a DMUTX assign, that's the one where you check against the quotas. It would start using the logical quotas. Whereas if logical quota is off, it falls back to the current implementation that we have, which is you apply it on the physical block allocations. So those were the changes that we did, and couple of other things that we modified is in the VFS or in the VNOps, where the backend for stat, which is your ZFS get actor, there depending on the dataset value for logical quota, we switch to reporting the L used instead of the used, DN used. That was one change, and then the other change is in the ZFS user space, where it reports both the used and the L used in there. I made a small change in ZDB so that it reports both the sizes, which is the L used of the D node. So those are the changes that we made. And so some challenges we had was we were not able to convert the existing or start supporting the compression on the reason I bring in compression. Of course, ZFS does support enabling or disabling compression, but for our purpose, the logical quota, we were not able to enable it on the fly for existing data sets. So we switched to using it only on new data sets. So that was one change, or rather that was a challenge. There's a couple of other things wherein we had an interesting issue where our record sizes, or sorry, the sector size that we support was 4K. And if you had a smaller block, which is like 512 bytes, you'd just allocate, you'd still end up allocating a 4K sector for it. So had to fix that problem, because if you just went with the L size for all the computation, things go wonky when you have a large number of small files. So we had to make that wherein it's actually a max of L size and A size. So if you well, yeah, that's a fix, and I'm yet to bring that into the port. So at what stage is this work right now? We I haven't integrated this with the project quotas yet. I'm still working on that one, trying to figure out how this should integrate with that. The changes I've put it out on the link there, so you can go take a look at it. I'll be working on it for some time to make sure it integrates with the project quota. So I'll get that sorted out. That's pretty much it. Let me see if I see there's a question. Oh, I'm sorry.
There was a question about the previous one that I
previous one. Okay.
didn't
Yeah.
read out.
So yeah. So
yeah,
that's a change.
Go ahead. You want to talk about that and then take questions on this?
No, Matt. Yeah, we'll take questions for this one.
Cool. Yeah, questions for Sanjeev. I think this is really cool. You know, I did all the quota stuff way back in the day, and it's cool to see that it extended. One question that I had was what your plans are, or if you have plans to change the way that right now you're talking about a logical quota that controls the behavior of all the other quotas versus, I think we had talked offline about the possibility of keeping the behavior of the current quotas and adding new quotas that are like, logical equals 1 gig, logical ref used equals whatever, logical user used equals whatever. I was curious if you had thoughts on how doable that is, and if
it is. Yeah. It's sorry. Yeah. Thanks for bringing that up, Matt, from the offline discussion. Yeah, I missed that one. Yeah, but yes, it's definitely doable, because the way I would look at it for the general consumption is that this brings in an additional field in the D node, and now you have pretty much all the control, because your block pointers tell us what the logical size is. Now the D node also tells you what the logical size is. And at the same point, for every user and group, we can now keep track of the logical consumption. So once those fundamental counts are available, we could easily build up logical quotas on top of it as individual properties. So it's definitely possible in there. Today, for our use case, it was we just wanted a simple switch to flip it, whereas it can easily be extended to have additional quotas applied. So it's doable. Yeah.
Cool. Thanks. Alan, did you want to ask your question live?
Sure. I actually had a different question. Do you ever run into problems with users having quotas, and if they're very near the quota, the performance is really bad, like write performance?
Yes, we do see that. In fact, it's a little tricky with our cases where if you draw a correlation to what Jitendra was saying earlier about distributed shares, so we have slightly more odd problems in there, because the distributed share itself is actually scattered across data sets, right? So assimilating them sort of becomes a problem, and there are quota overruns that we see. But with respect to the usage, yes, we do see it dropping. So because every time you try to do a mutex assign, it sort of sees that you're close to it, and since we overestimate as part of the assign,
the overestimate, the inflation ratio is 24x the logical size, which is probably too much. Yeah, so I'll have a candidate patch that will improve that.
Oh, I saw that. Yeah. I think that makes sense.
But I was definitely interested in other people running into this problem. And the easiest way to tell is there's a K-stat under the DMU-TX that counts how many times the system stopped assigning because it thought the quota was full. And if that counter keeps going up, then you're definitely running into this problem.
Yeah. I saw your patch on that one. Yeah, it makes sense, actually. In fact, when we are computing, probably I should just bring this in, because so the logical size that we are trying to assign, there's a couple of other tricky things that we had to deal with, wherein whom do you charge the metadata or the indirect blocks, and how do we charge them, because those are kept in triplicate. So there's some compromise that we worked on, that we said if it's not a data block, then you don't charge for the duplicates and stuff like that. It's not directly in the context of your question, but yeah, those again, that's when I was looking at the inflated sizes in there, or the inflated estimates. Cool.
Alan, did you want to ask your other question, and then Mark?
Maybe let Mark have his question first, in case there's short on time.
I had a simple question. You mentioned that logical quotas only worked on new data sets, right? So you could have an environment where you had old and new data sets, where old data sets would have physical quotas and new data sets would have logical quotas. Is that correct?
That's true, Mark. In fact, we went a little further in our use case. I mean, for general purpose, yes, you could still do that. Between each data set, you could turn on logical quotas.
Okay, so does that mean that your code is able to distinguish and say, all right, I know this data set has a logical quota support, so I'll use those fields?
Yes. Okay. Because the property that I was talking about is a data set level property, the logical quota property that I referred to earlier. Yeah. This one is a data set level, so you can enable it on individual data sets.
Yeah. Cool.
Thank you.
And then my second question was about when you added the accounting for how much logical space has been used, does that extend to snapshots? Like currently, there is no L used property on a snapshot, but is there now in your code?
I'm not sure I got the question, because the LU
because the snapshot space used is like, that's how much space is unique to that snapshot, and then the other accounting values are around, like, how much space was written, how much space is written since some old snapshot or whatever, based on the dead lists, which is all kind of different stuff.
Basically, where that unique value, I think it's actually stored in the object as the field unique. When that's calculated, it'd be helpful to calculate the logical size of that data as well, and store that so that you could actually see the logical used on a snapshot instead of only the physical used.
I see. Okay.
And if you're already adding other stuff to the dnode, it may make sense to do all of that in one go rather than separate.
Okay. Yeah, I'll probably have
data set rather than the dnode, but
right. Yes, sorry. I think it's in the dir obj or whatever it's called.
Right.
Cool. Well, any other questions before we move on to the last talk? All right. Thanks a lot, Sanjeev.
Thank you. Thank you, guys.
And the last talk is by Alan and Mark, who are conveniently already right here. And they're going to be talking about VDEV properties. And this will be the last talk of the day, but stick around for socializing time after that.
All right, there. So hello, my name's Alan Jude. I'm CTO at Clara, and we do FreeBSD and ZFS development. And today we're going to talk about VDEV properties. So as anyone who's used ZFS for a while knows, properties are a great way to express administrative intent. Basically for the administrator to tell ZFS how the administrator wants ZFS to manage the things, whether that's what compression to use, what the quota should be, or whatever different aspect of the file system volume or pool that you're trying to control is. And the user interface for properties is also very rich, allowing you to extract data from those properties as both human readable, as a human interface, but also provides nice machine readable output that you can hook up to a metric system or something to that effect. And so after playing with that for a while, I decided that VDEVs should have properties in that same vein so that you can control them and also get information out of them in both human and machine readable ways. So to start, I was like, well, what properties could we have on a VDEV? The first, when I started looking, was that in the struct VDEV that each VDEV has, there's a whole slew of counters that provide a lot of really interesting data about how many reads and writes and frees and other operations have been done on that VDEV. And those even percolate up to top level VDEVs. And so there's a lot of useful stuff there, but even other more stuff that's built in that's not necessarily exposed, like the enclosure path or the physical path to that device, rather than just the VDEV's name. So by exposing all of those, you're now able to get all that information about one or more VDEVs in this nice human and machine readable output. Then we added some writable properties, so you can actually control how the VDEV works. And then user properties, so you can store whatever arbitrary kind of key value data you want to store about a VDEV. And in my case, I actually store the partition scheme as a property. So when I'm replacing the disk, the automation can pull out and apply that same partitioning scheme. And the other thing I've always wanted was there's a lot of data in the zpool status output, including a bunch of counters for each VDEV about how many read and write and checksum errors it's had. But the output format of zpool status is not very conducive to machine reading. And so by exposing those properties, we can now read all of that in a more machine readable way and hook it up to metrics and monitoring and so on. So to start, the number of properties you can actually set on a VDEV is pretty small. What we have hooked up so far is a comment where you can just put some arbitrary free text about the VDEV. The path, so this is normally, dev SDB or dev, disk by ID and the path. But sometimes you want to change that, and you don't necessarily have the ability to export the pool and re-import it with the -d flag to force it to pick up the VDEVs from a certain directory. So basically allows you to change the path in the zpool config that it will try first for opening that VDEV. So next time you import it, it should pick up from the correct path. And then in a few minutes, Mark will talk about the allocating property and how that works. And then, as I mentioned, we have the user properties. So you can just set whatever extra information you want to control about a VDEV in there. And then the future, one of the original ideas we had was moving some of the per VDEV queuing information. So like maximum number of asynchronous reads that are outstanding, moving that from a currently that's a system-wide tunable into a per VDEV tunable. So if you had, say, a pool that mixed some hard drives and some SSDs, you could have different values for those different things, different VDEVs. And then for reading, there's quite a few properties that I managed to expose. In addition to being easy to get the device's GUID and its ID, you can get the physical path or the enclosure path, the serial number of the disk, its parent VDEV and its child VDEVs, and how many children it has, how big it is, how much of it is free, how much of it is allocated. The boot size property, I don't think that feature made it over from Solaris yet, or from Illumos, but where you can control when ZFS partitions the disk, how big of a space it leaves for the EFI, but also, the age shift of the device, how many read, write, or checksum errors or initialization errors, IOPS of each type, bytes read and written of each type, the expand size, the parity level, so you can, query a random VDEV and find out if it's RAID Z3 or RAID Z1, how fragmented it is, how big it is, its current state, and whether it's in the process of being removed. Basically, anything that's kept track of in the VDEV-T is now added as a property so that you can inspect it easily. So if you do zpool get all, the pool name, and then one or more VDEV names, or the special keyword all-VDEVs, then it'll print out a bunch of this information, and you can see, I have a VDEV here, 64% full. It's got 512-byte sectors. It's a 16 gig virtual disk. You see the original device name, its actual dev ID, the path, etc. And you see its parent is the pool itself, so it's a top-level VDEV. And you can see number of read and write operations and so on. The properties are persisted in a per VDEV ZAP. That ZAP already existed. It was added as part of the device removal code. So VDEV properties doesn't require any new feature flags. And that top-level VDEVs, so the meta VDEVs like MIR or RAID Z, can actually have properties as well. So you can apply properties to the top-level VDEV rather than just leaves. And now we'll let Mark take over.
All right, thanks, Alan. Do you want to stop sharing?
Yep.
All right, so I'm going to talk about the allocating property, which is one of our writable properties. The allocating property, as Alan said, is turns allocating off. It applies only to top-level VDEVs because that's the only allocating VDEVs you have in your pool. And VDEV has to have allocatable space in order to be allocating or non-allocating. The default, of course, is on. All top-level VDEVs can be allocated from by default. And setting it off prevents future allocations to the VDEV. So that means the remaining space on the VDEV is now unavailable. This obviously is going to impact the total available space in the pool. I'm going to talk some more about that here in a minute. One of the constraints with this property is that you must have at least one allocatable device in your pool. All right, this isn't about read-only pools. This is about allocating or non-allocating of a device. And so if you had were able to turn all devices as non-allocatable, that kind of would pretty quickly lock up your pool. So the primary use case for this new property is device removal. All right. So the current device removal process doesn't expose any notion of allocation directly or non-allocating directly, but it does it implicitly. So when you request device removal right now before this property, what happens is that the device removal code verifies that there's space available for device removal, and then it marks devices non-allocating internally. So it's an internal trigger that it has that allows it to set it non-allocating on a per device level, and then it removes the device by moving the contents of that device to the other devices in the pool. Then you could remove another device, etc., in a one device at a time sequence. Now that we have this property, and the reason we have this property is now you can actually do this sort of at a more efficient level. So if you want to remove multiple devices, you can set non-allocating or allocating off explicitly on those devices for all the devices. And that will immediately verify there's enough space to remove all those devices from the pool. And now you can issue your removals one at a time for those devices and not worry about getting new data into the device you're about to remove a little bit later. So let's go through an example of how that works. So here's a simple scenario. You have a config and you have a couple of old 4 terabyte drives, and you want to replace those with a bigger, faster 8 terabyte drive. Let's assume that each of your 2 drives are half full at the moment. So you want to move. Hello, there we go. Oh, that's not good. Why am I not getting my animation? All right. Well, you want to replace your two drives with device C. So the first thing you do is you add your new drive to the pool. And so dev C is our new 8 terabyte drive. And we have dev A and dev B as our 2 existing 4 terabyte drives, half full. This is the first step, is you're going to replace your 2 drives. And this scenario I'm going through first is without the properties. This is the traditional sequence you'd go through right now if you were to remove 2 drives. And so when you issue the z-pool remove tank command, you see that it becomes non-allocatable, and you see that it moves its data from that device onto the remaining drives in the pool. So in this case, dev B gets a terabyte and dev C gets a terabyte. So we've copied 2 terabytes of data, but we've done it inefficiently, because now when we go to move the second drive, instead of removing just 2 terabytes off of drive B, we now have to move 3 terabytes from drive A to drive C. So in the end, we end up moving 5 terabytes of data in order to get 4 terabytes of new data on drive C. So with the new algorithm, we're going to do the same scenario, except this time we're going to apply the allocating property, or the allocating equals off technique. So we add the drive, and now we set allocating off for A and B. And we can do this because we have drive C, so we still have capacity in this pool. And drive A and drive B are now non-allocating, but no data has been moved yet. We now issue a remove command for drive A, and its 2 terabytes are again of data are moved off. But in this case, all that goes directly to dev C, because dev B is non-allocating. So we do 2 terabytes of copy. And now when we remove dev B, we only have 2 terabytes of data left to move, and those 2 terabytes go to dev C. So we were able to move the 4 terabytes and only move 4 terabytes of data, rather than having to copy 5 terabytes of data around. So this is an optimization, and you can imagine this could get pretty significant if you're doing a larger transformation on your pool. If you're moving or replacing a bunch of drives with newer drives, potentially, you could end up copying a lot more data around if you have to do it piecemeal. So for configurations with many drives in them, this can be a huge optimization. So why allocating, though, instead of read-only? Well, mostly because this does not make a device read-only. All right, it's still possible to modify a device that's marked non-allocating. You can still update its labels, and you can still even do scrubs on it, right? In place, data manipulation is still possible. It's just we simply have disabled the ability to allocate new space on that drive. It also impacts the pool space in a way that's different than what you would think of for read-only. All right, and the expectation for read-only would be, I am only going to remove the unused VDEV space. Only the unused VDEV space from that drive would be subtracted from the available space, meaning in our previous example, we had 4 terabyte drives. If you were to mark one of those 4 terabyte drives read-only, your expectation would be that your available space would decrease by 2 terabytes because that was available space on those two drives, on each of those drives. So each drive would give up 2 terabytes of space from the total capacity of the pool. But the actual impact from marking something non-allocating is different. We subtract the entire capacity of the drive from the available space. Now, this is two reasons for this, really. One is it allows us to accommodate for an existing rewrite. So, for example, if you were to mark a drive as non-allocating and then were to rewrite that data, your expectation would be that I wouldn't run out of space because I would be overwriting logically the data that's on that drive. But in reality, you're going to have to rewrite that someplace else because it's not allocating now. And so this sort of takes care of that potentially odd oops moment you might have. But more importantly, from our perspective, this is because we are actually using this as a precursor to device removal. And so we need to make sure there's not just the capacity of the drive, but there's a full drive capacity available. So we're also, when we move that drive content, we're going to make sure we have enough space for it in another on the pool. Also, in general, just allocating is a more accurate name for this feature. I think that's all I had specifically talked about with respect to allocating. Alan, you want to come back in and talk about your last couple slides here?
Yeah.
Do you want to take control or do you want me to drive?
Yeah, sure.
All right.
Yeah. So yeah, the question is, what else could we do with this? Sorry. So the things that I've thought about that haven't done yet is obviously having support for channel programs to change the properties like you have existing. And a very commonly discussed idea is this concept of having a mirror read bias. So if you have a mirror with one of the members is actually remote via MetroNet or something, you'd want to try to have all the reads actually come from the disk that's local and not the one that's far away. But you might actually want to, rather than just say, in this mirror, prefer reading off the first member, you might actually want to say, each mirror member has the host ID of the machine that should prefer to read from it. So that when you actually do fail over to the other side of the metro, it knows, oh, I should actually read off what is my local disk, not what was the local disk of the original machine before we failed over. Another thing is currently libzfs does caching of all the pool properties, but does no caching of VDEV properties. I don't know if it makes sense, especially since pool properties, there's kind of one list and there's only ever one pool per libzfs handle. And so, the amount of memory is kind of fixed. But with VDEVs, it could be a lot to try to cache or to, automatically load all those properties as soon as you open the handle. So it might not make sense, but it might be interesting. We've talked previously about having inheritance for properties. So far, there's not a use case where it is worth the hassle, but there might be. And another idea we had was currently the counters, like number of reads and writes and so on, are not persistent. They're just come from the VDEV-T. So they're only persistent through importing the pool. So if you export the pool and import again, the counters go back to 0. There might be some counters where we'd actually want to persist those and keep track of long-term how much has been written to this SSD, or how much have I been using this cloud so I can compare it to my cloud bill. But we'd also have to balance how frequently do we want to persist those out, because we don't want to create more write load by keeping track of how much write load there was. But the other question for the kind of takeaway is, what other settings could be VDEV properties? There's quite a few tunables where we started to think about maybe these could be per pool or per VDEV, but what other things about a VDEV would it be interesting to be able to control? One of them that I've thought of is the special VDEVs, the metadata class stuff. Being able to control, if I have multiple special VDEVs, I want to say this special VDEV only holds metadata and this one only holds small blocks, or this one's only dedupe or whatever, with a bit more granularity than you have now. Or maybe that ends up being, rather than one setting that says it takes this type or that type. Maybe there's special metadata equals on or off, special small blocks equals on or off, or whatever. Another question that I've brought up a couple times is how many properties is too many properties? Do we end up wanting to have some kind of a flag on a property that's not necessarily hidden, it's just not displayed by default? So if you get that one, or we have a second keyword after all, like really all or something, to display them, there's a bunch of them where maybe it doesn't make sense to display this all the time, but if someone wants it, they should be able to get it. And then Pavel had asked about being able to set VDEV properties at pool creation time. Definitely could use some input on what the command line syntax for that should look like. If I'm specifying a pool and it's going to have 4 different VDEVs, and I want to set this property one way on this one and a different way on a second one, how am I going to express that on the command line without making it overly complicated? And you can find me on Twitter or whatever if you have questions after.
Cool. Thank you, Alan and Mark, for closing us out with a great talk. Are there any questions? I see there was one that you answered already. Jorgen, would you like to ask a question?
Oh, I had a short one for Alan, actually. When you said you can change the VDEV property name,
the path,
path, right? But that does not include physical path.
Correct.
Okay.
The physical path is that one's a bit more OS specific. Like I think on Linux, it ends up being literally like the PCI path or whatever. And it's a bit different, but the path in this case is like dev, whatever that you're opening.
Yeah. No, the old one out here is obviously Windows, because path is cosmetic only. Like it's purely a nice string that the users see. It doesn't use it ever. And physical path is where we hide the ugly thing. But on the other hand, I'm not sure I want users to be able to change, the partition offset and the path name. It's kind of scary. So yeah,
if they need to be able to, it's easy enough to make the property not flagged read only, and then they can.
Okay, I'll think about it. But thank you.
Cool. Any other questions? All right, then thank you, Mark and Alan. And that's all the presentations that we have today. So before we go to socializing, I just wanted to remind folks that we have the hackathon tomorrow. If you would like to keep in touch, otherwise there's the Slack channel for keeping in touch after the conference. Slack will be probably a great place to organize what we're doing with the hackathon tomorrow. So look in your email for that link. I'll also send the link out in email tomorrow morning with a link to the Zoom, which will be a different link, and the Slack invite in the email that'll go out tomorrow morning. Hopefully I will manage to only send out one email that has the correct info tomorrow morning. Sorry about that little snafu this morning. Maybe this is a great chance to plug for people to help organize. Like, I always find it motivating when I see people doing a job and I'm like, I could do that job better. So I think that it is not hard to see that you could do a better job than me at conference communications. And I would welcome someone to take over and own that for next year. And there's a lot of other stuff like that. Also, I would say, there's a lot of other things that maybe you don't feel like you could do a better job than existing people who are doing it, but it's still valuable for you to help out. There's a lot of jobs that first of all, we all tend to underestimate how good we're going to be at something compared to other people when we see them doing it. So, it's not necessarily accurate that you would do a better or worse job than somebody else who's already doing it. But also, just taking the load off of existing people is hugely helpful. And you don't know what the impact of that is going to be going forward. Maybe it'll help that person to spend more time on other things that are also very valuable to the project. So bringing more, more helpers, more contributors onto these organizational stuff is going to be great for the project long term. Last thing, if you're watching on the live stream, I'm about to turn off the live stream, but if you would like to participate in the hackathon, there's still time. Even though the website says register by November 5th, if you register before tomorrow morning, you will still get the email with the links to the Slack and hackathon Zoom, and we would love to have you join us for the hackathon tomorrow. Awesome. So with that, I'm going to figure out how to stop recording because there's nothing else that's really going to happen in the main session here. And turn off YouTube. Maybe I have to do it here.